Okay, so let's go live at the YouTube as well.
Yeah. As soon as I share screen, something funny happens. Yeah.
Yeah, it's coming up. I think. Good.
But I don't see it.
I can see you.
Right.
It's your browser. I can see your browser. You just move your PowerPoint there. Should be.
So you can see my screen?
Yeah,
you
I can see. Yeah, I can see your screen. Yeah. Yeah. Now it's fine now. Yeah,
you
I
can
think.
see? Okay. All right. Great.
Yeah.
Okay. I'll be back in 2 minutes.
Okay. Yeah. Sure. Oh yeah. Okay. Let me see.
Guan, you need the screen back or is it okay?
Yeah, it's okay. I don't need screen back.
Guan, this is recorded, right? Because I have it's a really nice program, but
Yeah, it is recorded. Also, it's streaming at the YouTube as well.
Right. But I cannot do live. That's the thing that because of the my schedule. But I want to listen to several of the talks.
Yeah, sure. You can watch. I can send you the link. Yeah, let me see. Okay, maybe we can get started. So today is the second day of our workshop. It's a great pleasure. We have Professor George Kanidakis from Brown University. Today, he's gonna give a talk on the approximation functions, functionals, and operators using deep neural network for diverse applications. George, yeah, I can start.
Thank you, Guan. Can you see my screen? Can you hear me?
Yes.
Okay. Thanks everyone for getting up early. And I wanted to have a treat for you, some coffee, since it's early in the morning. And I want to start my talk with this coffee. It's a real application. And I want to emphasize that our work, especially this last few years, emphasizes real applications and real applications problems like this one are not well posed. For example, in this one, I convinced this company, LaVision, that I'm partnered with, to do an experiment. You can see the experiment here. They have many different cameras from different angles, and they get a Schlieren photography, which means basically they obtain the gradients of the temperature, of the density of my coffee cup, the espresso coffee cup. So my job is to just take their video, a 3D video of the Schlieren photography, and obtain the velocity field and the pressure. Clearly, a problem like that, it cannot be solved with classical methods. It's an ill-posed problem. We don't know the Rayleigh number. We don't know the boundary conditions. The only thing we have is the video. Okay, so I'll get back to this problem, but I want to set up the stage to say that I'm interested in problems that we cannot solve with classical methods. For example, in physics for a long time, and in mathematical physics, we've been doing problems like this, where we pretend, certainly in applied mathematics, we have a well-posed problem, and we have some data that give us the boundary conditions and the initial conditions. We know all the material properties, we pretend anyway, and we tackle the problem. More often than not, what you have is cases like this. We know some of the physics, or we can resolve some of the physics. For example, in turbulence, we may know the Navier-Stokes equations, but we cannot resolve the physics at the high Reynolds numbers. But we could have data. We could have data which could improvise for data-driven closure models, for example. And then the extreme, of course, is in social systems or very complex systems where we don't really know the description, the mathematical physics, but we may be able to get lots of measurements. So I'm going to talk correspondingly about two things. One is the PIN, physics-informed neural network, and the other one will be operator regression. And in between, I will talk about also functional approximation. So that's sort of the outline of my talk today. Now, what is a PIN? If you haven't seen it, it's a composite neural network. It uses data and it uses physics. The data corresponds to minimization of some norm. Here I show you the MSE norm, but I will talk about different norms a little later. And of course, if you have a lot of data, this is sufficient to do even regression, of course, classification. However, we know in real problems is that we don't have enough data. We don't have 10,000 measurements of the same quantity everywhere in this spatial domain and time domain. So we have to resort to physics. That's what my group pioneered. I now have a patent on this, that we are able to take this variable and encode the physics by doing automatic differentiation. So we don't have to do grids. We don't have to do the like we usually do the approximations. The space and time is continuous, and we can obtain the differential operators, and therefore we can take the residuals. Now we minimize the residuals again in some norm. It could be the L2 norm, the L1 norm, the relative L1 norm, or the H1 norm. And then we have we take a weighted sum of this, and that the loss function that we set up. Okay, so PINs have been a huge success in industry. I didn't work in the industry before. I work now with many. NVIDIA, of course, has their own codes. ANSYS, the powerhouse in finite elements, are turning into it. Companies like Cummins do engine companies, Hitachi, General Electric, Bosch, Siemens, TSI, they do flow visualization, LaVision I talk about. This company here, Analytica, is a new company in the AI domain, and they're interested in buying all our patents, 4 or 5 patents we filed last year on solving, as I said, real problems using various extensions of pins and deponents. I want to go back to my coffee, my favorite example, early in the morning, as I said, and I want to show you just this one picture here from our science paper a couple of years ago that we demonstrated how you can combine, let's say, some passive scalar that you observe, in this case, the images of Schlieren photography of the cup of the espresso. And then you postulate a model. You have to have a model. The model could be a parameterized model. Here, for example, we say that the Schlieren photography will correspond to this passive scalar. And then we have the Navier-Stokes models in 3D, in this case, for the coffee example. And then we couple it. We compute these operators using auto differentiation. So it's very simple. But not. I want to point out here that, and this is what we show in this hidden fluid mechanics in this paper in Science, that you can have the data only in an arbitrary domain. In that domain, you are able to infer both the velocity and the pressure. And I want to show you the example. Here is my coffee espresso. It has a neural network in it, as you can see. So this is the data I can reconstruct from the temperature gradient. I get the temperature, then I match the temperature. So I match the temperature that is the passive scalar, and correspondingly, I can compute, or I can infer rather, the velocity and the pressure in 3D domain here, just for visualization purposes. So this is a paper we published recently in the Journal of Fluid Mechanics, and the point is again to demonstrate that this type of very simple framework, codes are about 100 lines, can solve real problems. So that's why the industry, as I said, is a big success with industry. Turns out pins are also favored by academics because they can write more papers to extend the applicability of pins. Pins are not sitting idle. We're not sitting idle. We are also evolving. We're developing new things. This is a deep Kronecker neural network. This is not just for pins. This is for all neural networks, where basically we extend this idea of adaptive activation function. So you can see here, every neuron will fire at its own rate, and you can have a decomposition, composition like that. Now, one manifestation of this Kronecker neural network is what we call the rowdy, like the noisy, the noisy activation function. So we take, let's say, the hyperbolic tangent, as I show here in the first layer, we superimpose some sinusoids on it. This here, the frequency could be a trainable parameter, the amplitude, a trainable parameter. And the reason we do that is because there are some problems, multi-scale problems, multi-rate problems, high frequency problems, which standard neural networks were not able to approximate because what is called the spectral bias. Just something like we have in Fourier methods, you first resolve the low frequencies, then the high frequencies, but because of the tough training, you may not be able to reach the high frequencies. This way, you reach the high frequencies. Now we have the theory in this paper, which will appear in neurocomputing, that shows that if you have this adaptive activation function, it turns out that you can avoid bad minima. So that's rigorous theory, and the training is much faster. So problems like people trying to do homogenization now, it can be solved directly from data using very high, because you can tackle high frequencies. Another extension of this method is space-time decomposition. As we said, neither space nor time are discretized, but here I show you how you can actually do parallelism in time, which is a very tough thing to do for PDEs. As we know, parareal is an algorithm that doesn't work really well. So here we have one domain, the blue domain, and then we have the dolphin domain. As you can see, both are non-convex domains. This is very difficult decomposition, but this is easily done using X-pin. X-pin basically takes the residual on one side, let's say the residual here, outside, and the residual on inside, and you penalize that. And that's how, of course, the residual has to be continuous because it's zero. So that's the only stitching that you do. In the process, what you have is actually two different neural networks assigned to two different GPUs, and this can be parallelized. So we recently wrote a paper on parallel pins, and this has been extended to 128 nodes, which with almost perfect weak efficiency. Also, you can see here, solving the Berger's equation, there's no sim. It's a seamless integration of the domains, and you have very little communication between processors, just the residual that you have in the loss function before you assemble the loss function. You do it like that. Okay, so I'm not going to talk about. We have a paper, a recent paper in Nature Reviews that talks about pins and other manifestations of physics-informed learning. You can deal with stochastic PDs, fractional PDs, and so on. And I just told you about extent pins, but I want to say something about the math behind this, and that is we have been experimenting with different norms in the loss function. So this is a very simple case of a linear advection equation, just to demonstrate that if you change norms, you may and are able, to, of course, to train the network, you will get better results. For example, this is the solution, and this is the derivative of the solution using the L2 norm. And I don't know if you can see the numbers. If you use this norm here, this mixed norm, it's like it looks like an H1 norm in time and X. If you use this norm, you can see the errors are an order of magnitude smaller, both in the derivative, also in the solution. So what norm to use and what loss function to use is still an open question. Recently, I presented this yesterday at the Air Force meeting. We have developed a meta-learning procedure, a meta-learning algorithm, where we actually learn we're learning with the bi-level optimization, we learn the loss function. So it doesn't have to be L2, it doesn't have to be L1. You actually learn it on the fly. And you can parameterize the loss landscape, or you actually have a neural network to do that. So that sometimes pays off, as I said. The first paper on the convergence and generalization of physics informed neural networks was published here in this archive. And we proved for elliptic and parabolic equations that we have convergence, pointwise convergence, strong convergence in the L2 norm, even if we don't satisfy the boundary conditions, just like the coffee example. If we satisfy the boundary conditions, we show that we have strong convergence in the H1 for this type of equations. I also wanted to mention this great papers by Sid Mishra from ETH with his students, and that they address both the forward problem in pins and the inverse problems, and they use bounds in quadrature. They treat the collocation points we have as in a certain way. It's easy to follow paper, this one. I have another paper, a recent paper, where we derived error estimates for linear PDs. And we did that both for the continuous formulation and a discrete formulation. A discrete formulation here, let's say you pretend that you are on a lattice, and in both cases, of course, you need stability and existence. You need to have a large network of, and in addition, you need the discrete norm stability for the discrete formulation. But we have both a priori and a posteriori error estimates. So this is also in the archive. In the second part of the talk, I want to show you what we actually need in real life. And this is a real example of a destroyer simulated as a destroyer, a US Navy destroyer swimming through Sea State 8 in the Atlantic Ocean. So this elevation, the stochastic elevation of the sea that you see here of the Atlantic Ocean, corresponds to the spectrum in the Atlantic Ocean. If it's in Pacific Ocean, something different. So anyway, we have a specific stochastic excitation. You have a body, and it takes about 1 week using classical methods, CFD methods, for a MIT graduate, my collaborators, to do this simulation. So obviously, you cannot use traditional tools for autonomy. You need real-time answers. And the answer that you want is a time series that gives you in advance, a little in advance, what is the motion of the what would be the motion of the vessel, the rolling, the heaving, and so on. So it's basically what you want to forecast is a functional, okay? And I was wondering, I was teaching a class 5 years ago, and I said, could we actually approximate functionals with neural networks? And if you look at that literature at that time, it was really a mess. Everybody was saying something in their blog that was inconsistent. And then finally, I found this this jewel paper by Chen and Chen from Fudan University in Shanghai, where they show at that time, 93, the year that the Saipenko theorem also came out, and other approximation theorems for functions. They show that a functional also can be approximated with a standard neural network, even with a single hidden layer. And that's for 1D case, but also they have also the n-dimensional case. So as you can see here, the standard neural network can approximate its functional with arbitrary accuracy. So that means that now, how do you do that? Well, it turns out that if it's a single hidden layer, you need a lot of neurons. We know that even for functional approximation. But if you have a deep neural network, and in this case, because of the time series, it makes sense to use a off-the-shelf LSTM or sequence-to-sequence, like RNN type networks. So what you do here, you input the stochastic excitation, different stochastic excitations. You record, this is supervised learning, you record, let's say, the 3 most important degrees of freedom. As you can see, these are stochastic responses as well. And then after you train the network in 0.01 second on a laptop, not 1 week, but 0.01 second, you can actually forecast the motion. Here's one stochastic excitation. This is another stochastic excitation on the right. And underneath, you may see the CFD that takes about 1 week to get a response like that. So that gave us so we thought maybe we can actually do something more ambitious. We can increase the level of abstraction. Can we approximate operators? Okay. So we wrote this paper, which appeared in 2019, how to approximate operators. And by operators, we mean just standard explicit operators in math, all the math operators, integer calculus, and as well as other calculus like fractional calculus, PDEs, so implicit and explicit operators, operators which are black boxes, like a social system, for example, for which we don't know how to write. So this is also for identifying black box operators or gray boxes and so on. Now, here. Okay, so it turns out, so what's the difference, of course, with the function is that now instead of a finite mapping like this that we have in image classification, we go from infinite dimension to an infinite dimension. So the operator is in between. So I already talked about this. It turns out that Chen and Chen, 2 years later, in 1995, also had a theorem for this, for a single layer. But a G in a nonlinear continuous operator, if we have inputs functions from a compact set, as you can see here, can also be approximated with a somewhat different neural network with a single layer. Now here you can see a term like this, which is associated with the input. U is the input in input space V, which is compact. And then also the output here, output is a continuous output, a G of U of Y, as you can see, that's what we're trying to approximate. So it's a composite network, input and output. You sample the input at, let's say, M points, we call those sensors, and then you approximate also the outputs. Therefore, you have a continuous approximation of the operator of this nonlinear continuous operator in a compact set. Later on, I will show you some theory that removes these constraints, but for now, this was sufficient to give us something that we could actually realize in practice. So what we did is actually take the theorem of Chen and Chen and construct different operators. We didn't know at the time what was the best operator. We settled on this one that I have marked here, where the branch, which is associated with this term here, relates to the input. The output, as I said, is called the trunk, is down here. You cross this and you find your continuous operator. So it's pretty simple in the implementation. The problem is that a single layer will lead to an exponent to the Kirchhoff dimensionality at the input. So you will not be able actually to train the operator. And indeed, at that time, Chen and Chen did not have any examples in their paper. What we did is to derive the same theorem, but for deep neural networks. So we know deep neural networks are more expressive. They could beat the Kirchhoff dimensionality if you have the right composition. And indeed, we replace these terms here with, these are now neural networks. And you can prove this by relatively simple. We have this in the paper in Nature Machine Intelligence, that we published in the appendix. We have the proof for those of you who are interested. But now we can use deep neural networks to replace the single layer. This could be more expressive. And we can also derive some error estimates. For general operators, it turns out that at least we couldn't derive, we derived part of the error estimate, but one part was diverging. If we restrict ourselves to advection diffusion reaction equations, linear equations, we come up with the estimates which look like this. This here, the 1 over p, is associated with the output. This is associated with the input, and you can see terms which relate to the branch. S here is a negative exponent, and also the trunk, that's a very small error. So basically, these are error projection errors, encoding errors, reconstruction errors, and so on. Also, we have obtained results for the Berger's equation, but of course, the Berger's equation with the Hopf transformation have a rational approximation. And for rational approximation, we know that there's a very good deep neural networks can do a good job on for rational approximations. So let me give you in a nutshell what we actually try to do here. Again, how we train this. This is supervised learning. We take the input functions, many of them, and we record the output, G of u. Then upon training, you ask the question, if I give you a new excitation inside the distribution for interpolation or outside the distribution, can you get the correct answer? I have marked the same thing here down to the right. What you see here is on purpose, I have lots of points for the input, but then for the output, we're trying to have as few points as possible because that's where the expenses, that's where the experiments are, that's where the ab initio expensive simulations are. So you want to minimize that as much as possible. It turns out that that's the answer using these deep neural networks that I talked about. A simple case to illustrate my point is shown here. So basically, we want to do integration. We want to teach DeepONet how to integrate. So we take the integrands, we take 10,000 integrands, and we train it by using S of x naught at a specific point x naught. Now, x is in an interval from 0 to 1 here, or it could be from 0 to infinity, let's say, if you do Laplace transform. We have done that for Laplace transforms as well. So DeepONet can learn Laplace transforms, can learn Fourier transforms, and so on. But the point I want to say is that at the output, we only take 1 point. So we only need one integral evaluation, for example, in order to train this. Of course, we need to repeat that 10,000 times. So upon training, you plot the mean square error versus number of iterations. You can see here the error is very small. In particular, I'm interested in the generalization error, the difference between the training error and testing error. And if you can look at different architectures from ResNet to sequence, CNN, and so on, it turns out that this unstacked architecture that I show you has the smallest generalization error. It's all about generalization error. You can have other architectures that you can train. Okay, so there has been a lot of press about this DeepONet and other operator regression. In fact, in this Quanta magazine, in addition to DeepONet, there was an article about other work from Caltech on the Fourier. And I think later today you may hear about it from one of the authors. That network is called FNO. It's based on Fourier approximations and some nonlinear activation functions. I like the idea, but when that FNO first came out, MIT Technology Review, there was an extent article about it. This came out after our paper, and I think they overstated their case because they saw that it's the fastest and the best, and they even could solve turbulence for any type of fluid. Now, anyway, we're writing a paper to make a fair comparison of DeepONet versus FNO for fair data, as they call them. And I want to show you a very simple example that we took. Can we learn for different initial conditions which look like this? It's a classical problem we use in aerodynamics, where you have, you have Gibbs phenomena, you're trying to avoid them. Then you have C0 continuity, L2 discontinuous solutions, and so on. Can you advect different waveforms like that with a very high accuracy, it turns out that FNO gives you an error of about 50%, as opposed to DeepONet without doing anything, we have 0.3%. If we apply the same thing to a hyperbolic boundary layer, which I will show you later, the stability of it using PSC parabolized, we get an error about 9% with DeepONet, and we get 22% with FNO. Some other problems, like the where the Fourier transforms are appropriate, like the earthquake, if you have an earthquake signal, you can see the results are comparable, and so on. But even for simple advection problems, as I said, FNO, which as I said, I like the idea a lot, but it's very limited in terms of regularity and geometry and so on. But operator regression, I think, is here to stay, and I will continue with this. Let me go back to DeepONet and show an example of fractional differential operators, which are difficult to compute, but you can do this offline. You want to compute, let's say, the Caputo derivative here. You take known functions, you compute analytically or otherwise their outputs, and therefore you can train this DeepONet to, just like before, as you can see here, to learn how to do differentiation with fractional derivatives. Fractional derivatives are not trivial, for those of you who don't know it. Here we have to take not just the function itself, but also different fractional orders. Let's say alpha could be a continuous variable from 0 to 1. The reason I show you this is because I want to make a comment about the input space V. So far, and I didn't talk about it, how I define the input space V was a GRF, a Gauss random field, which actually violates the compactness assumption of the theorem, but that doesn't matter. It turns out it works. But what I want to show you is that if you choose a different space to represent the inputs, now that space could be actually a neural network, could be wavelets, could be Fourier, could be what I have here, polyfractonomials. You can actually get an order of magnitude better accuracy for the same number of data, same number of iterations. So the key to operator regression is how you represent the space V, how this reaches the space. And I want to finish my talk with two real examples. One will come from mechanics, the other one from hypersonics, which are real and hot topics these days. So dynamic fracture is, of course, a very difficult topic, but finally, with methods like these phase field methods, which are somewhat smoothing methods, and Cahn-Hilliard equations, we're able to produce data. Of course, it's expensive proposition, so you cannot really do fast computations using this. But we wanted to see if a DeepONet could learn to do crack propagation. You initiate a crack somewhere. Can you train it to propagate the crack further, not just from the inside the distribution, but actually for cracks that has not seen before, the length and so on, outside the distribution. So it turns out, and that's why I show you this here, is the supervised learning doesn't work very well. I'll show you results later. So what we did is we took the variational form of these phase field equations, and we put it into the deep neural networks. For example, here you can see this is what we put in the, so it's a sort of combining the variational form of pins with neural networks during DeepONet during the training period only. But as you can see here in the loss function, I actually have the physics weighted plus the data. In other words, I also need to have some real data from the simulations or from some video together. So it's a hybrid training that I do, and I do that using the variational form of the PDEs that I have. Then, of course, in testing, I abandon that because I don't want to do any further optimization without any optimization in any more training I want to forecast. So I'll show you some results here. And this is actually for out the distribution. So I take different cracks, different lengths here. Not a lot, it turns out. And as I increase the number of samples, only 80 different snapshots, I can reduce the error of propagating these cracks in less than 4%. So this is pretty accurate, actually, for this type of problems. I also want to show you what happens if you, if what I call now the variational DeepONet versus variational physics informed DeepONet versus the data-driven DeepONet. Data-driven works fine, except for these problems where you have these discontinuities and these dynamic fractures. You can see this is the case if we just use data. This is a case where we use the variational form of the equations. And if you look, so basically we're looking at a crack right here. And you can see the blue is the truth solution, the red, which is not very accurate. There's still some error, of course, with the variational, because this is the extrapolation, so you expect some errors of the order of 5%. And I want to finish very quickly with, let me see the time. Yeah, with this example. This is a flow in hypersonics. If you don't know what that is, you're not supposed to know, is basically a system of conservation laws that have very complicated chemistry. For example, for Mach number 5 and above, the air, this is air, will dissociate behind the shock into different species. So you have to keep track of the species. The problem is, even for standard solvers, Eno and so on, discontinuous Galerkin, you lose monotonicity. So you have to be very careful how you do that. And you have to deal with shocks and basically it's a problem of multi-physics and multi-scale. The chemistry is very fast and the mechanics, the velocity and the temperature very slow. So it could be like 5-6 orders of magnitude. That's why the CFD solvers have difficulty in simulating this, even in 1D. Here we use some data from my colleague's code and his students, Qinwan Xu, to produce data. So what you see here, we have different Riemann problems. We set up different Riemann problems. And then we use WINO to compute solutions for 3 species. You can see the chemistry. There are 3 species right here. Okay, so we take this, we call them trajectories. We compute 1,000 trajectories from their code, but we only use 100 trajectories for training and 50 trajectories for testing. What we did here, we could have used one DeepONet for everything, but for each one of the species, we created a DeepONet. We trained a DeepONet offline, and then we put them together using some new data, let's say 2 or 3 data for new conditions on velocity and temperature. Okay, again, what drives this is a Riemann problem, which is basically a state like that and a state like this, let's say in the pressure, and we can change the smoothness of the initial profiles, the initial conditions. That will give you different answers. Okay, so here's one example where we can predict with pretty good accuracy. So we basically map the initial condition to a specific time, and we do that in 0.01 second. You can see here the generalization error is very small because the training and the testing errors are small. I mean, very close to each other. But you can see if we follow here, let's say this one, the density of oxygen. The black is the initial condition, which will correspond to the pressure. You can see it's very close to the pressure. The initial velocity is 0, turns out, but of course, you pick up big velocities because it's Mach number 4, I think, or 5. And you can see we match the WINO solution very nicely. A more complicated case is a realistic case. And the realistic case is the wing of an airplane, of a hypersonic airplane, will have these sensors. So basically you have flow in this way, and you have these sensors. And these sensors record in real time, record these signals. You can see actually there's a transition here because this is a laminar signal up to here, and then you pick up this turbulent signal. So somewhere here, there is a transition. So you have this discrete number of pressure sensors. That's all you have as data. Now, we can train, like I just told you, offline with synthetic data or real data. We can train the neural network, the DeepONet, in fact, the inverse DeepONet. So the inverse DeepONet will take this as an input, the downstream disturbances, and will discover the inflow, which is the unknown inflow free stream disturbances. Okay, having now the free stream disturbances, we can set up the forward problem in a forward DPoNet, and therefore we can now compute the three-dimensional field, two-dimensional, three-dimensional field like that in the forward problem that therefore predict the flow over this wing. So this is in a nutshell what we're doing for DARPA, a project that we have. But the idea of this project is you build multi-physics and multi-scale problems from modules of DPoNet that are pre-trained, and then in real time, just you kind of simulate a few measurements, 2, 3, 4 measurements, like 8 measurements here for the pressure transducers to predict full 3D fields. Talking about performance metrics and how fast you do. I didn't show you this example of electroconvection, but in this case, we have like 6 fields, the number of scales, like 3 orders of magnitude scales, accuracy 10 to the minus 3. And there was a 10,000 speed up, that's published work. All this is published actually in the archive. The hypersonic case I show you, it involves 7 different fields, it turns out, 8 orders of magnitude in multi-scale, and the speed up factor is 100,000 compared to CFD. This is what, of course, that generated the data. Of course, there's a huge cost in the pre-processing, but that is offline. That is done offline, just like we do with the reduced order models. And then for the case of high-speed boundary layers that I show you at the end, there was a speed up of 40,000 compared to spectral solvers. A couple of thoughts to finish here. Operator regression requires a lot of theory to, and the group of Sid Misra again from ETH developed some really great work on solid foundations of DPoNets. One of the main conclusions of their work is that DPoNets with the deep expressive networks as components can break the curse of dimensionality for very general nonlinear operators, which means that basically, and we have observed in the experiments in our paper, we observe exponential convergence. And they verify that, but also they could see that they can break the curse of dimensionality at the input, as I said. They can also work with non-continuous operators, discontinuous operators, and also the assumption of compactness is not needed. They also produce error estimates, the encoding and reconstruction error, or basically the total error. There's 3 errors there that they have bounds for, and they demonstrate that for certain equations, given some mild conditions of smoothness, this curse of dimensionality proof is correct. Another surprising result is that how you actually sample the input. Let's say if you're in a physical experiment and you do measurements, a random sampling is almost optimum, and some other results there. I also want to leave you with this thought from DeepMinds. Irina Higgins wrote a 2-page paper in Nature Machine Intelligence to talk about our DPoNet, and says DPoNet is still a first step towards building truly powerful and scalable universal operator approximations, but it opens up exciting opportunities like modeling dynamics of complex systems. She's also talking about training the neural network both from simulation data, synthetic data, and experimental data. And now it becomes clear that this is the need. How would you train all this? We don't have big data. So actually, it's very important that you train this, as fast as possible, especially at the operator level. And anyway, this is our sponsors. In addition to DARPA, we have support from the Department of Energy and also from a recent NURI from the Air Force. And I'm pretty much done here. Thank you very much for your attention.
Yeah, thank you, George. It's a very inspiring talk. So now we open the floor for questions. So Junqiao, yeah, sure, go ahead.
Hey, hello, George.
Hi, Junqiao.
Wow, as usual, very extremely impressive talk. Thank you. I just have a question about all this wonderful example you gave, how much when you how much how different is this test data is from the training data? How different they are when they
yeah. So the crack problem I show you, which I think you know about cracks and so on from mechanics. That's actually we train it with the 3% error. We train it with 85 different cases, which is not a lot, and that corresponds to different lengths of the crack, initial crack. Okay, you can also have different loading, but let's say the same loading. Now, the case I show you was for a different length, not from that distribution. Let's say that you have a length from, let's say, 0.1 to 0.3 in some units, right? The length that I show you the test was extrapolation. That's why we call it the power of extrapolation. It was not between 0.1 and 0.3. It was actually outside the distribution. It was 0.5. So it was totally different extrapolation. Now, on the hypersonic problem, the last problem, we did a Mach number 8 to 10, and that's the training. Now, the program manager from DARPA told us, look, that's fine, and of course you can interpolate, but how about extrapolate? Because you know the Russians are chasing us, and the Mach number is 13. We have to go at Mach number 13. 8 to 10 and doing the Mach number 13 is of course way out of the distribution. Now in that case, the error is 20%. If you don't do anything, no new data, you have 20% error for the pre-train because the chemistry changes. The mechanics doesn't change too much, but actually at these high Mach numbers, the chemistry induces huge changes, which basically change the viscosity because you have all these parameters depend greatly on the composition of the medium. And in that case, you need new data. So what the data we used was like about 5 new velocity measurements and maybe let's say 5 temperature measurements. But these are the mechanical scales, not the temperature. You have no data for the temperature. So with this, you are able to reduce the error to a couple of percentage, going from 20% down to 2% by specifying the conditions, because the chemistry is tied to it, and of course has been in pre-trained. So extrapolation is always tricky. There's no way you can find bounds and so on, theoretical, but empirical evidence shows that if you enrich the space V a lot, in other words, if I double the number of snapshots I have to train my input space, I do a much better job, not just interpolation, but actually extrapolation. So the key is to enrich that space, the input space, and then the extrapolation will be much better. But obviously I don't have any proof of that. I just have empirical evidence.
So the first example of crack propagation, you just learn this lens is just like a one dimension. Is underlying is a one-dimensional problem. All the other things are the training data will be the same except the length, right?
No. Well, the length is one-dimensional, but you can also change the loading on the side, of course, or the shearing. But the problem is very multi-dimensional, right? Because the crack propagates. You saw it goes into the side because.
It's a multi-dimension, but in principle, it's a low dimension. Otherwise, mathematically, I find it's very difficult to visualize how, I see. So the L4, this second problem, you train for certain different kind of Mach number, then you do this test data is for different Mach number. I'm sorry.
Different Mach number. Yeah, that's why I said Mach number from 8 to 10. Then we look at Mach number 13.
I see.
Way outside the side of the
what do you call it extrapolation? Because
it's outside the distribution, outside outside the input space V, totally outside. We're not supposed to. Yeah, I mean, there's no guarantee. You're not supposed to actually get anything there.
So there's other method like for this low dimensional, not necessarily. It's multi-dimensional, but not terribly high dimension. Is this a POD or this is No,
POD is not. Look, the modern era. You should know that the modern era of modeling is not to go under-determined, but over-determined, over-parameterized. What the difference between this and reduced order modeling is that DeepONet, it sort of does what this is a surrogate model, but DeepONet is a hugely over-parameterized network. And we know now from Poggio's work, other work, that yesterday you had a talk by Jason Lee, who talked about over-parameterized networks. Over-parameterized network generalize well. Under-parameterized networks, severely under-parameterized networks like POD is very local. There's no way. I wrote a paper in 1991 with Orzak to show, and Yannis Kevrekidis to show that POD cannot extrapolate. 1991, cannot extrapolate. It's a local model because we know now it's but over-parameterized network. So if you ask me why I got lucky in extrapolation, is because this is an over-parameterized network.
Great, thank you very much. Thank you, George.
Sure.
Okay, so Eric, you have some questions?
Yeah, actually, my question changed over the course of that exchange.
Okay.
So it was good timing. So you're doing all these chaotic systems, and in that case, you have a energy cascade that kind of goes down the spatial scales. Do you have a sense, like, have you looked at any problems where you might have emergent structure, like in a turbulent plasma model, you might actually have structure that emerges as a result of the simulation, or the evolution, the physics? Have you looked at that kind of problem yet with these?
Eric, are you asking about pins or depot nets?
Probably depot nets, but maybe pins. Yeah,
pins would do that. Pins would do that. You should know that from Nat also. That if pins are, because they have the equation, so if you actually resolve it and you have the right parameters and stable network, pins will resolve the bifurcations. Depot nets will not do that if they have not seen it. But if you have sufficient new data, that's why this last example, as I said, when you go to a different Mach number, that's the case where you have a different chemistry, not necessarily a bifurcation. You need new data. Without new data, the error could be 100%. So you're right. There's no way from just supervised learning, and even with DeepNet, even with any over-parameterization that you do, there's no way you can capture this type of bifurcations because these are new states. So you need new data. If you have new data, it is possible to get to that state if you are not very far from that state. But there's no way to do theory on this type of things.
Sure. Yeah. I guess one other maybe technical question. When you talked about because I just don't know, when you talk about the variational pins, and I guess you're computing this integral and minimizing it in some way. Are you just using like a Monte Carlo style integral for that, or are you actually discretizing space?
Discretizing space, but Monte Carlo, like SimNet, it does. NVIDIA SimNet could be used here at the expense of accuracy. But we use a quadrature, yeah.
Okay, thank you.
Thank you. Any other questions? Yeah, we have 2 minutes. So George, for the quadrature integration, continue Eric's question, for high dimensional problem, the quadrature will become more expensive, right? The curse of dimensionality will kick in.
Yeah.
Right?
So I have a student who trained a depot net to do high dimensional integration.
Mm-hmm. Yeah.
But Nat Trask just told me that he has a way of doing it, with almost zero quadrature. But actually, depot net can learn to do three-dimensional integration. So we have a depot net that can do three-dimensional integration.
Okay, yeah, that's cool. Mm-hmm.
You maybe
Sure.
When you have maybe 2 or 3 dimensional spatial dimension, but then you have other parameters, many other dimensions. You want to do the expectation together is a high dimensional problem anyway. Maybe you just might as well just do
Monte Carlo. Yeah,
Monte Carlo for space as well, because collectively is high.
Yeah. But let's say in 3D, let's say we have the crack problem in 3D, right? That will get expensive if you have the variational form, for example, because you compute these inner products all the time. So you can do that just like I show you. I can do the fractional operator I can do that. So DeepONet can do explicit operators and PDEs, not like some other methods that I mentioned. They can just do PDEs because they're done for that. But DeepONet is very general. It can do any operator. It doesn't have to be a mathematical operator. It could be any map, nonlinear map from one function to another function. It could be a black box. So you can trick it or train it to learn that map, the nonlinear map.
Well, in chain theory, they do assume the operator is compact, and you need.
You don't need that in practice, Jin-Chao. As I said, all the examples I have, we have 16 examples in the paper in Nature. None of them uses a compact.
Compactness is at least theoretically is necessary because you have to have a low. Compact is pretty much a low dimensional. Otherwise. Compact things can be operated approximately low dimensional subspace more easily. Anyway, mathematically it seems to be necessary, but you are
No, you can see in the theory of Mishra, he removes that because he works with measures and he has some assumptions, so he can actually remove that.
But implicitly, something like that has to. Anyway, it's good. Thank you. But I just want to think some more.
Yeah, take a look at the paper of Mishra.
I have read those papers. Not in depth, but yes.
This is 120 pages now.
Yeah, I know. And okay. You're as a co-author.
Yeah.
I didn't do anything. They just.
Yeah, George. Thank you very much for the nice talk. Yeah. Okay.
Thanks,
I'll talk to you later. Bye.
Yeah.
Okay, so let me share the screen. Okay, so Jita, she cannot make it, so I fill her slot. So I'm gonna give a talk today. So today I'm gonna talk about a topic on accelerating convergence. So let me see whether this is okay, let me see, go to the first page. Okay. Today I'm going to talk about scalable algorithm for Bayesian deep learning, why stochastic gradient, Monte Carlo, and beyond. So this is a joint work with my student Wei Deng. So he's right now on the market. So he basically carried out most of the work I present today. So if you are hiring, I would highly recommend you considering him. And the second author is Yating Wang. She's my previous postdoc. Currently, she's assistant professor at University of Hong Kong. And Qifeng and Liao was previous Purdue students. And Georges is my previous postdoc, and also my long-term collaborator, Faming Liang here. So this is a collaborative work. So we published a series of papers on the NIPS 19, 20, and the ICML 20, SAR 21, and a series of GCP papers. So let's first go to the first part. First part, I'm going to talk about the Bayesian sparse learning with preconditional stochastic gradient Markov-Chinn Monte Carlo. So if you are interested, you can find it in our NIPS 19 paper in the GCP at 2020. So first I will give some brief introduction, then I will introduce a new class of adaptive stochastic gradient Markov-Chinn Monte Carlo. And following, I will talk about predictive SGLD and the hierarchical Bayesian models. So first, I want to talk about the motivation. The motivation is try to be able to do the async quantification for the deep neural network. The challenge facing the deep neural network is first is the overparameterized deep neural network require heavy memory and the computational power, and it may cause overfitting, right? Also, the cost function is difficult to optimize, and a good local minimum is hard to obtain. Okay, so this is the challenge part for the neural network. So the object of this work is to do sparse learning to enhance the efficiency and the robustness and the interpretability. And because we will have a very compact neural network, so that it provides you the robustness, efficiency, and also you can look at the ways to be able to do some interpretation. And in addition, the Bayesian approach is able to capture the uncertainties, so you can evaluate like the confidence interval of your predictions from this Bayesian approach. it can compute the posterior expectation to obtain more robust results. Finally, it can escape this shallow local optimus and settle point to achieve better point estimate. Okay, so here's some notations. So in this talk, I will using the capital D as represent the entire data set. I will using the B as a mini batch of data. And I'm using beta to represent the model parameters, and using the L represent the log posterior densities. Okay. So the true gradient we right here is a gradient L. So we can carry out this true gradient. However, in reality, we have to using stochastic gradient to approximate using a mini batch. So that's why we're using the notation of gradient L tilde here. So you can see the compare the difference. Okay. So this is on the using mini batch, we have batch size small n instead of the capital N. So that's why we use the L tilde here to represent the stochastic gradient here. So the key components of our Bayesian sparse learning is following. So the first part is we try to do sparse learning so that we can enhance efficiency, robustness, and interpretability. And the Bayesian to capture uncertainty, we employ the empirical Bayesian method to learn a class of hyperbayesian models, so yield a data-driven adaptive penalties. And to do the training, we're using the adaptive stochastic gradient longitudinal dynamic, or we call it SGMCMC, to capture parameter uncertainty and avoid overfitting, and also escaping the shallow local optimal and settle point, and the compute posterior expectations. Further, we developed this so-called preconditional SGLD to update parameter with different step size and adapt to local geometric, and resulting in a faster convergence for components of beta have different scales. It's very suitable for solving a heterogeneous media multi-scale problems. And later, we also included this stochastic approximation approach to optimize latent variables in prior, so to convergence to the asymptotic correct distributions with controllable bias. Finally, we developed the pooling strategy to enable a sparse deep neural network. Sparsity is ensured, resulting in less usage in memory and computation power. So this is SGD, so we're not going, so everybody knows. So we need to find the map for model parameters through the stochastic optimization. But the drawback is it do not capture parameter uncertainty, and it can potentially overfit data. So that's why motive is to develop this variation of different kind of form of a longitudinal dynamic. So a longitudinal diffusion with a stationary distribution can be described by the SDE, this d beta equal to the gradient L dt plus square root of dw. The dw, the w term is a Brownian motion term. So we can using the Euler discretization of this equation 1 approximate the true gradient by the stochastic gradient we represent by the equation 2. You can see we replace by a Gaussian distribution here. And the equation 2 asymptotically convergent to a distribution that proportional to e to the tau times the L. The tau is represented as 1 over the temperature. So tau is increasing. So this epsilon k decreases. The solution tends to the global optimum with a higher probability. So the advantage of using this stochastic gradient longitudinal dynamic is it can sample the neural network posterior to model uncertainty, and also compute the posterior expectation to obtain more robust results, and also escape local optimus to achieve better point estimate. The SGLD update all parameters with the same step size. This may cause slow mixing when components of beta have different scales. That motivates to develop this so-called preconditional SGLD. So also we optimize the prior with stochastic approximations to improve the efficiency. So there's several approaches we developed. If we want to improve the efficiency of sparse sampling, we can infer prior from empirical data, and then learn prior through optimization instead of sampling, and ignore uncertainty of prior to speed up inference. So we optimize prior by the stochastic approximation approach. Basically, we optimize latent variables without affecting the convergence to the asymptotic correct distributions. So the basic idea of stochastic approximation is the following. So we intend to solving the root of the integral equation, the equation 3. Here, this h is a bias estimator to the mean field function h theta, where k is finite but asymptotic unbiased as k goes to infinity. So this stochastic approximation algorithm has 2 steps, and it's also an iterative recursive algorithm. The first step is we sample the beta k. The beta is the hyperparameters in the neural network. So basically, we sample the beta from the transient kernel, which admits the f theta as the invariant distributions. Then we update the parameter inside the prior theta k plus 1, okay, using this the biased estimator of the mean field function. So that's the 2-step approach here. We develop a class of adaptive stochastic gradient MCMC methods. So first we develop the first order stochastic gradient MCMC. Okay, it's basically a sampling algorithm which asymptotically converges to a stationary distribution. So, and also for the adaptive SGLD, we introduce the auxiliary variable theta and formulate an inhomogeneous Markov chain. So you can see we add this theta here, okay, so that it can do some adaptivity here. Where this eta is basically satisfy a normal distribution, okay. So the eta here is the learning rate. The h is biased by asymptotic and biased estimators, okay, of the mean field h. Okay, so that's we do this SG MCMC, and then I will talk about the pooling strategy to enable the sparse deep neural network. So what we did here is we apply the magnitude-based weight pooling to our compression experiments. So the weight pooling, basically, we set up a threshold. So if the weight over some threshold, we keep it. If below, we throw them away. So the weight pooling can also be viewed as a greedy L0 regularization in the optimization. So by doing this, we can obtain a sparse neural network. So the following, I'm going to talk about the predictional SGLD. I've told you the motivation to do this is because we want to update the parameters with different step size and adapt to local geometric, and resulting in faster convergence for components of beta have different scales. That's the motivation we want to do here. So it's the theoretical background of predictional SGLD is come from the Langevin dynamic in Riemann manifold. So consider the family of the probe distribution lying on Riemann manifold, for which the expected Fisher information matrix defines a natural Riemann matrix tensor. So here, if you look at the SDE define the Langevin diffusion on a manifold, the G is the manifold metric tensor. And if we take the gradient of G, we get a tau. So, and then we add a tau into here. So you can say this is the difference compared to the traditional Langevin diffusion. It has an actual tau term, and they have this the G term here. So then we can do the Euler discretization of the equation 6 using stochastic gradients. So we can discretize the equation 7 here. So in fact, adding positive definite matrix G inverse define a valid Riemann manifold. So we are not restricted to using the G inverse beta equal to I beta. We can choosing a different kind of G inverse to do, as a preconditioner. So here is the iterative steps. So first we define the G as a diagonal of 1 over lambda I plus square root of V, and the V is iterative. So at a V beta k equal to alpha V beta k minus 1 plus 1 minus alpha G beta k dot G beta k here. So you can say the G is basically the gradient of the, there. Okay, so we develop a hierarchical Bayesian formulation for sparse inference to encourage the sparsity. So we're using the Spark and the SLAP Gaussian Laplace prior so that we can gain this sparse posterior. So here I basically showing you the preconditional SGLD with the stochastic approximation pseudo code here. So within the loop, first we obtain this G beta k approximated by the gradient of Q. Then we updated this V by using this iterative step, omega k times the v plus 1 minus omega times g dot g. Then we updated the capital G beta, okay, equal to this inverse of the diagonal matrix. Then we updated the beta. Then we do the pruning. Okay, if you define the pruning, the bottom as percent weights with a lowest magnitude, then we can greatly reduce, okay, the very small weights, then get a sparse matrix. Okay, then we do the loop. Okay, so that's the basic steps of the preclinical SGLD. The following, I'm going to show you some results. So consider a data set. We do a simple regression problem that's a y equal to x beta plus eta. So we have the n equal to 100. So and the p equal to 1,000. Okay. So this is a large p small n regression problem. So we have three parameters. One is basically the beta, right? So we want to estimate beta, eta, right? So we want to estimate and the sigma here. So you can see, so in the bottom, so basically look at this black is the true value, and this blue one is our method. So you can say our method can obtain the true, very close to the true posterior distributions, and the other, like for example, the SGLD are way over, compared to the true posteriors for these three different parameters. So our method all be able to capture the posterior distribution well. And also, if you look at the spread of the data, right? So you can see the black is the true value. So our method can very close to the black dot, the blue dot very close to black dots. Okay, but the other, for example, the red one is spread out, cannot capture it accurately. So let's look at what the advantage of this method in the network compression. So if you look at our proposed method, so on the top, if you look at the table, so we use on ResNet 20 compression on the CIFAR10 dataset. So if on the first, on the table, if you look at the first row, it's S represent the compression rate. So on the right, if you look at the 90% compression rate, that means we throw away 90% of the weights, only keep 10% of the weights. So that makes it the network very compressed. And however, if you look at the accuracy, we still can preserve 91.68 accuracy. So for CIFAR10, we can achieve the state-of-the-art accuracy. We can using only 27K parameters with 90% sparsity. We can achieve 91.68% accuracy. If you compare all the literatures, for example, 2018, the people using dropout, they can achieve 91.48% accuracy, but however, they need to double the number of parameters to achieve the same accuracy. Okay, so this already state-of-the-art. So you can see our method can achieve a much better network compression and preserve the accuracy. Okay, let's look at the small n large p problems using the preconditional SGLD. So if you're using the red one represent the preconditional SGLD, you can see we achieve a better than other two benchmark. Okay, so if you look at the black one is true, our method can overlap with the true posterior distribution very well for the beta 1 and beta 2. Okay. So we're testing the MSE arrows. Okay, so if you look at the MSE arrows for during the iterations, so you can see the black line is our preconditioner approach. It can converge much faster than without the preconditioner. This yellow line is without the precondition. So we can achieve much faster convergence here. Okay, and I want to show you some more difficult problems, such as the multi-scale flow equations. So let's look at a multi-scale flow problem. So this the kappa inverse times u plus gradient p, okay, equal to 0, then we have divergence equal to f. So then we want to basically, traditionally people using on a fine grid using the mixed finite element approach, then also using the velocity approximation, normally people using RT0, okay, for the pressure, people using P0 finite element to solve it. And the difficulty is that the AH is large and it depends on the kappa. So we want to using the neural network to learn the structure of the kappa and obtain the multi-scale basis. So this is the basic idea. So we want to develop a so-called multi-scale model reduction. So we want to mimic the standard multi-scale finite element approach in the restriction and prolongation approaches. So the difficulty using traditional approach is the multi-scale velocity basis usually needs to be recomputed when the kappa changes. Our goal is design a sparse learning algorithm to achieve efficiency and maintain accuracy here. Okay, so basically is you give me a kappa. So if I have a neural network, I can predict the solution of U. Or if you give me a right-hand side F, I go through my neural network, I can predict the solution of U. So here is our convolution multi-scale setting of this problem. So you give me a kappa, so I will go through this upscaling, go through the convolution, pooling, flattening, then dense reshaping, and then we go through the convolution flattening, then we can downscaling again, right, to predict the solution. So that's the architecture of this one. So we want to learn the feature through these convolution steps, and using that to do this model reduction. So here I want to show you some numerical results using this approach. So in the dense neural network, we need over 6 million number of parameters to carry out this prediction. However, if we using this 70% sparse rate, we only need a 758K of parameters. That's almost like only 10% of the parameters we keep for the neural network. However, if you look at the accuracy, so this is the E1, E2 are basically the MSE, E2, this is the K-norm. So you can look at the basically using these two different norms, you can see even with a 70% reduction, we still can keep very similar accuracy. Okay, so but we only using 10% of the neuron. Okay, also let me show you some the learning curve with different convolutional representations. For 128, is the problem has higher dimensions, basically 128 dimensions. If you can take a look at the problem, so you can see our predictive approach can achieve much consistent and faster convergence. And if we look at this with true versus prediction, so on the left column is the true prediction of the velocity field. On the right is without the preconditioner. The middle one is with precondition. So you can see, apply the precondition can capture the structure very well. However, without this preconditioning, it has a lot of noise. Okay. So this is the convolutional representation of 32. This is 64. You can see they have a more fine scale structure, but we still using preconditioning approach, we still can capture it pretty well. If we increase in the dimension to like the 128, you can see it has a lot of finer structures. Our approach still able to capture, the fine structures. But however, if you look at the without application, it's totally blurred. Okay, so here's a summary of the first part is we propose a class of adaptive stochastic gradient MCMC approach with wider applications and prove the convergence. And also it can be applied to the empirical Bayesian method to learn a class of high-grade Bayesian models and the yield-driven adaptive penalty. And also we propose an adaptive Bayesian sparse deep learning algorithm for regression problem. And also we optimize the prior through the stochastic approximation. And we sample with a preconditional SGLD, which can adapt to the local geometric and results faster convergence. Okay, and the convergence to the symptotic correct distribution with a controllable bias we introduced by the stochastic approximation. And here's some reference I will go through quickly. The second part of my talk is about accelerating convergence of stochastic gradient MCMC while replicas change and beyond. So this work is also carried out mainly by my student Wei Deng. So let's look at what we do here. So first I will just go quickly about some background. And because asynchronous quantification is crucial for AI safety problems and reinforced learning, so which draws our attention to using MCMC, which is known for multimodal sampling and the non-confined self-optimization. However, MCMC has some drawback limitation. We want to speed up. That motivates to develop this series of methods here. The multimodal sampling can accurately predict the confidence intervals, and also it can achieve better point estimate. And we approach this problem using a Langevin diffusion. So a famous sampling algorithm is called the Langevin diffusion. So the d beta t is equal to minus gradient u dt plus the square tau dwt. Okay, the beta t is the parameter time t, and u is the energy function, and wt is the Brownian motion, and the tau is the temperature. So as t goes to infinity, the beta t converges to the stationary Gibbs distributions. And here the tau represent, like you can see, so if we increasing, okay, the tau, the distribution will become flatter and flatter. Okay, so that's so they can see the difference here. So we can control the tau to achieve different purpose of speed up. However, evaluated gradient is a big problem, and it's very computationally expensive. To tackle this issue, so Max Wellin proposed the stochastic gradient Langevin dynamic. So it's basically introducing the beta k plus 1 equal to beta k minus the eta at its linear rate. The gradient u tilde, tilde means the batch size approximation plus a normal distribution. As t goes to infinity and eta goes to 0, the beta converges weakly to the stationary Gibbs distributions. And let's look at this movie and show you a multimodal distribution using stochastic gradient Langevin dynamics. So let's see whether I can play it. Let me see. Yeah, seems I cannot play. Yeah. Let me see. It seems I cannot play. Anyway, so I can move. Okay, I know what I do. I need to. Okay, I think now I should be able to play it. Okay. Let me see. Let me do Control L. Okay, so now you can play. I don't know. Okay, so you can see we started this SGLD. We have a lot of local minimum here. You can see it. The blue points can jump from one local trap to another local trap, right? But very slowly. You can see it has the capability of jumping out of the local trap, but in the middle is the global minimum, right? But however, it has to do a lot of sampling to be able to find out the global local minimum. It takes a lot of time to get a converge. Eventually, it's gonna converge, but takes a lot of time. So that's the showing you what happens if you're using SGLD. So that's motivated to develop some strategy to accelerate MCMC. The several different approaches. The first one is simulated annealing in '83, and the second one is the replica exchange MCMC by Swenson and Wang in '86. And so that's motivated to develop this replica exchange SGLD. We published at the RCML 2020. So the basic formula is we consider two Langevin diffusion process. We're using two different temperatures. So the first equation and the first equation, we have a tau1 larger than tau2. So we have these two Langevin diffusion, and we want to swamp them. Okay. So the position of the two particles swamp with a probability S. So they satisfy this distribution with the e to the 1 over tau1 minus 1 over tau2 of this two energy function difference. In other words, a jump process is included in a Markov process with a probability here. The R is the intensity rate times the swamping. So then there's this inverse of the probability is basically 1 minus this R times S. Okay. The basic idea of philosophy behind this replica exchange is try to using the high temperature to do this red line, this high temperature. So we want to using the red curve high temperature chain to explore the whole landscape. And once we find some good point to start with, then we switch to this low temperature one to do the exploitation. So this way we can take advantage of both high temperature and low temperature, because high temperature is good at exploration and low temperature chain is good at the exploitation. So we combine the both advantages so that we can find the global minimum very fast. So that's the motivation we try to use in the replica exchange. So that's basically this figure show the trajectory plots of for Replicate exchange of Langevin dynamic. So why the naive numerical algorithm fails, right? So here, basically, if people just naively using the traditional Replicate exchange approach for this stochastic gradient Langevin dynamic, they will fail. So let's look at why. Because if we using this, consider using a stochastic gradient Langevin dynamic with two temperature, tau 1 and tau 2, if we swamp the chain with a naive swamping rate, the R times S with beta theta, and yeah, so then the explanation the unbiased estimate L theta will lead to a large bias is because we're using a small batch size. Okay, that will lead to that's a large bias. To solve this problem, so we have to do some correction terms. So if we look at this L theta, satisfy a normal distribution, and consider this geometric Brownian motion in each swamp as a martingale, so we can represent this S theta as an exponential term included this geometric Brownian motion term here. So take the derivative of the S theta, so we can represent the ds theta equal to the square root of 2 times 1 of tau 1, this two temperatures of for this two chain, 1 over tau 1 minus 1 over tau 2, okay, times delta S theta. Then by fixing t equal to 1, we have the suggested unbiased swamping rate. That is, we need to add this orange term so that to do the correction. Okay, so that's the we want to add this correction term. So let's look at some movie to show you the Replicate exchange stochastic gradient versus the right is the Replicate exchange, the left is traditional SVD gradient. So let me show you that. Okay, so let me first show you this Replicate exchange. Okay, so let's see whether it can play. So you can see the right one can go to the middle very quickly. You can see it's swamping much faster than the traditional SGLD approach. It can explore the landscape very fast. It can go over to the middle because the middle is where we have the global minimum there. Okay, so you can say without the knowledge, right, of where the global is, it can explore the whole landscape very fast. Okay, so that's our using this proposed Replicate exchange approach. It can show much faster convergence. Here, I want to present some convergence analysis of the Replicate exchange SGLD tracks the Replicate exchange Langevin diffusion. Okay, first, this lemma is to present you the discretization error. So given the smoothness and the dissipative assumption in the appendix of the paper, and a small learning rate eta we can the expectation of the soup of the beta t, the true beta t minus the beta t approximation, okay, small batch approximation is bounded by eta is learning rate, and the maximum of the expression of phi norm square to norm square is the phi is basically the noise in the stochastic gradient, okay, plus okay a maximum of square root of expression of psi square. The psi is the noise in the stochastic swamping rate. So basically, you can say it's controlled by three things, right? The first thing is the learning rate. Second thing is the noise in the square gradient. The third rate is affected by the noise in the swamping rate. So that motivated later on, I will introduce about the variance reduction approach is we want to reduce the noise in the stochastic swamping rate. Okay, so the convergence of the Replicate exchange SGLD is controlled by three things. Okay, so here's our theorem of convergence of Replicate exchange SGLD. Let's smooth the dissipative assumption hold for the distribution mu k associated with the discrete dynamic of our parameter beta k theta. We have the following estimate for k. So the Western distance of the mu k compared to the target distribution pi is less than equal bounded by these four terms. The first term is d0 some constant, okay, it is here the representative of d0 here times exponential term. the exponential inside the exponential term, we have this delta S here. The delta S is the acceleration effect, okay, depending on the ramping rate S. Then plus the square root of the learning rate, and plus the maximum expectation of the phi I represent noise of the SGD, and plus this maximum expectation of psi I. This is the noise in the ramping rate. Okay, you can say it depends on these 4 terms here. Then I'm going to show you some numerical results. So here I basically presented the comparing the SGLD versus replex exchange SGLD here. So if you look at it, you can find out that on the top black line is SGLD, and in the bottom one is the acceleration using replex exchange. On the x is the k, the iterations, and the y is the Washington 2 distance compared to your current distribution of beta versus your target distribution pi. So you can say the replex exchange can achieve much faster convergence. Okay, so can we do better, right? So that motivated to develop some better, faster replex exchange algorithm using the variance reduction. So that motivated to develop this another work on the exponential acceleration y variance reduction. Yeah, published at ICLR 2021. So to accelerate the convergence using the variance reduction, the motivation is to obtain more effective SWAMP drivers to design more efficient energy estimators. To reduce the variance of the noise energy estimator, so we're using that is the L equal to the capital N is total number of samples, and divided by n, and small n is the batch size number of samples. Okay, little n here. So I'll have the H and equal to from 1 and 2. The 1 represents the chain 1, 2 represents the chain 2. So we obtain an I-bias estimator of L, right? So and a constant C. So we set this new estimator we can represent by a control variate. So this C is a constant, so we can optimize the C to obtain the optimum performance. So the L tilde, if we apply the control variate, so we have L tilde equal to this L plus C times this L minus the summation from I equal to 1 to n. Okay, so the second term is basically a surrogate estimation of of the beta of the energy functions. Okay, so the whole thing we can prove is still unbiased estimator. By decomposing the variance, so we do the variance decomposition. So we find out the variance of L tilde equal to this is 3 terms. Then if we want to the variance of on the left-hand side to be 0, then we can derive the constant C, right? So in such case, we can obtain this C star, right? The C star is equal to minus the covariance divided by the variance. Okay, so this is basically just standard control variable approach. So if we apply here, so we can obtain this optimum constant C. By doing that, we can achieve reduce the variance of the estimation. To make a variance reduction work, it requires 2 crucial steps. The first step is to propose a correct control variate beta hat. And we approach it by update the beta hat through every m iteration. We do a kind of a global estimation of the beta h, okay, to do the updation, to build a surrogate. And the second is we need optimum C. Okay, it's unknown, so that's why we have 2 approaches. The first approach, we can set C equal to just -1 for highly correlated energy estimator, or more advanced approaches, we set adaptive C for the less correlated cases. So here, this variance reduction replica SGLD leads to a more efficient energy estimator with a much smaller variance. So here's the lemma about the variance reduction energy estimator. So under the smooth and the distributed assumption, so the variance of the variance reduction energy estimator is upper bounded by these 2 terms. One is controlled by the m square. M is like how many steps. The step size you want to do the variance reduction. Okay, the eta here is the learning rate. The little n is your batch size. The number of samples inside each batch. And also the variance of this, the total number of n divided by the each batch number of n, then do the summation of the L energy, basically energy estimators approximation, and it's a variance. Okay, and so therefore we can have this variance reduction for large swamping rate. So basically, given a large enough batch size n, the variance reduction estimator yield a truncated swamping rate that satisfies the following. The expectation of this swamping rate is the minimum of 1 and the S of the beta 1 and beta 2 of 1 over n squared plus the exponential of minus this n squared eta or n plus 1 over n squared. So this basically tells you so like how frequent we estimate, right? So we can achieve better accuracy. Okay, so that's, I will show you some examples here. So here basically want to show you is we using do a comparison of 3 different methods. The x is the k, the y is the Washington 2 distance of the mu k, is our target, our estimated distribution of beta versus the target distribution pi. If we compare these 3 methods, so the black line is SGLD, and the blue line is the replicate change SGLD, and the red one is the variance reduction, that's the replicate change. So you can see by using this variance reduction, it can achieve further speed up, okay, and then faster convergence than the other 2 approaches. And here, let's look at some results. We're looking at the A is our parameter beta 1. If we look at the tracing plot, although this beta 1, you can see it has 2 modes, right? So the red is ground truth, and the blue is the variance reduction approach. You can see they overlap each other. So even it has a multimodal distribution. So our approach can to capture these 2 modes very accurately. And for the second one, you can see if we compare to the SGLD with our replicate exchange, right? You can see red one is a ground truth. And if we're using the SGLD, it only can capture 1 mode. And if we use replica, it can capture this both 2 modes very well. The third one we look at is different M. So if the red one is M equal to 15, okay, and so basically the blue one is M equal to 50, and the green one is M equal to 100. So you can see a smaller M resulting in smaller variance, okay. So the y coordinate is just log of the variance, okay, square, the log of variance. X is just number of iterations. So you can see smaller m means I do the variance reduction more frequently. Okay, so then that way I can reduce the variance more dramatically. So that's why we observe the smaller variance. Okay, so that's agree with what we see in our approaches. And so if you don't do anything, just the black line, okay, just replicate change, it has a larger variance here. The last one, we're basically showing you the contour of this log of the variance versus of your learning rate, of your batch size. Okay, so the x is your learning rate, y the D cell figure. Okay, so the x is learning rate in log, and the y is your batch size. So you can see the number of samples inside each batch, if you increase it, you're gonna achieve a smaller variance here, okay? And if you reduce your learning rate, you also can achieve a smaller variance, okay? So this is just showing you 2 factors gonna affect your variance, okay? And here, this plot I want to show you is the variance reduction on the noise energy estimators on the CFI 10 and CFI 100. So you can see M infinity means like we almost don't do any variance reduction, right? So so if M equal to 50, so you can see on the larger data set, right? For the smaller data set, you can see you do you apply the variance reduction, the effect, you don't see much gain unless you do in the later iterations. However, that's because this simple problem, right? All the method works. But however, if you look at more challenging problem on the CFR 100, it's higher dimension problem. And then if you look at apply this variance reduction at m equal to 50, it can dramatically reduce the variance. You can see here, okay, the second plot, B. The same thing happened to the variance reduction setup for m equal to 50, 392, okay, in the C and the D, it's similar setting. Finally, I want to show you the accuracy. So using, we have developed a different version of a variance reduction approach. So you can see compare on the CFR 10, CFR 100, on the ResNet 20, 32, ResNet 56. So we all can achieve still at the best performance compared to the other approaches. The M, it means momentum SGD, stochastic gradient, Hamiltonian, Markov chain, replica exchange, variance reduction, replica exchange, cyclic SG, Hamiltonian, Markov chain, our cyclic variance reduction, replica exchange SG, Hamiltonian, Monte Carlo. So you can see all these different approaches we have compared. So our method is still state of the art. And also I want to show you the non-convex optimization on the CFR 10 and CFR 100 on the using the adaptive coefficient. So you can see by applying this adaptive coefficient, we can achieve almost like 1.5 accelerations, okay, by using this adaptive coefficient versus non-adaptive coefficients, right? So you can see we do be able to gain some speed up by using the adaptive procedures. But however, when you epoch increases, right? So the effective of this using the adaptive coefficient will drop close to like 1.1 something, So this basically you gain a lot in the beginning. This basically I want to deliver the message. So here's a summary. So basically, we're introducing replica exchange stochastic gradient MCMC show a potential in exponential acceleration in the convergence in non-convex learning. And also the variance reduction of energy estimator yield exponential more effective SWAMP, which further accelerates exponential convergence in a non-convex learning. And this is the first work to do variance reduction on energy estimator in deep learning, which paved the road for accelerated advanced stochastic gradient MCMC algorithm in non-convex learning. Yeah, thanks for your attention. Yeah, I'm open floor to take some questions. So here's some reference. Yeah, Ralph, please. Yagu.
Hi, Guang.
Hey, Yagu,
Thank you very much for the talk. Really enjoyed it. I have a quick question.
Sure.
I'm actually not sure it's quick, but can you, it seems to me that during replica exchange, so imagine a situation where you have a convex problem, not a non-convex problem. In such a case, replica exchange will not be useful. Whereas in a situation where you have lots and lots of local minima,
yes,
it seems to me that replica exchange will be very useful.
Yeah, I agree with you.
I'm wondering if your theoretical results somehow reflect this. In other words, is there, does this difference show up as to how many local minima are present and what its effect is in terms of replica exchange being effective?
Oh, okay. Yeah. I think that's I think you raise a very good question, right? It's also a challenging question, right? I would say. I think that might be so. Yeah, I think that we need. I think this is a kind of so what we are doing is basically we change this thing to be a kind of sampling approach, right? Instead of optimization, right? So then we estimate the energy. So I think maybe your question like more related to, for example, how do we represent this the multi-mode energy, whether the energy landscape is rough or just single mode, right? How do we represent it, right? In a way so that we can put it into the error estimator to represent maybe the roughness, the smoothness of the energy landscape, right? We use some metric to represent and put into the error estimator. Maybe that's one of the kind of approaches we can use. Right. I think that's definitely a good direction. What you, it's a good question. I think it's worthwhile to look into it to kind of, to represent in a more, look into more details. Yeah, I agree with you.
Thank you.
Yeah, Hajal, your questions?
Hi, thank you very much for the nice talk. I just want to ask a quick question about the numerical examples.
Mhm.
So in all the figures you saw us, you compare the convergence speed for about order 100 epochs.
Mhm.
And actually, when you saw the numerical numbers for the
Mhm.
accuracy, how
Mhm.
many epochs did you use? Okay, do you can you tell us some comparison when the optimization after like 10,000 maybe probably people might use 10,000 epochs
Yeah.
to get the results.
Mhm.
Can you tell
Yeah.
me the result?
Yeah. I think my student Wei Deng is here. So Wei, can you address Hajal's question?
No problem. Can we go back to the experiment part?
You mean here or here?
Yeah,
Here.
maybe the next slide.
Next one. Next. You mean? Yeah.
For the table.
Oh, here. Okay.
Yes. So, Professor Yang, can you like elaborate your question again?
So typically, I assume that to get this result, you may take like 10,000 epochs to get results.
10,000 epochs? No, we just use like 500 or 1,000 epochs.
500.
Yeah.
Okay. So my experience that when I use deep learning, the number of epochs might be very large, and if we compare the curves of different optimization algorithms, sometimes some algorithm might converge faster in the first few iterations, but after that the performance might be quite similar. So I just wonder the performance after like 500 to 10,000.
Okay. For me, I think what all it matters is about the learning rate. You know, when we use a larger learning rate, we're gonna do the exploration, and when we use a smaller learning rate, we're gonna do the exploitation, because the noise in the smaller learning rate will be smaller, right? So it basically this somehow inspires us, like we need to use a very large learning rate and run it for a very long time. And in that case, we have a larger probability to hit the more promising region. And that's why in the later period, it's not that matter at all. I think all that matters is the exploration period. If you explore it sufficiently well, and then you decrease your learning rate immediately, just using a very short period. In that case, you have a very large probability to hit a very promising region. And I feel like, although we may see some similar patterns in the later period, all it really matters is the previous period when we do the exploration. So I feel this is kind of the difference.
So do you mean that learning rate is more important than algorithms?
Actually, you know, this algorithm can be adapted to that algorithm. For example, for 2 replica, and if we will SGD with constant learning rate as a Monte Carlo method, then SGD with a larger learning rate is the exploration chain for the replica exchange, right? And the SGD with a smaller learning rate is the exploitation chain for the lower temperature process, right? So somehow they have to exchange, and learning rate is more important. And in Monte Carlo, temperature and learning rate are both important. So yeah.
I see. Thank you.
Yeah. Okay. So Jianfeng, you have questions? Yeah.
Yeah. So actually, kind of related with the answer for the previous one. So I'm slightly worried that if you using 2 different discretization parameter for the 2 replica, and also there are all these like stochastic gradients involved, right? So can one say something about the invariant measure? I mean, because it's not entirely clear to me that the invariant measure is preserved, or I mean, whether the error can be controlled.
You mean the W2 distance, or what kind of error?
Yeah,
I mean, not finite step, but I mean, like, what's the invariant measure of the process?
I think if we use a constant learning rate, there will be definitely a bias associated with the discretization.
Yeah, but I think you mentioned that you're using different learning rates for different replica, right? So that seems to be a bit dangerous to could that mess up the invariant measure. Okay, I understand your question. And actually, I have thought about this question before. And I feel like, and I have done a simple experiment if we use two replica with two different learning rates, and the result is it's still the same. My understanding is like, for example, we use a larger learning rate for one process and use a smaller learning rate for another process. Then if we become careful about the swapping rate calculation, then let me see. Well, yeah. First of all, it's like that you have the usual replica exchange, right? But then you are multiplying one of the replica, the gradient, by a constant number. I mean, one can think in the SDE level like that, right? Yeah. And I mean, I haven't done any calculation, but that seems indeed a bit slightly dangerous. but maybe it's okay. So I'm just wondering whether you have thought about it. Yeah. How about we think about it in this way? Like we use a larger learning rate for the low temperature process and use a smaller learning rate for the high temperature process. In that way, if we split the larger learning rate for the low temperature process into two parts, one part is for the same learning rate compared with the high temperature process, and another is just a process without the swap. So in that way, the invariant measure can be comparatively the same. So because your question is indeed quite promising, because I ever thought about this empirically, because we are very interested in different learning rates, and I indeed have done some experiment to support my conjecture, and the answer is if we use different learning rates, at least in simulation, it's still the same. Maybe theoretically there are some slightly difference. But yeah, we can discuss about that later. I mean, I think one can actually see theoretically what the effect is. Yeah, I'd be happy to talk later. Yeah, John. Thank you.
I just want to comment on John Feng questions, actually. Okay. So if I understand it correctly, right, you are trying to learn the invariant measure of a gradient system. So by changing the learning rate, it seems to me that you're pretty much just perturbing that stochastic dynamics, right? So then your question probably can be postulated as whether, when you change this around, whether you're still going to converge to the underlying invariant measure associated to the appropriate ergodic measure. I think, is that correct?
Yeah, it could be even worse, right? Because by multiplying one component of the gradient by some number, right, you could also destroy the gradient structure of
course.
So it's actually a bit non-trivial.
So basically, I think the answer to your question probably has to go back to the paper by your colleague, right? Mattingly, Stewart, and so on. They have a paper where it just basically depends on what is the global Lipschitz or local Lipschitzness of the vector field, and then when you make this perturbation, whether you still satisfy all of this condition for ergodicity, geometric ergodicity of the underlying dynamics. I think that's the lead to do that. If I may comment.
Yeah. I think it's a good. Yeah, thanks for the good comment.
Can I interrupt for a little bit?
Sure.
I feel like the geometric ergodicity won't be affected a lot. Anyway, I feel this is a very enlightening question. Thank you.
Yeah. Okay. Yeah. Sounds good. Okay. So maybe, yeah. So we just we need to move on. So let's say so we're gonna start at I think it's 10:20. Okay. So for 1 minute. So Rishi, is Rishi there? Let's see.
Yes, I'm here.
Oh, okay. Can you share screen?
Yes, just a sec.
Okay, so our next speaker is Rishi Kondo. He's an associate professor of computer science, statistics, and computational and applied mathematics at the University of Chicago. And he's going to give a talk on equivariance and Fourier space neural networks. Yeah, Rishi, you can start now.
Great, thank you. Let me switch on the video as well. All right, can you see the shared screen? I presume the answer is yes.
Yes.
All right. Okay. So I'm going to talk about this broad framework of equivariant neural networks that has emerged over really the last 4 or 5 years, but especially in just the last 2 or 3, and has found applications in a variety of domains, in particular when trying to model physical systems and the structures with internal symmetries. And in particular, I'm going to want to talk about the underlying mathematical or theoretical framework, because I think it is one of the ways in which to build in structure into neural networks in a more or less principled way. And it's interesting to see whether building in structure in this way in particular has clearly I guess clear implications in terms of the performance of the neural networks as well. So for the purposes of this talk, I'm just going to focus on the simple feed-forward architectures. And the way I'm going to conceptualize this is just this sequence of functions chained together, typically linear functions that are learnable and interleaved with simple nonlinearities, which are usually pointwise. So what the neural network is going to do is just going to apply the composition of the sequence of functions. And equivariance is defined in terms of the action of the group on each of these functions. So in particular, equivariance deals with the situation where there is a known group which acts on the inputs in a particular way. So the first cat and the sequence of cat transformations here.
Hey, you see, I'm still looking at your first page. So is that correct?
Oh, that is okay. That is a bit of a problem. So how about I share the entire desktop?
Yeah, it works.
And now?
Yeah, good.
All right, yeah.
Mm-hmm.
Okay, so you missed the beautiful cats here. So the group acts on the input to the neural network, which is the 0th layer. What equivariance deals with is how what this transformation results in subsequent layers. In particular, in equivariant neural networks, the expectation is that the group acts in a well-defined way on all the subsequent layers as well. And then typically at the very end of the network, you do something to symmetrize over the transformation because you want something that is invariant. So the kind of groups that people are that crop up in this context are things like the translation group, which is classical and computer vision applications, of course, but also in physical applications, the rotation groups, such as SOD, because ultimately, if we simulate a physical system, we want the whole thing to be invariant with respect to rotations of the system, or rotations and translations together, leading to something called the special Euclidean group. Or if we are dealing with relativistic particles, then the Lorentz group. Or in cases where the system has internal permutation symmetries, such as when dealing with graphs, but we're dealing with certain physical quantum systems where the particles are indistinguishable, then the symmetric group. So these are indeed some of the standard applications where equivariance has been used the most widely and has really become one of the key requirements to just getting off the ground. So there's a little subfield, for example, which is concerned with learning force fields for interactions between atoms in molecular dynamics simulations. So it's clear that in that sort of situation, the force needs to transform with your coordinate system. So if the force is just a function of the nearest atoms and you rotate your local neighborhood, then the force acting on you must rotate accordingly. Another standard application, which has resulted in a lot of papers, is learning different properties about molecules, such as drug molecules, for example. So that's fundamentally a graph learning problem. And there you want to be invariant with respect to the permutations of the atoms. Okay. So the citations are just some of the most recent work, but really there are dozens and dozens of papers that have pushed the envelope in these two applications. But the thing to note in both cases is that, or at least especially in the second case, is that ultimately you want to be invariant to the action of the group. But you don't do that by taking your input data and symmetrizing with respect to the group action immediately. Rather, you propagate this group action through your neural network and you only symmetrize at the very end. And this is important because, in fact, what you want to capture is that the group acts on different parts, say different parts of your data in different ways. And the way that different parts of the data, for example, different parts of the image or different parts of the molecule interact, needs to take into account that action rather than just average out over it right from the beginning. So that is why each layer needs to transform in some predictable way until the very last layer. Okay. Now I have trouble advancing my slides. All right. So this is a fundamental. So in terms of commutative diagrams, the way to contrast these is here. So equivariance means that you have a transform, and you have these two layers. So the input and the output to a given layer. You have the action of or the behavior of the layer is captured by phi, and equivariance means that the action of the group on the input and the output to the layer can be interleaved with the phi transformation itself. So this is captured by the diagram on the right. In contrast, invariance means that the layer just doesn't care about whether you applied this transformation TG in the first place. Okay. All right. So to approach this in this problem in a systematic way and build up the formalism, the natural place to start is group representations. So I'm going to talk for a couple of minutes just about this concept of group representations in case some of you are not familiar with it. So a linear representation of a group is just a system of linear maps, or in the simplest case, finite dimensional case, just a system of matrices which behave the same way as the group elements do. So here G1 and G2 are two abstract group elements. Remember that here we're talking about groups that are possibly not commutative. So G1 times G2 is not necessarily the same as G2 times G1. So these can be fairly abstract mathematical objects. And what a representation does is that it just translates it to something simpler, namely it just kind of translates the structure into operators, linear operators in particular, which behave the same way. So the representation corresponding to G2 times G1 is just the product of representation corresponding to G2 and the representation corresponding to G1. So this is like the way of modeling the group with the matrices. So why is it that as soon as we start talking about equivariance, this concept of representations comes up so naturally? So essentially, the reason for that is that whenever the group actions that you're talking about, that you propagate through this network are linear, then you can ask yourself, okay, so I've got a particular activation at a given layer of the network, and now I look at what happens to it when I apply the group action. So that's going to be some linear operator. Then you ask yourself what happens if you apply the group action corresponding to a different group element, and that's going to be a different operator. But then you can also apply one group element after the other. So like one translation followed by the other translation. And what you must get is the operator corresponding to the composition of these two group elements. But that's the same as just first applying the first transformation. So the first linear transformation followed by a second linear transformation. So these linear transformations must indeed be actually a representation of the group. So as soon as you have linear actions of a group on a given layer of a neural network, then you're really talking about a particular representation of the group as applied to that layer. So really what we are going to be dealing with is formulating a neural network where individual layers behave according to specific representations of the group. What we need to define is what the representation is and how to actually implement that in the architecture. Okay. So this is very natural in the given context. The slide just reiterates this, this point. Okay, so this is nice because representation theory is really well developed. It's in fact one of those areas of math that binds some part of analysis and algebra together and comes with a huge formalism and some very powerful fundamental tools, especially when the underlying groups are compact groups, so finite or compact groups. So that covers a lot of the ground that we're actually interested in. So it covers things like the permutation groups, but it also covers all the actions of rotations and even the Euclidean group that we're actually interested in. So when looking at these representations, one thing that sticks out is that you can apply a similarity transformation to the representation on the left and the right, and that doesn't really change anything. So that's still that's called an equivalent representation. It's really just expressing the same thing in a different basis. Another thing that that is easy to see is that sometimes representations can fall apart into the direct sum of smaller representations. So that effectively means that this vector space that the representation is acting on falls apart into the direct sum of two or more smaller vector spaces that are invariant with respect to all these transformation operators. So that's like, you know, different parts of this vector space behaving completely independently and not being mixed by these transformations. So clearly that greatly simplifies things, and what we're going to be interested in are the irreducible parts of these representations. So things that really do get transformed as a unit and under the action of the group. Okay, so the reason that I said that it's best to stick to the case of compact groups or a few exceptional cases is that it is for those groups that you can prove that that every representation does in fact decompose into a direct sum of smaller representations. So that really means that in terms of developing the theory, what you're going to be interested in is just the behavior of these individual irreducible parts. Okay, so I don't want to dwell too much on specific cases, at least in the introduction, but as examples, it's easy to think of cases such as the rotation group. In that case, the general theory says that the irreducible representations can all be nicely indexed by a single number, like an L index, and actually the dimensions of these representation matrices, or the dimensions of the corresponding irreducible spaces, go as 1, 3, 5, 7, and so on and so on. The matrices are actually given by something called the Wigner D matrices, which are well known to physicists, of course, and people dealing with geometrical problems in general. They are tabulated and they have the closed forms. I don't want to write down the exact form, but anyway, so this is something that is just a matter of, and they're actually closely related to spherical harmonics. So it turns out that the middle column of these matrices actually corresponds to the spherical harmonics. There's a specific formula to generate them. So this is all well known. A slightly more interesting case is the case of the permutations, which in which case it turns out that instead of just indexing the irreducible representations by numbers, it's more convenient to index them by these diagrams. So the diagrams have something to do with the symmetry properties of the different of these different irreducible representations, or rather the corresponding spaces. The way the game goes is that if you're looking at a permutation group of n objects, then you put down n boxes in these different diagrams. No row can be longer than the one above it. So it starts out with this horizontal thing, and then you can move, kind of shift boxes onto subsequent rows. And there's going to be one irreducible representation corresponding to each of these diagrams. The dimensionality of these grows as the diagram moves further and further away from this flatter one. In fact, it grows pretty steeply, exponentially, and then starts decreasing again when you move closer to the vertical diagram and the end of the sequence. Okay, so there's lots of interesting combinatorial aspects to this game. Everything in terms for the representation theory of the symmetric group, it ultimately boils down to these games that you play with the individual boxes and these diagrams and putting numbers in boxes and so on and so on. But I just wanted to illustrate that this is again something that is well charted and has connections to all sorts of underlying combinatorial and even algorithmic issues. In particular, the diagrams can be gathered in, can be collected in a lattice. I have some trouble advancing my slides, which is causing a little bit of a delay here. Might have to stop sharing this for this purpose. And the lattice tells you about how the different irreducible representations are going to be related to each other. So this is a rich area of mathematics with lots of books written about it, and also including the applications to signal processing and engineering problems and so on. Let me just go on to talk about what bearing it has on actually building neural networks. So, right at the beginning of any treatment of representation theory is a key result called Shor's lemma, which essentially says that if you have a linear mapping from one space that is acted upon by a combination of irreducible representations to another, which is also acted upon by a combination of irreducible representations, then this mapping can only mix parts of the two spaces which correspond to the same irreducible representation. So if you look at a mapping from one space corresponding to some irreducible representation of the group to another space corresponding to a different irreducible mapping, irreducible representation, then that must be zero, because the irreducible representations are really irreducible in the sense that the way that they act on these spaces is essentially just unique. So you cannot change it, change this action by just a linear transformation. So this seems like a fairly minor result, but actually most of the fundamental results in the representation theory of compact groups at the beginning just fall out straight from this. And this result, in fact, is at the cornerstone of the application of this whole theory to neural networks as well, because this is going to give us all the constraints on what the individual neurons can do. After all, the neurons, the learnable part of the neuron is a linear transformation. Now we're looking at the neuron acting on these representation spaces. So this is exactly what's going to define what the neuron is allowed to do to preserve this equivariance structure. Okay. So I now want to relate what this kind of vague things that I said in the last 10 minutes to something that is much more concrete and much better known, which is in neural networks literature, which is convolution. So convolution is this a simple signal processing operation, literally involving using one function as kind of a template for the other function and tiling space with it, that are given by this classical formula. In recent years, it has also been elevated to this magical status that even popular imagination has picked up on, as you can see on the right-hand side of the slide. I'm not sure about the subtitle as applied in terms of what it implies about the perception of our community. Anyway, so convolution is an operation which is trivially equivariant with respect to the translation operation, right? So if you take a function, convolve it with something else, but then you first translate the function, then the output of the convolution is just going to be translated. This is evident just from the definition of convolution. And this is exactly the reason that convolution is the standard building block for for neural networks and computer vision, because most of the time, at least at the lower levels, you want these image recognition systems to be invariant to translation. Okay. Another way to look at convolution is as this kind of template matching idea, where what you're convolving with really is a very small filter, and sometimes in modern systems it's just a 3x3 or a 5x5 filter, which and then the convolution operation, what it really does is it just matches this filter against against your inputs or against the activations at the given level of your neural network, and kind of detects whether what is captured by the filter is present or not present at a specific point in the image. What's particularly nice about this is that when you apply this layer after layer, then you get this kind of pyramid of filters, which is able to ultimately capture features at multiple different scales. So first you detect smaller features, and then you detect combinations of features, and so on and so on. And the whole pyramid is equivariant with respect to translations. So the question is, the natural questions that people ask is whether it's possible to generalize this whole machinery including the equivariance and including this multi-scale structure to the case when the group is not the translation group, but for example, the rotation group or the permutation group in terms of, in the case of graphs. And whether representation theory in particular can help us with that. So the answer is yes, because convolution has a natural generalization to groups. So what is convolution based on? Well, it's based on the notion of just moving, translating functions, and that then the definition of convolution is, as I said before, and it's clear that with respect to the translation action, convolution is equivariant. Now, in the group's case, the notion of translation of functions is well defined. It's essentially just the action of the group on the corresponding function looked at as a vector in the corresponding vector space. And then the notion of convolution that it gives rise to is what you see here. And indeed, this is going to this is a linear operation that is going to be equivariant with respect to this action. So if you rotate your inputs, then you do a convolution, and the convolution is going to get rotated correspondingly. The trouble is that this operation looks a bit, in terms of when you think about actually implementing it on a computer, it seems a little frightening, since it involves an integral with respect to that new in the formula is the power measure, the natural measure on the groups. It involves an integral over the whole group. So if you think of doing this on the Lie group, such as the rotation group or the Lorentz group, which don't even have regular discretizations, then it's clear that this is going to be a very expensive operation and it's going to involve quadrature error and so on and so on. Okay, so the way out and that people have realized can make this much easier and translate it into kind of a crisp concept in the neural networks context is realizing that not only convolution, but this whole machinery of Fourier transformation also has an analog on groups. So, and we know that the convolution is an operation that looks particularly simple in Fourier space. So on the left-hand side, you can see the classical Fourier transform. If you just kind of squint and try to generalize it by sticking in the corresponding analogous concepts in the non-commutative case, then you realize that you need to do an integral over the group of your function to get the Fourier transform. But you also realize that e to the minus ikx, which is like the kernel of the ordinary Fourier transform, what it is simply just the representation of the group. So the claim is that the reason that there's this e to the minus ikx in the ordinary Fourier transform is because those e to the minus ikx's are the irreducible representations of the translation group, or of R or RD in higher dimensions. So the way to generalize this is to simply do the same for the irreducible representations of the group that you're working on. Okay. And if you do this, then it's a little strange because now for non-commutative groups, you have high dimensional representations. So that rho of x is actually a matrix valued function. So the Fourier components are going to be matrices. On the other hand, much of the rest of Fourier analysis generalizes beautifully. In particular, convolution still looks like a product, except that now it's a product of matrices rather than the product of scalars, as in the classical case. Okay, so this means that if all that you're interested in is convolution, and that's what you're trying to get your neural network to perform, then it's much easier to work in Fourier space and make the neural network do all the work in terms of these matrices rather than in terms of the underlying function. So this machinery also allows you to prove general results about the whole formalism. In particular, it was in 2018 that we had a paper which showed that This notion of generalized convolution is the only linear operation that you're allowed to have in your neural network if you want linear operation. So it's the only linear learnable operation which is going to be equivariant to the action of a group under fairly broad conditions, essentially in the case of any finite group or any Lie group. Okay, so in the this was a theoretical result, but in parallel, a very large number of empirical works have appeared applying this whole formalism to a range of different cases. There's even a GitHub site which keeps track of the literature. This is just some part of it. Noticing this connection between group operation and group convolution and what's actually done classically in convolutional neural nets goes back to the paper Taco Cohen and Max Wenning's paper in 2016. And this was generalized to the case of steerable convolutional neural networks the following year. And subsequently, it was applied to convolution on spheres, all these force field learning neural networks, a whole bunch of applications on computer vision and robotics and so on and so on. So this is just a subset of the literature as of December last year. I'm sure the list has been updated since then. Okay. But I want to go back because this is meant to be a theory talk concentrating on the fundamentals here. I want to go back to the underlying algebra and what this analogy with Fourier transformation really is trying to tell us. Because one way to look at what's going on in these neural networks is in terms of always functions on the entire group, maybe their Fourier transforms, but really it's simpler to look at it in terms of just these irreducible subspaces. So the Fourier transform, after all, is just a linear transformation from the basis of functions on a given set or functions on a given group to a basis which is adapted to the subspaces which actually correspond to the different irreducible representations, right? So if you do the classical Fourier transform, you get the Fourier components, then the kth Fourier the Fourier component indexed by the wave number k is going to transform as e to the minus ikx when you apply a translation to the underlying function. The same thing happens in the case of these non-commutative Fourier transforms. So really what the Fourier transform is just the diagonalization of all these of all these of the representations, the block diagonalization. So expressing it in a system where the function clearly separates into these components transforming to individual irreducible representations. Okay, and the reason that and then the underlying reason for the theorem that I showed you, and the underlying reason why it makes a lot of sense to actually in an equivariant neural network to represent your functions in this basis is that according to Shor's lemma, these subspaces corresponding to the different irreducible representations must indeed transform independently. Apologize for this. Some delay. Sometimes the computer is just not responsive. Okay. Okay. So another way to formulate the problem is simply that you want to build some network consisting of these individual processing units called neurons, and each neuron receives inputs which correspond according to specific irreducible representations. Then it needs to do something to combine these inputs, but it needs to output something which is guaranteed to transform according to another irreducible representation. So the fundamental question is, what operations is the neuron even allowed to perform in this case. And then the corollary of the previous theorem is that really all that's the linear part of the operation, in order to preserve this structure, must just be that you collect all the parts of the input corresponding to a given irreducible representation into a matrix. And then what the neuron is allowed to do is just multiply that matrix by a weight matrix. So that means literally mixing the columns of the matrix corresponding to the different copies of the same irreducible representation that occur, but not messing with what happens to the vectors in the irreducible subspace internally, and in particular not transferring information or not mixing not mixing vectors corresponding to different irreducible representations. Okay, so this is a very so this theorem really reduces the operation of the neuron to a very simple operation. It's simply just matrix multiplication, and also something that is very efficient and natural to implement in present-day neural network architectures. So diagrammatically, all that the neuron allowed to do is this, right? It takes the different irreducible parts of the input that it has received, and it mixes it with other irreducible with other copies of the same irreducible part, but propagates them, propagates the parts corresponding to different irreducibles completely independently. What I have not talked about yet is the nonlinearity, because that is something that puts a little bit of a twist on this game, because in general, nonlinearities, especially the drastic ones like the ReLU that people like to use in present-day neural networks, do not have such a nice expression in the Fourier space, even in the classical domain. And they do tend to mix the different Fourier components. So essentially, in these equivariant neural networks, it is always the nonlinearity which permits any sort of information transfer between the different irreducible parts of your data. So here again, we are in the situation where the neuron receives information corresponding to different irreducible representations. But now we ask the question, what is the nonlinear, so following this learned linear operation, what nonlinearity is it going to be allowed to do to ensure that still the entire, the neural network remains equivariant? Okay. So various things have been proposed. The simplest thing is always to transform back onto the domain where everything is expressed and on the original group. And then you apply a pointwise operation. So if you think about it, that's exactly what happens in the case of classical convolutional neural networks when you have something like ReLU operation. So that's clearly equivariant because you're applying it separately at every point of your image. So essentially applying it independently or pointwise at every group element. You can do that generally in any of these group equivariant neural networks. The trouble is that it again requires an inverse Fourier transform. So then you need to go back from this expansion in terms of Fourier matrices, you need to go back in terms of looking at your activations as a function on the underlying group. And that operation is again fraught with computational expense and potentially errors. An alternative, which you might think of, is just to take products. In particular, once you have these Fourier matrices, just take their tensor products. So how is that going to transform according to the group? Well, it's going to transform according to the tensor product of the corresponding representations, which is of course also representation, but in general, it's not irreducible. However, so this will give you the nonlinearity. It's only a quadratic nonlinearity, but at least it's easy to compute. And because the resulting but because the resulting object does not transform according to just one or the other irreducible representation, this actually can mix the different isotypics, so the different irreducibles. But what you then need to do is need to look at what comes out and again reduce it in terms of irreducibles. So this is the very fundamental question. What happens if you take the product of two irreducible representations of the group and take their product? How is the product going to, what combination of irreducibles does that correspond to? How is the product going to decompose? So this is such a fundamental issue that this comes up multiple in various contexts in representation theory, and at least for the more common groups, people have worked out the solution in painstaking detail. This is called the Clebsch-Gordon transform. Those of you who have a background in physics will recognize it as from the context of, say, adding the angular momenta of different particles. This is exactly the same thing. It's just the question of how to reduce or reinterpret the tensor product of these irreducible spaces as a linear combination of irreducible spaces. So if our neural network or a poor neuron is actually aware of this theory and is able to perform this operation, then it can do a nonlinearity, which mixes the different irreducibles, yet also, and it can also reduce the output into irreducibles again, which can be combined with the irreducibles from other neurons in the same linearly and as the same way as before. So again, we get an output which transforms according to the group in this very controlled way. Okay. So this gives, so this is now a prescription for the entire thing. We have a prescription for how to do the linear part of the neural networks operation, how to do nonlinearities, and we can do the whole thing efficiently in Fourier space. What's also nice, as you will see in the next few slides, is that it also meshes really nicely with the just the kind of the expected form of, say, physical laws in any sort of context where you are where you're dealing with learning to model physics, because it's just in the character of physical laws that individual quantities that appear are, vectors and tensors and maybe higher order things or more exotic objects and particle physics. But there's always this obsession or concern with how quantities transform according to underlying symmetry groups. And in particular, when you take products, such as in the addition of angular momentum or in other cases, how those products decompose again. And finally, everything usually collapses into something like a scalar, like energy, or a vector like distance, and so on and so on. So if you follow this kind of prescription and build neural networks out of these ingredients, then you get something that is strictly equivariant. So it respects the underlying symmetries. It is efficient, and in some sense, its structure also mirrors the kind of structure that you expect from physical laws in the first place. And computationally, it just boils down to doing these linear operations, which are like the bread and butter of all these architectures, followed by this single quadratic operation, which involves the Clebsch-Gordon transform. But the Clebsch-Gordon transform itself is just a linear decomposition, right? So this is also relatively efficient and easy to implement. So one context in which our group pursued this is this force field learning problem. We developed an architecture called Cormorant about 2 or 2.5 years ago now, which was where the whole architectural network was actually modeled on the type of interactions that people already talk about in this molecular or chemical setting, right? So you've got parts of your system which correspond to actual atoms, and the actual atoms interact through electromagnetic forces. You have monopole interactions, and you have dipole interactions, then you have quadrupole interactions, and people obsess about how to build good force fields from these and how they might combine and so on. Now, it turns out that if you allow your imagination, if you relax things a little, allow your imagination to run wild and just try and build a neural network to learn the same forces from first principles, then and you follow these rules of equivariant convolution and the tensor products, then the parts of the neural network will actually look pretty similar. There's going to be these interactions between the L equals 0 and L equals 1 and L equals 2 irreducible representations, which kind of correspond to the same monopole, dipole, quadrupole hierarchy. Now we had to throw in a couple of extra things to make this actually click. We had batch normalization, and we had a more complicated form for what the individual layers look like. This is the actual layer in what we tried. I'm convinced that it can be simplified further. And in fact, since then, a number of other authors have come out with publications which propose alternative architectures, but still following the same underlying principles. So this, at the time, actually reached pretty much state-of-the-art results in terms of just this force field learning problem for molecular dynamics. Since then, some more complicated architectures have surpassed it, I'm sure. Okay. Now, in the remaining part of the talk, I wanted to talk about how essentially the same machinery can also be used in a discrete setting in the context of graph neural networks. I'm not sure. I guess I only have 5 minutes, so I'll have to skip through most of these slides. But just to give a kind of high-level overview, graph neural networks are an interesting beast because they can be very broadly applied, and indeed people use them for a very broad range of in very different ways in different types of applications. But they are subject to not just one, but a whole range of kind of conflicting expectations. So one of the fundamental one, what fits naturally in this equivariance framework, is that the first thing that you realize when starting to think about any sort of graph learning algorithm is that no matter what the algorithm actually does, it needs to be invariant with respect to relabeling the vertices, right? So this is just another, and one way to look at graph neural networks is just another instance of this equivariance phenomenon. You have multiple layers, and at each layer, what propagates in neural network somehow corresponds to the underlying vertices. But if you permuted the numbering of the vertices at the beginning, then you know how each of those layers are expected to transform. But in addition, in graph neural networks, you want a couple of other things. So, for example, people are very interested in picking out local structure. Like really, in the case of the molecules, you want to pick out functional groups. On the social networks, you want to get small groups of individuals related in specific ways. And you also want to pick out multi-scale structure, potentially, as in the case of convolutional neural networks. But you need to realize that here it's much more tricky, right? Because you are dealing with an object where the structure changes from point to point. So how do you define this kind of hierarchy of filters then, when every part of the graph, the filters are going to combine in different ways? Yeah. And finally, there are existing notions on at least parts of the graph. Many, if you look at again, say molecular graphs and geometric graphs, then they are full of little cycles or little paths, and in those cases, it's very natural. It's a natural expectation that whatever definition of convolution you come up with for the graph, you want it to reduce to the known standard definition of convolution on these substructures. So putting these 4 components together is one way to look at trying to put them together is with one perspective to look at all the literature on graph neural networks from, and all the kind of open questions in terms of how these criteria are in some sense conflicting. So an earlier attempt at graph neural networks tried to follow the classical route of the spectral graph theory and build actually a analogy with convolution on Euclidean space using the Fourier formalism, just by diagonalizing the Laplacian. But then an alternative approach, which actually is the most popular and kind of simplest to capture algorithmically and therefore very popular nowadays, is just to say that, well, I want an operation that similarly to ordinary convolution just kind of transfers information locally. So it's a bit like message passing. It's just a message passing that is invariant to the local structure which neighbors you receive the messages from. So let's try and build a graph neural network based on these principles. And then there are more complicated versions of these things. For example, one of our earlier papers attempted to follow the message passing idea, but built up higher order versions of it, where in fact the local structure is maintained up to a certain number of levels by keeping track of which neighbor information came from in these tensor form messages. But more recently, this literature was kind of tied up with the general principles of equivariance, in particular equivariance to permutations, and the most fundamental requirements for satisfying equivariance, while still allowing for the maximum amount of freedom in principle in these neural networks, was formulated in this paper called Natural Graph Neural Networks by Dehaene et al. Okay. So, and looking at this more closely, you'll not be surprised to learn that one way to enforce all this, and one perspective to look at it, is again through
you might want to wrap up.
Permutation group. Yeah, I realized that's why I was trying to just give the high level picture here. Okay, so if you look at the problem in terms of equivariance of the permutation group, you realize that what's really going on is that you have these vectors and matrices and tensors which correspond, which transform according to permutations, local permutations, hopefully. And then the question is how you stitch these together into larger objects. And the fundamental rules are again reduced to the action of the symmetry group on these various objects and how it decomposes into irreducible parts. So in this regard, what I wanted to finish with is this recent work, which applies this formalism to graphs, in particular to molecular graphs, but is a little bit more sensitive to the local structure than previous works, in that it realizes that all this formalism is great, but actually locally, and you could say that what you always worry about is equivariance to permutation at every local part of the graph, but actually when the graph at a particular region has a simpler structure, for example, it's just a path or it's just a cycle, then then the right group to look at is not all permutations, but only those permutations which preserve that structure. So just the local automorphism group. So that's why this work is called autobahn, because it's based on the local automorphism group and can act and explicitly identifies the local subgroups and creates an architecture which applies this whole formalism, but to these local subgroups, and then stitches them together into something that is globally equivariant. All right, I think this is the right point to stop, because it's kind of brought together the continuous and the discrete, but only a couple of minutes late.
Thank you. It's fine. Yeah, Rishi, thanks for the nice talk. So due to the time limitation, I will move to the next speaker. And Eric, can you Rishi, can you okay, all right, good. So Eric, can you share screen?
Yes, I am.
Okay, good. Yeah. So our next speaker is Eric Hsieh. He's a staff scientist at Sandia National Lab. He will give a talk on a layer parallel approach for training deep neural networks.
And so do you see my
yeah, I can see it, but it's not in the presentation mode. It's in the navigation mode.
How's that?
Okay, good. Yep.
Okay, great. All right. Yeah. So I'd like to thank you for the opportunity to give this talk. It's really been a great seminar, great series, and so I've been really interested to see all kind of the different work in this thing. So I really appreciate the opportunity to give a brief kind of overview of some of our work in developing a layer parallel approach for training deep neural networks. So as I said, my name is Eric Hsieh. I'm from Sandia National Lab. This is joint work with a large number of people: Stephanie Gunther, who's the Fernbach Fellow at Lawrence Livermore, Lars Rothoto at Emory, Jacob Schroeder at UNM, Nico Gauger at TU Kaiserslautern, Gordon Moon, who's now in South Korea at the Korean Aeronautics University, and Ravi Patel, who's a staff member at Sandia. So I'm going to start off kind of slow. So we'll start off by, in my kind of standard way, defining what a neural net, my view of a neural network. And there's a lot of different perspectives. We've seen graph neural networks, we've seen all kinds of deep O-nets and all this stuff, but generally the structure kind of sort of follows this kind of form. So a neural network, and from my perspective, is really just a parameterized model where we take an input, and then we have some parameters and then some output, and we'd like to learn the kind of mapping from X to Y as specified by some data. And typically this is composed of multiple layers. So in this case, we talk about these feature vectors used here. We have our input data, and we go through an affine transformation defined by A0 and B0 in this case. And then and that defines kind of our first kind of feature vector. The next feature, then we can iterate this in a kind of a layer-wise fashion, where each layer is defined as this kind of this activation function, which I'm writing kind of very abstractly as F here, this mapping from layer I to layer I+1, subject to these parameters AI, BI. Of course, we all know, or we've all kind of experienced this by now, that this is typically an affine transformation of UI subject to some pointwise nonlinear activation function like ReLU. And then I tend to just write it like this. At the final layer, I always have this linear layer at the end. Of course, your mileage may vary here. But again, AL is learnable. And so the parameters then are just kind of the combination, the union of the layers of each layer, the parameters from each layer, AI and BI, and then the final layer. Again, nothing new here, really. So in supervised learning, we have input and output. So we want to learn this mapping from input to output, XI to YI. And so we end up the way we do this is by finding our parameterization, our parameters for our neural network that minimize the loss over this training set. And so I've defined the loss here kind of in a pointwise fashion over the data set, so that what it's trying to do is kind of minimize the difference between the neural network prediction here and the observation here. Okay, so if it can find those parameters that minimize this, we say that we have trained this model, we've learned whatever predictions kind of are implied by the training data. All right, so the loss then is a function then of the loss is just a function that defines the difference between the model and the data. And so we have just a standard regression, kind of L2 loss and cross entropy loss here that would be used in classification. All right. So what does training really mean? Typically, this means some sort of gradient descent. You know, we've seen a few different variations on this, but often they just end up, they all have to kind of, if you're going to do a gradient-based optimizer, you're going to have to take the gradient of this kind of objective function at some point. And the way this works is you do a forward propagation, and that gets you kind of on the manifold that's represented by the neural network, the neural network evolution, and then you compute what's called the back propagation to compute the gradients. Okay, so this process is kind of best, and I think of it visually. So we do this really slow, this kind of sequential forward propagation where we take the input, we compute each feature through this network. And so we have to do this in a very serialized fashion where we're just passing information from left to right and so forth and so on. So we get to the output, and that puts us on kind of the solution, the kind of constraint surface that's represented by the neural network forward propagation. Then we compute a back propagation. If you're familiar with PD constraint optimization, I would typically say an adjoint, but you do this with back propagation, and so you transfer information from the forward solution to the, you have to save the features from the forward propagation so that you can then linearize about those and compute the gradient. And so there's this coupling between the forward and the backward problem to compute this gradient. And so there's different ways to handle it, but in general, this is kind of a slow process where you go forward for a little bit, and then you go backward and you get a gradient, then you do the whole thing again. And so there's different ways to accelerate this. You know, there's checkpointing, which would allow you to maybe not store some of these states along the way. But in general, this is an expensive process, and people tend to just go ahead and store these things anyway. All right. So another approach that really has kind of revolutionized machine learning and the use of neural networks and deep learning specifically is the notion of parallelism. And so one can kind of see that the rise of machine learning, not coincidentally, came with the rise of GPUs and really kind of high density compute capability. And so parallel computing is really important to training, is the kind of bottom line there. And generally we do it, you know, focus on GPU level parallelism, thread level parallelism on relatively small clusters of GPUs. And so there's kind of different options that you might have in this context, okay? So if you're familiar with the PDE world and the parallelism in that world, you can think about the first one is kind of a parallelism in terms of UQ, where you would want to sample different points in some sort of parameter space, and then you would solve the PDE and push that through in an embarrassingly parallel fashion. Similar, this data parallel scheme for neural networks, where you have replicated the neural network on each processor, and then you can push through different subsets of the data of your training data on each processor, kind of in an embarrassingly parallel fashion. So you do that forward propagation, then you do the backward propagation to compute the gradient. And then because the loss is typically just a linear combination, you just have to do an all reduce to kind of compute a global gradient. And people do different things to kind of accelerate this and maybe eliminate the need for kind of this global communication. But in general, that's the general structure that really exploits a great deal of parallelism you might have in your training algorithm. A different approach that we're kind of been exploring at Sandia and other places is notions of model parallelism. So in this case, your an individual data item might actually be too big to fit on a GPU. We have examples of this where we have, 2000 by 2000 by 2000 CT scans, a voxel image CT scan, where just to do kind of store the data on a single GPU becomes a actual burden, computational burden. But we still want to kind of learn from that data. And so what you end up doing in this case is you can break up the neural network the evaluation of each neural network layer across processors. Okay, so here you would say, okay, well, this subset of the domain, say subset of the image, is going to be processed by processor 1, another subset is processed by processor 2, so forth and so on. And you have to then do a halo exchange to communicate between them. This works very well in the context of convolutional neural networks, where that exchange is local, and it looks exactly like the kind of parallelism you might see in a spatial decomposition of a partial differential equation. So this is kind of the other approach. Now, both of these approaches are kind of specialized, and they handle two different particular growth mechanisms you might have in a training problem. So if your data set gets larger, you can always do data parallel. If your data items get very large, you might do model parallel in this context. So those have been existed for some time, and they've been approaches that people have used, although the software maturity, I think, is the maturity of the tools is still a little bit limited, although that's growing rapidly in the model parallelism case. So another question, another dimension of the neural network, which neither of these models kind of address, is the growth and depth. So if you have a neural network and it's 8 layers, but you've decided for whatever reason you'd like to double the number of layers to 4, I'm sorry, you start with a neural network of 4 layers and you'd like to double it to 8, there's really nothing to kind of neither batch data parallel or model parallelism as defined previously is going to really reduce that runtime. And so if you're really interested and you want to get to 128 layers or 512 or something like that, then maybe this becomes a computational burden that you can't overcome. And note that this isn't really going to be solved by a bigger computer, right? As you go to if you do data parallel or model parallelism, you run into kind of a strong scaling limit where either the stochastic gradient descent algorithm might break down with too much data parallelism, or you run into kind of a traditional strong scaling limit for model parallelism, kind of the spatial parallelism, where adding additional processors don't really do you any good because you have the communication cost relative to the computational work is simply too high. So this is a kind of parallelism we're going to attack. And you know, in general, one can ask the question, well, do you really need a 500 layer ResNet architecture? And you know, I think it's arguable that you probably don't. There's also this development of these neural ODEs where you would discretize in some sort of time dimension as opposed to a layer. That could lead to deeper neural networks. The last one, and the one I'll kind of spend the most detail on today, is in recurrent neural networks. Here, the depth of the kind of evaluation that I'm thinking about is actually defined by the data itself. And so really, if you have, say, a very long movie, you know, a spatial parallelism or a model parallelism might not be as effective for training and accelerating training as you might need. And so how do we address these kind of the growth with the depth in the neural network? So before I kind of talk about the algorithm that we use to do this, I'd like to make a transformation that I think is a very useful one. And the idea here is to take the loss that we have and say, oh, well, you know, this neural network evaluation, we can replace that with the output Y here. Okay, so all I've done is I've kind of taken this neural network that I wrote here and wrote it now as a constrained optimization problem. This training problem is this constrained optimization problem where I have kind of unrolled the neural network in the constraint. Okay, what this allows us to do, and this is just kind of an algebraic trick, there's really nothing special about this kind of structure, but what it allows us to do now is to think about these equalities as approximate Okay, so what we're going to do is we're going to allow ourselves to relax this equality statement here. And then what that inexactness actually makes room for kind of sneaking in parallelism and doing notions of domain decomposition in that structure. But the key then will be to add convergence for this kind of training problem to then recover these equalities, right? So it allows us during the training process to deviate from that, take advantage of it by doing something a little bit faster, and then only at the convergence you actually end up kind of recovering the equality. In fact, we already saw this a little bit earlier today when George Karniadakis talked about his domain decomposition algorithm. He had his little dolphin, and he was using a penalty to tie those things together. He was allowing if I understood the approach correctly, he was allowing the boundary of the dolphin to be inexactly kind of matched at intermediate phases of the neural network training, so that only at convergence does he kind of at some notion of convergence or minimization, does he actually guarantee that those things match. But in doing so, he is able to actually get more parallelism out of his training algorithm. So I've now kind of talked at a high level about what we're going to be going into. The kind of motivation here, of course, is that training neural networks can be costly, kind of weeks of time to really do these things. There's lots of data to look at, lots of weights and features to optimize. These are all expensive operations. And so the question is really, can parallel computing in general and high performance computing kind of as a familiar to the kind of PD simulation world, really, or scientific computing world, be of help here. And already, these GPU codes are really helping. And I'm, really enthusiastic about kind of the degree of optimization algorithms that we're seeing being developed both here and elsewhere, and as an opportunity for both kind of faster training, but also the opportunity to introduce different levels of parallelism, different approaches to parallelism. So the rest of the talk will really concern kind of this layer parallel idea specifically. So, I drew those pictures of data parallel and model parallel before. This is kind of the obvious extension to layer parallel, where you put each layer on a subset of layers on each processor, and then you want to be able to do kind of local work on each processor, and then communicate the kind of connection between them, kind of at some convergence. So we're going to try to. So the way we're going to do that then is we're going to assume an inexact evolution. As I said, that's kind of a repeated theme. You'll see it at least once more. And then we try to stitch them together in some way at the end so that we actually converge to a correct neural network problem solution. So, I had a postdoc and he started at Sandia, and the first thing he did is, of course, went and presented his thesis work at supercomputing. And he was talking to his friends and he said, well, okay, this layer parallel idea really makes no sense. They're kind of right. So you have a gradient descent algorithm where you're doing a forward propagation. This is a serial thing. If you remember that really slow, boring movie from before, we saw forward propagation is necessary. And then we have back propagation, where we kind of move backward through the neural network, again, slow and boring. And then we update the weights and biases with the gradients, with the computed gradients. So because these things are serial, it really doesn't make a whole lot of sense to then do this layer parallel approach, right? But of course, I've already motivated what we're going to be doing. We're going to relax the exactness kind of assumed in traditional forward and back propagation by introducing an error. That error is going to be controlled by whatever algorithm that we're going to use to actually introduce that error. But ultimately, it will give us an approximation to the forward propagation that we can exploit to get kind of better performance. And so just by doing this simple trick, which is a very common trick in numerical methods, so like we know how to exactly invert matrices, but we tend to use Krylov methods because they're much faster. Those are really just inexact kind of inverse operations. So this trick is very common in numerical methods. And so we're going to try to exploit this in the machine learning context, in this neural network context. And so I'm going to actually do this through a multi-grid algorithm, which I'll explain here momentarily. There's one last transformation I'd like to make just to make my storytelling a little simpler. We're focusing on ResNets. The reason for this really is that the ResNet architecture is more stable at large number of layers than, say, the traditional kind of feed-forward neural network, which suffers, say, from vanishing gradient problems. And so one transformation that's been recently developed is to transform this kind of ResNet architecture into an ODE. So the way you do that is by pretending at each layer you've got some little delta t parameter here, and you recognize this as explicit Euler time discretization, and you transform that by taking delta t to 0. And so now your layers are represented by basically the time value, and you end up solving this ODE for the neural network instead of this kind of algebraic kind of equation. So there's a number of different papers about this, both this paper in NeurIPS several years ago, and the stable architectures that Lars and Eldad Haber put together. So with this formulation, this time-dependent formulation, we can start to leverage some of the existing methods in the say PDE community or ODE community that use parallel in time. So there's a nice review article by Martin Gander on this, but the kind of highlights for me are this parareal algorithm, which was, very classical and kind of started the resurgence in parallel in time algorithms. The FAST algorithm by Michael Minion and collaborators, that's kind of an extension of that approach. And then a very kind of similar algorithm is this multi-grid in time kind of approach developed at Lawrence Livermore. And this is the kind of approach that we'll be taking in this talk. All of these algorithms kind of do the same type of thing, where they do a decomposition of the problem into kind of coarse kind of evolution and then kind of fine corrections, okay? So in the multi-grid context, what we're going to do is we're going to take our fine grid neural network, say, that has 8 layers, and we're going to take a subset of it that, say, only has 4 layers, okay? On the fine level, we're going to be able to do local work where we just assume that the kind of initial guess, say for layer 3, came from whatever kind of previous information we had about the output of layer 2. Okay, and then we're going to do a relaxation here. So we're going to basically do several sweeps of forward propagation in this case. And that produces a local approximation of the state of the neural network. Then we're going to transfer that approximate state to the coarse grid and say, okay, that we know that's inaccurate because we've not resolved these kind of discontinuities here. And so we'd like the coarse version to resolve this discontinuity by propagating serially. Okay, so now we do a cheap but serial operation on the coarse grid and produce a correction to bring back to the fine grid. Okay, so the fine neural network now has a correction that has global information, kind of end-to-end communication throughout the whole neural network, even if it's at this kind of coarser representation. Now it takes that correction and then uses that to update its, to locally update in an embarrassingly parallel fashion each of the states for the neural network. Now you can repeat this process kind of multiple times, where you go through the exchange between fine level and coarse level back to fine level until you actually achieve convergence for the forward propagation. So basically, you don't really have the you always have this discontinuity until you actually reach some sort of convergence within this kind of iteration. And for the forward propagation, for instance, you can do this kind of in a multi-level context by just recursing again, and so that you have you assume that this coarse problem isn't coarse enough, you coarse in again, and you have, say, a 3-level method or a 5-level method in this multi-grid idea until you get whatever performance that you kind of require. And so we do this for both the forward propagation, and if you reverse all the arrows, we do it for the back propagation too. Okay. So then how does this algorithm work? So we've tested this on these ResNets using kind of 3 different kind of problems. We have the peaks problem that Eldad and Lars put together, where the idea is to classify the location of point clouds in a level set, which level set they belong to. You also have the Indian pines, and this is a hyperspectral imaging thing. You're trying to determine if this field is corn or soy or like chinchillas or something. And then you have MNIST, which is the classic handwritten digit representation. So the first set of results that I'm going to show are based on the XBraid code. Well, they're all based on XBraid, but we actually wrote a hand-rolled C++ neural network code just to kind of work through the details of how one might go about doing this. And so the neural networks for these problems are not optimized. You certainly don't need a very deep neural network to do MNIST, for instance. And then the performance isn't really tuned. So I'd like you to kind of bear that in mind as we're looking at the results. And then, know that we're spending more time on this now to make sure that the performance is kind of where it needs to be in the serial evaluation. All right. So for these 3 problems, what we have here is the training loss and the validation accuracy. So the training loss here is the solid lines. The validation accuracy is these dotted lines as a function of iteration or epoch in this case. And here we're using the layer parallel is in purple and layer serial is in cyan here. And what this is showing is that both for the peaks and the Indian pines problem, despite the fact that we're doing this kind of inexact forward and backward propagation, both the loss and the validation accuracy is matching well the serial version of the code. So we're not really being penalized from an accuracy standpoint for these problems for actually doing this inexact forward and backward propagation. So then the question is, how does the speed up actually work? Well, if we do a weak scaling study, this is where the neural network gets deeper as we add more processors. And so we're able to kind of run a larger neural network. We see that the runtime is basically flat. It doesn't grow with deeper neural networks, but we're adding more processors to balance that out. So this is kind of ideal weak scaling, showing 10x and 16x kind of speed ups for both Indian pines and MNIST out to 2048 layers. Pretty deep layers and 512 cores, okay? In the strong scaling case, we have, in this case, we have a fixed number of layers, and we're just kind of trying to accelerate the training algorithm with by adding more processors and doing the layer parallel decomposition, we see that we get good strong scaling, especially for the deeper neural networks. This is a feature of multigrid in time, where it actually does work better as things get deeper or you have more time steps. So this is kind of the expected behavior, where if you have relatively few time steps, in this case 256, you see that we're only breaking even at around 16 processors. We've now been able to shift these things down a bit, so that even at like 128 steps, we're able to get speed ups at 4 processors. So we're moving in the right direction, but that's really a very big challenge with any parallel in time method. All right, so the prior algorithm that we were using was actually more of a kind of second order optimization method. Here I'm looking at how neural networks actually work in how we can actually use layer parallel in the context of stochastic gradient descent, and if this actually works just as well. So to start with, I looked at these fashion MNIST. Okay, so it's nice because it's a very small problem, but it's known to be harder in some sense than the standard kind of digit MNIST data set. Okay, it's harder to achieve good accuracies, basically. And so what we can see here is that regardless of the number of processors that we use, if we use serial or parallel, the algorithm, the training actually gets to kind of the same level of accuracy as the serial algorithm. So this is kind of what we want to see, is that despite doing this inexact thing, like I talked about before, we're actually doing very well in terms of test accuracy for the training. All right, so I want to shift gears a little bit from the kind of ResNet image classification type problems I was just talking about to more sequence classification problems. So in sequence classification, you have a sequence of input kind of data. So you would have like a time series, or maybe it's a video. In our case, it'll be videos in time series, where you want to take that operation, the sequence, and map it to a particular class in this case. And so we'd like to really learn phi here, which is that mapping function. And so the solution that's been come up with over several years, at least one of the solutions, is recurrent neural networks. So what a recurrent neural network does is it takes as input the sequence, okay, and produces a hidden state. That hidden state is then passed to the very same neural network, neural network, and that one takes a new entry in the sequence and then passes it along. Okay, so basically, this queue is going to then be basically sliding over the sequence, and you're going to kind of iteratively maintain a hidden state, kind of based on the observed sequence between entrances, values in the sequence. In the final layer, you have the output of the hidden state, and you can do classification or regression. There's also cases where you might just do a straight up transformation of this sequence to some other sequence. We haven't looked at that. I don't view that as kind of a substantively different problem, but it is an interesting next step for our work. If you're interested in recurrent networks, you should look at this Cola's blog. It's basically the best discussion I've found. I'm not in love with the LSTM paper that I originally read about this, but Cola's blog is a pretty good description. So over the years, they've kind of come to realize some of the challenges of recurrent neural networks, and have kind of overcome that with two different distinct architectures. There's the long-term, short-term memory LSTMs and generalized recurrent unit neural networks. And I'm going to focus on the generalized recurrent neural network here. In this case, what happens is you've got this, the hidden state is written in this kind of update equation. So you have some sort of ZT that's computed from these weights and biases on the sequence data, and you can update this hidden state using this kind of expression here. So these equations really just encode the weights and biases and produce an evaluation that is then kind of used for this evolution expression. Okay, so this is the expression I actually kind of want to pay the most attention to in this discussion. So I looked at this a little bit, and before I mentioned that we did this transformation to an ODE form, and I think that's a really useful transformation from the multigrid perspective, because typically in multigrid I require a coarsening operator, a representation of somehow a bigger step, and so a natural way to do this is with a bigger time step. And so I actually introduced this, and using delta t equals 1, I add and subtract the ht minus 1, and then I get this kind of updated GRU formulation where I have a delta t here that represents our fictitious time step. But of course, I can take that fictitious time step to 0 now, and I can learn a little bit about how GRU might actually work. So when I look at this ODE that we get from this, you see that this is a stiff mode, okay? So this is basically a mode that's collapsing onto some sort of multi-rate at some multi-rate kind of asymptotic. This is basically a dissipation term. So it's taking all the kind of old information and kind of deciding on a fixed hidden state that represents it. And then we've got this kind of other term where we're introducing new sequence information. We're injecting more information, basically energy into this system to push us off the kind of the collapsing asymptotic and hopefully incorporate information. And so this is, in a sense, this kind of memory notion. It's just being kind of propagated through some sort of ODE term that has a asymptotic long-term behavior. So when I think about it this way, it kind of suggests that there's a problem. If I want to take delta t equal to 1, and then I double my time step size, it may be that stiffness reveals itself as instability on the coarse grid in the multigrid context. So that's going to be a problem. And so what we end up doing then is say, oh, okay, well, I know where that stiff term comes from. This term here is the stiff part. So I'm going to put it on the left-hand side and make this thing implicit in this stiff term. So I'm changing the GRU algorithm now a little bit. And when I do that, it allows me to actually take bigger time steps and step over this stiff mode, this kind of this stiff decay here. But still kind of incorporate kind of the instantaneous information from the sequence data. So we're going to leverage this in the multigrid and time solver. So there are different options that we can use for this, but the basic idea here is that I want to do this implicit GRU on the fine level using delta t equal 1. So I'm going to be very close to what a standard GRU is, but I'm going to just set delta t equal to 1 on the finest level, and then use on the coarse level bigger delta t. So I have a couple of examples here. We have got human activity recognition using smartphones. This is a really small data set. You have 6 labels. Each sequence has 128 steps with 9 features. We're going to run this through the GRU approach. And in general, for GRU and LSTM with 5 to 10 epochs on atom, you can get to 90% test accuracy. So this is a really easy problem. And so, we're not going to get great speed ups here. You can see here, for the parallel GRU here, we're able to get about 2x speed up over the serial version. We use a lot of processors to get that speed up, but we're able to actually get speed ups. And then the other question, and there's 2 aspects to this other question, is the classic GRU, say the explicit GRU, as good as the implicit GRU as good as that? That comparison you can see with the dashed lines, the black lines, they are basically pretty much the same. So implicit GRU and serial GRU are kind of in the ballpark doing the same thing. Then we can ask, well, okay, how does our parallel GRU work if I'm using a parallel inference? So that's this red line here. So this is as trained, basically. The parallel GRU actually does kind of comparable, roughly, to the serial versions. The last one is this serial inference. So what this is I take the parallel trained algorithm, take the learned weights and biases, shove it into the serial one, and then do a serial inference. Okay, and because you know, the parallel version has all this error in its propagation, the parallel GRU, the serial GRU in the serial version does not in the inference. One can ask the question, are those kind of giving you the same answer? Is the parallel inference kind of good enough to be applied in serial? Have we resolved those discontinuities well enough? And the answer is, from a test accuracy perspective, we have. In spite of the fact that we're kind of doing this inexactly, the serial inference still works just as well. So going to kind of a more challenging database, we're looking at this HMDB51, which is a large human motion database where we have a large number of classes of different kind of human motion activities. I'm just going to take a subset of those. So we have these videos that show people chewing, eating, jumping, running, sitting, and walking. And we're going to kind of train on this neural network and see if we can train on this subset data and see if how well we do in the classification and the testing. A comment I'll make about this, because it's relevant from a performance perspective. If you do this, our architecture uses a pre-trained ResNet 18 to take each frame from an image to some sort of classified or some set of features that were pre-trained. And so this is somehow simplifying or reducing the complexity of our recurrent neural network by kind of filtering through some sort of or pre-trained ResNet to limit the kind of complexity of the classification task. And so what you end up with here is a new set of sequences that are just based on using this kind of ResNet architecture. A few details, we have a batch size of 100, we're using Atom, and then I'm very careful to not apply ResNet 18 on the coarse grids of my multigrid scheme. And this is because I really don't need to. I've already evaluated on the fine grid, so I might as well just reuse them on the coarse grid. And so that's what we do. So each image for both the serial case and the parallel case, the feature is only computed once. This is saving some computational effort. So in terms of loss for the different versions, so we've got the implicit in parallel and the classic in serial. We see that the loss is kind of decaying kind of equivalently. These are very similar results in terms of the training. And then the accuracy is kind of in the same ballpark for all of them. And so that's kind of what we want to see. And I will say that the implicit one, if I then shove that those weights and biases into the serial inference implicit GRU algorithm, those actually work just as well as the kind of parallel accuracy. So as before we saw with the previous data set, we haven't really lost anything by doing this inexactly. For this case, we have 128 processors, 128 time steps. We're able to get to 7x parallel speed up with 32 processors. So this isn't ideal parallel efficiency, but it is showing that we can get real speed ups that can actually really help our problem. And if the data set gets deeper, so for instance, in the kinetics 400 data set, it's 256 frames basically. we can expect kind of better speed ups as we go to longer problems. So that's a kind of a scaling curve that we want to be on. To kind of break this down a little bit, I'm interested in seeing where I'm getting performance benefit. So I've broken this down. This is a linear scaling, time scaling plot. Here we can see that these things scale really well, just like we saw in the previous for the total computation. It's probably a little bit easier though to look at the log plot, but it's just not as pretty from a performance standpoint. So we see that basically the forward time is dominating here. Even for the serial algorithm, and the backward isn't nearly as expensive. This is something I haven't dug into, but I'm pretty interested in kind of figure out why that we have that strong disparity. There is some disk read where I'm reading these movies from disk kind of constantly through the algorithm. The parallelization gives you better performance here because you're able to kind of spread that out over more processors. So that's an added benefit, but I think it's one that's kind of a little bit false because we can always cover the disk work with the forward work. So that's some further improvements we need to do to our algorithm. So that's kind of the end of the algorithmic discussion. I will say we have a code, we call it Torchbraid, that combines kind of PyTorch and XBraid, and those previous results for recurrent neural networks are based on that. It has a computer architecture, which I'm happy to talk through if you're interested. And then let's see, and so it gets good speed ups. Okay, that's what we've seen in the end. Even for the ResNet case, I'm able to get to 30x speed ups for fairly deep neural networks on relatively few processors. And we do this with kind of no accuracy loss, really, in terms of test accuracy. So I want to close here, and I will say we are hiring. So if you're interested, feel free to reach out. I'd be really excited to hear about anything you're interested in, if you'd like to work with me or the team at Sandia. The thing I want to kind of point out, maybe the highlight here, is that parallelism is really exposed by permitting inexact propagation. We've done it in these kind of time sequences, these very deep neural networks, but one can imagine other regimes where by doing this constrained optimization approach, you can open up other kind of inexactness that leads the way to parallelism. And so that's really kind of maybe the take-home message I'd like to kind of deliver. If you're interested, here are papers. This SciMod's paper is probably the core one that's focused on layer parallel. That's the one I'd point you to initially. I'd like to thank the DOE Office of Science Early Career Program for this support. And I think with that, I'll close and take any questions. Thank you very much.
Eric, thanks for the nice talk. So any questions to ask? So Bing, you have questions?
Yes.
Sure, please.
Very nice talk. So one question is, when you try to use the reduced layer to do parallelization, I wonder whether you could also explore whether you will actually need that many layers, like in ResNet, whether you can actually get similar performance with also fewer layers.
Yeah, that's a great question. So in fact, I presented this as starting from a very deep neural network and then kind of going down. In terms of the multi-grid cycle, what's really nice to do is to actually do a nested iteration. So you start at the coarse level, and then you can always do the kind of slow kind of growth up, go slowly expand your network. But at any moment, you should be able to stop. And so I think that's actually a nice feature of this algorithm, that it allows you to quickly get to the amount of accuracy you desire, or kind of generalization error that you desire, using a nested iteration where you start at the coarse grid and work your way up to the fine.
Yeah. The other question is, it's great to see the accuracy match. I wonder whether you look at the individual images, whether they also give almost the same level, because you can have average performance the same, but they kind of swapped, and then you have more mileage to average or something.
Yeah, that's actually, I have not looked at that. That's a really good suggestion. Yeah, I haven't looked at that. That's a good idea. Thank you.
Great, thanks.
Yeah, okay. Any other questions? Okay. Okay, so if not, let me make a small announcement. So Jianfen Lu asked me to make an announcement on computational mathematics workshop that's gonna happen on August 17. So I put on the chat so you will be able to see a link there. So yeah, if you're interested, you can attend that workshop. The Zoom link is posted there on the link as well. Okay, so now we're gonna close this morning session. We're gonna restart at 1:30 p.m. East time. Yeah, thank you. See you in the afternoon. Bye.
Eric.
Yes.
So do you talk to people at Livermore? So I'm kind of starting a project with UCSF and also UW, try to do some MRI imaging calibration. And I know people at Livermore are engaged. So we haven't really started, but I would think that we might end up using some of the deep learning for, because eventually the MRI is about data analysis. And I would like to think to have the calibration also take into account what we're going to do with it.
Mm-hmm.
Do you talk to people in Livermore?
Yeah, so I work with a few different people. Stephanie Gunther is the Fernbach. So I work with her. Jacob Schroeder was actually at Livermore prior. And Rob Falgu, who is in the computational, the CASC group, is the kind of multi-grid in time core developer. It's kind of his algorithm in a sense. And so I talk a lot with those people. There's another group at Livermore that it's possible that you're connected with also that does, they do the L-band, which is Bay Area Neural Network or large scale Bay Area Neural Network library, where they are doing domain decomposition style stuff. So like in the MRI context, I assume that these are these 3D images that you're looking at?
I would think so. Right now, it's only using probably in the beginning Phantom to calibrate, but I think I like to carry us through to the next stage, right? Because I don't think that standard calibration might work for all tasks.
Yeah.
So it'll be good to. So maybe I'll just ping you when we start, in case you know people.
Yeah. No, I can connect you with people in Livermore, and we're also talking with people in New Mexico that do. Well, we do a lot of CT scan stuff.
Okay.
So they,
is there
like,
there must be a calibration problem there too, right?
That's right. So there's like an image segmentation where you're trying to determine like materials and stuff like that. So we do a lot of that kind of work. And so we've been looking at UNets or VNets for that kind of work. So we want to label image like pixels basically with their material.
I see.
And so that's work that we do. And those problems are really because of the size of these CT scans, like in the way the VNet architecture works, they are basically intractable on a GPU. You need many hundreds of GPUs just to store the memory requirements for training these things for one image. Which is so we've been kind of doing a lot of work there, which I didn't present, on kind of domain decomposition ideas for that.
So back to the details. So you have turn this forward equations into constraints. Do you have to tune the threshold for the constraint to satisfy, or is that? So
the actual error itself is introduced kind of as part of the algorithm. So what happens is that when you decide to do this multigrid, you've kind of created the error already. And what you can do is you converge that multigrid. So that would be the moment when you actually tune the errors, you would have a tolerance that you would have to achieve on those constraints. In practice, we've just been doing 2 iterations of this multigrid cycle, and that's been sufficient.
Okay.
And so that is a question I think is a really interesting question, in that you know, we have error, but we're not really doing the exact gradient. We're not really doing the exact evaluation, and we're still kind of making progress to the objective function.
Yeah, because it makes a lot of sense. It's because there's a lot of noise in the data, and you don't need exact. That's why stochastic gradient design works. And you kind of I'm curious to see if you compare the paths, right? You're based on a different path. There's just different paths, and so especially curious to see whether you actually end up with, for individual or image, you have the same labeling. Actually, if you don't, that's a good thing, because then you basically achieve the same accuracy with a different path than the stochastic gradient.
Yes.
And then that give you advantage, maybe combine the two.
Oh, cool. Yeah.
So I was talking to some security, internet security people, and then the first idea I think we had was like, because the deep learning is very easy to attack, right, with adversarial attacks. And one idea is that if you build 100 different wave, like a deep learning, and they're all kind of different, you random select them to encode, then it's harder to attack. And then they told us that actually the different ways of training it always end up with almost an individual level, just say like the weight level, the surface level, that were too similar. And I feel like it's the space so huge, why we end up with something so similar, right? You should find very different configurations and have the same result. So I think if you can get out, I think there might be also some good security in terms of when you have very different things, and you can take advantage of some ensemble.
Yeah. Okay. That's a really, I'd not heard that ever. So thank you.
Yeah. So I think it would be interesting. Yeah, keep me posted. I'm curious, because I have been puzzled about how we kind of, everything's similar, but then different, but then become same. And I find it very hard to believe. It's a huge space, and it must be the type of algorithms we train with.
Yeah. You're exactly right about the path being different. This is, kind of a saving, like I showed kind of good, fine parallel speedups, but I think we can do much better because of this path question. We take very slow paths through control space, but in fact, if you couple the forward and backward problem more directly, you can take bigger. Hopefully we can take faster steps or bigger steps through control space. But these parallel and time algorithms are kind of ideally suited for that case, because you can now solve the forward and adjoint problem together, or a forward and back problem together. Yeah. So,
I think in theory, you also don't have to set the threshold for all your constraints the same. You kind of, there's a lot of variations you can do. And I think in terms of, diverse paths, it's actually good, because that gives us some, I feel like it's better. I'll send you something. It's like, I really like this stability idea that we have in this framework. And then I think it's very sensible common sense for many different problems. It's really introduce perturbation and then build stability on top of that.
Okay, cool. Yeah.
But in terms of random forest, you might have heard, it's really taking advantage of that.
Huh. Okay.
It's a decision tree build. It works really well for genomic problems. That's another line of research in my group for discovering driving genetic factors and things like that. Huh. And yeah. So we also try to connect with random forest. And when the time comes, we want to scale up, I might contact you and to see. Because we have very limited, right? At the university setting, it's just a small cluster.
Sure. Yeah. Oh, absolutely. I'd be interested to see. I'm not so familiar with random forests, so.
Yeah, we try to build some connection there, actually.
Okay.
Yeah. Keep me posted if you find the paths, how different or similar they are.
Yeah, I will. That was a really great idea. Thank you.
Yeah, so my email is pretty easy. Just beame@berkeley.edu, or you can just Google me. I think it's pretty, it's easy to find people in universities.
Yeah. Okay. Well, thank you very much.
Well, very nice talk. So I will take a break and come back after lunch. Oh, my.
Yeah. Brunch for you. Yeah.
Yes. So I think Shuhao also raised hands. Maybe, I don't know, he's still there. Shuhao,
I have a quick question.
Sure.
Have you tried this multi-grid like acceleration for transformers, assuming it already has a nice parallel structure?
Yeah. No. This is something I would love to do, actually.
Oh, really? Nice.
Yeah.
So are there any experts of transformers like BERT, or even bigger, like or performer, random feature attention? No. Anyone tried?
No, not to my knowledge. This is something I would really love to do. We just haven't had the bandwidth to do so, and no expertise as well. Yeah. So as soon as I mean, those things are beautiful because they're taking all this data in at once, right? But that's a really expensive operation for any large data set. So yeah, I'd be really excited to work on that topic. If it's something you're interested in, let me know.
Yeah, I will give a small a presentation about my recent research on transformers.
Okay.
So if you're interested, I mean, this evening.
Okay. What time is that?
I think the first talk in the evening, I think it's 7. It started at 7. So you're Mountain Time or something?
Yeah.
So you -2.
Yeah.
So you're 5.
Okay. Great.
No worry. Yeah. So
no, that's really exciting.
Because a transformer is really hard to train because of its size, and you have to tweak the optimizer, like using some warm-up scheduler, and then you have to do some annealing as well.
Okay.
So, and because it has this natural hierarchical structure of because some people at DeepMind, they use this I think it's Google AI, they call it some sort of performer. So it's using hierarchical this cosine sine basis to build the feature space of transformers. But anyway, so nice talk.
Yeah, this is the temporal encoding or something like that. This is the sine cosine thing that you're talking about.
It's not just encoding. It's so the first transformer uses that encoding, but later they use cosine sine, these orthogonal bases to orthogonalize the latent representation, so that they can get a better condition number on the tension matrices to get to reduce the computational complexity of it. Yeah.
Okay.
Cool. Yeah.
Well, great. Well, thank you. Thank you.
Hi, Anima. Welcome.
Great, thank you.
It's good to see you. We have just a couple minutes. Would you mind sharing your screen? Let's see, are you?
Yes, I'm
Yes.
gonna do that now.
You
There.
might have to- there you go. Okay, good. Yep, looks good.
Great.
And let's see. Just want to make sure. Okay, and Lexing is here too, so he's after you. Great. I'm really glad you could join us today.
My pleasure. Thanks for having me. And yeah, I think, all these areas coming together is such an exciting time.
Yeah, it's been a really nice mix of some very mathematical things, some more applied things, and I think it's been a really good conference.
That's great. Yeah. And hope, one day we can meet in person.
Definitely, although it does make it easier to meet lots of new people from around the world even.
That's right. So where are you right now?
At Purdue, Indiana.
Okay. Got it. Yeah, because, people are.
No, for sure. Yeah.
Yeah, so yeah, I guess that's one nice flexibility that, you can spend some time elsewhere.
Yeah. And actually, I do a lot of work with Charlie Bowman. His daughter is Katie.
Yeah, of course. Yeah. I was just catching up with Katie yesterday, and it's great. We are so lucky to have her here.
Yeah. I think she likes it a lot there. Maybe not so much the housing market, but.
Oh yeah, I know. We talked about it. She found the place, and it's bad. I guess it's bad probably everywhere because people are buying things left and right everywhere, right? So I don't know if it is even there.
Yeah, different scale of prices.
Yeah. Yes. I guess hopefully things will, stabilize in a bit. We have to see.
Yeah, right.
Yeah, but I don't think it's going to go down. It's only always going up.
Yeah, for sure. All right, we'll wait just one more minute for people to rejoin after lunch, and then we'll get started.
Yes. Yeah, with all the different time zones too. So yeah, I appreciate giving a good time for me because some of those are like really early in the morning. I guess that's
No, we try to make our speakers happy.
Yeah, so it's always the right in the West Coast. That's the issue.
Yeah,
we can stay up later in the evening, but yeah.
Good. Okay, well, why don't we get started then? So I'm very happy to welcome Anima Anandkumar, who's the Bren Professor of Computer and Mathematical Sciences at Caltech. She will be talking about AI for science, the convergence of AI, simulation, and HPC. So.
Thank you. Thank you, Greg. It's a pleasure to be here virtually in the workshop. And yeah, I mean, I think all these areas coming together is very exciting for me. For me, coming from the perspective of laying down algorithmic foundations for AI and asking how we can solve some of the hardest scientific problems has been a very exciting, but also a journey where I've learned so much. The domain experts, what they have to offer in terms of all the methods that have been developed over decades. The domain knowledge and the constraints, how to incorporate that into machine learning. And more importantly, for these methods to be ultimately incorporated in real world applications, we would need to design AI that can extrapolate, not just interpolate to a distribution similar to the training data, but make entirely new discoveries, right? Like what we call zero-shot generalization, be able to generalize to new instances that are never seen before and that are out of distribution. I think these are aspects that also challenge us to design better AI, right? Ultimately, if we want to think about any form of highly generalizable AI, that would also be very impactful for the sciences. And so that's where I see a virtuous feedback loop here, that we AI scientists can contribute to all different domains, but also learn from those domains, the challenges, the constraints, and how to incorporate that to design better AI. And that's been my journey over the last few years. And both at Caltech and at NVIDIA, at Caltech, I co-founded the AI for Science with Esong to really build AI into all scientific applications across campus. How do we create this fabric of collaboration and come up with ways to scale up these methods to large-scale data sets, to real-world problems? And if the data is not available, how do we incorporate domain constraints to have meaningful results with machine learning? And on the NVIDIA side, as you will see in this presentation, the HPC aspect of it is something that NVIDIA has had now more than decades of experience in terms of building supercomputers and serving the scientific community. And so now, how do we bring that to the modern age and combine both AI and HPC together? What kind of computations at scale can we enable with high efficiency, and what kind of scientific problems can we solve? And that's where, both my connections to NVIDIA and Caltech have been very helpful in informing these problems and coming up with good engineered solutions for them. So anyway, that's a very quick overview of my intentions here today. And yeah, let's get started. So to me, AI is perhaps the most powerful technological force we've seen in our lifetimes. We've seen the model complexity just explode, right? From the time AlexNet was created to now GPT-3 and beyond. You see this now new form of Moore's law. It's doubling every 2 months if you think about the largest models that are being constructed. And that is really exciting in terms of, HPC community, right, was traditionally focused on scale, and now AI is the new HPC in the sense of the largest models are getting built with AI foundations and ultimately integrating HPC and AI together. And now we are delving into harder problems, whether it's drug discovery, which I will talk about later here, but also like all kinds of embodied AI, right? Like building intelligence into robotics is highly non-trivial because of interactions with the real world, maintaining safety, stability constraints while being agile and dynamic and learning all kinds of new environmental conditions. So lots of hard challenges, but also ways to incorporate that into our AI frameworks has been very exciting. And so given this, I just want to quickly remind everyone that what has resulted in this AI revolution is really the trinity of data, algorithms, and compute infrastructure coming together. Right. So, and now when we are going to the sciences, we also want to ask what kinds of data is available. And there are some scenarios where lots of data is available. For instance, when you think about astronomy, right? We are barely able to manage all the data that is collected in the satellites. Most of it is discarded even before it reaches the Earth. On the other hand, there are settings like protein engineering where the lab experiments are extremely limited. So, we need to be able to adapt to both very large data sets to very small data sets. And then there are domains where we know lots of physical constraints. I'll talk about partial differential equations where, if your entire goal is to only simulate the PDE, the constraints exactly. Right, but then there are complex systems like any biological mechanism where you cannot have a precise model. So then do you impose any kind of imperfect prior knowledge, or is it better to be fully data driven? I think that facet of it, right, again, we need, it's not one size fits all. We need to be able to incorporate all kinds of different constraints. And sometimes when there are none, how to be informed purely by data, especially when the data sets are small. I think this aspect is important to think about. The compute aspect is also getting to be more important. Traditionally, like I mentioned, HPC has been very high precision computing. 64-bit is the standard, but with AI algorithms, we are going to extremely low precision, even as little as in one of our latest papers, we showed you can handle with just 5 bits and get the same accuracy on ImageNet and other big data sets as the full precision models. So if that is the case in standard AI benchmarks, what would the implications be for the sciences? Do we still need very high precision in each part of the pipeline, or can we afford to do low precision? And if it's AI is involved, can we then adapt to low precision frameworks and hence be a lot more efficient? And that's, I think, a big equation that is forming now. And we've seen a lot of good evidence that we can even handle hard scientific problems in low precision with the use of AI. And also the other aspect is on the edge. When we are building now robotics, we are building sensors. We need to ultimately miniaturize it to small devices, expose it to all kinds of environmental conditions, limited battery power. So we can no longer afford to just expect that there will be the cloud, right? So in those kind of applications, how do we design better algorithms? So that's where I think there is just a huge renaissance of developing new AI algorithms because the standard paradigm of supervised learning, what made ImageNet challenge successful was pretty standard supervised learning, right? But going beyond now to unsupervised learning, causal discovery, zero-shot generalization, they require new algorithmic frameworks. And so that's why it's, I always start with this motivating slide of Trinity, because we cannot design one in isolation, right? Where if we are questioning about what algorithm to use, we need to certainly ask what kind of data do we have and what kind of compute infrastructure do we run this on? And all this has to be co-designed. Ultimately, we can envision, right, co-designing all these 3 facets together for specialized applications to get the best efficiency. And that is indeed the connection also with HPC, right? Like I mentioned, there has been continuous improvement in terms of frameworks getting better, but the biggest improvement is really coming from not running the traditional HPC with, say, 64-bit precision, but AI computations in much lower precision. And having this available means we can run, like, say, the largest molecular dynamic simulation like that was done last year, but use AI to accelerate that and be able to make use of the flops efficiently. And I think that's an exciting future in terms of the larger scale. How can we use AI in meaningful ways? And indeed, the recently announced fastest supercomputer will be ALPS with 20 exaflops of AI, right? So it's mind-boggling in terms of the scale we now have compared to just a few years ago. And it's really the use of AI that can now enhance the flops by a huge amount compared to just the traditional HPC. And also, thinking about hardware optimizations, having GPU and CPU being tightly optimized together can give us a lot of benefits in terms of efficiency. So this is on the computational side. Now, if you think about what kinds of challenges are compelling to solve with such supercomputers, right? So indeed, to me, and probably to many of you, the climate change is the challenge of our times, right? And especially over the last year with the pandemic, with all the fires, in California, floods in Texas, everything we've seen, the extreme weather events seem to be accelerating, and we seem to be at the precipice of big climatic changes. And so I think it should have been yesterday when we were already thinking of strong interventions, but now hopefully the global community is further energized to, go through having availability of these good models and then designing interventions. And for that, predicting uncertainty is also important. And what makes this predictions very challenging is the highly multi-scale nature, right? For instance, the CLIMA project here at Caltech looks at multi-scale models. So you have a scale for the clouds. And in fact, there is a further micro scale or a microphysics for precisely modeling precipitation. And ultimately, you want to map it to global measurements taken by the satellites. So all these aspects of first simulating at every scale and then mapping it to the coarser scales makes it expensive and challenging. And to do this at planet scale is a huge feat. And ultimately also giving uncertainty measurements, right? Because you don't just want a deterministic prediction, right? That's meaningless. You have to give calibrated uncertainties. And the CLIMA project here at Caltech has been spearheading all these aspects, and where we feel that AI, one of the places AI can play a role is, for instance, in being able to accelerate solutions to partial differential equations, right? And that was just one example where that is applicable, but so many others. In fact, it's no exaggeration when Steve Strogatz calls the differential equations the most powerful tool humanity has ever created. So, everything from fluid turbulence to material design is incorporated as partial differential equations. And the equations themselves are very usually succinct and easy to express. But what makes it highly challenging to solve is that all these complex equations do not have a closed form analytical solution, right? So you have to do numerical brute force computations and do that also in multi-scale. Like you have to go to the finest scale. So you cannot afford to just take big discretizations, because then you lose information, the high frequency information in those phenomena. And so that's what makes it challenging to do this in traditional methods. And the other aspect is, with these traditional methods, you're redoing all the computations, right? So even if you slightly change your parameter or your initial condition, you have to redo everything from scratch. Whereas the hope is, with machine learning, you learn the underlying structure of the solutions, and hopefully you can generalize to now new conditions, new points in a meaningful way. And so that was our goal, to design machine learning methods that can be way faster compared to traditional methods, but also be as accurate and have guarantees of being able to get good solutions, at least in some scenarios. And that was this interdisciplinary project we started on neural operator. And at Purdue, you have now Kamyar. He's been such a pleasure to work together, first as a student and then as a postdoc with me. And I'm really happy to see him be at Purdue and have a great time there. So, given his initiative and having Andrew Stewart from Applied Math and Kaushik Bhattacharya from Material Sciences, and the students and postdocs together created this interdisciplinary initiative. And I think that I want to quickly emphasize that that was critical to success of this project, because having all these perspectives, having the wealth of knowledge from all of the methods that have been developed over the decades, thinking about these multipole methods or thinking about iterative solvers, right? So all these gave us inspiration to design neural networks, but have these kinds of structures that are informed by traditional methods. And I think that has been critical for us to get good, successful outcomes. Yeah, so in terms of framing this problem, the way we wanted to frame it is one that can, right, in principle, you should be able to treat it as any traditional solver, right? You should be able to give different initial and boundary conditions. Let's say you design a solver for a parametric family like Navier-Stokes for fluid turbulence, and then you give some initial and boundary conditions, you should be able to get the solution. And in order to be able to do that, you need to first train your neural network by giving a whole set of initial and boundary conditions and the corresponding solutions. So this is a data-driven method. And indeed, you may ask, in some situations, I don't have data, right? Because it's so complicated that the traditional solver would be too difficult. So later on, I'm going to talk about using only the physical constraints for training. But for now, let's assume the setting you have such training data. So you have the availability of a whole set of initial and boundary conditions and the corresponding solutions. So if this is the case, it seems trivial, right? I can just put this into a standard neural network, maybe convolutional neural network, or even fully connected network, and hope for the best. Now, why is this not just that trivial? So the reason it's not trivial is what we want in our solvers is really a function-to-function mapping, right? So ultimately, you're mapping initial and boundary conditions over all arbitrary discretizations or even continuous sets to the corresponding outputs, which are the solutions at those points. And whereas traditionally, what we have is really just fixed-sized inputs and outputs, right? So the vocabulary is fixed in language. In image, the resolution is fixed. You assume images of a particular resolution. But this won't work for the case of PDEs because, as I said, you should have the freedom to give any kind of discretization, right? You may, in some application, require your solver to just give you answers in this coarse discretization. In a different downstream task, you need your solution to be available at all kinds of fine discretizations. And even the meshes, you could have all kinds of designs of meshes. So how do we, in principle, formulate a neural network framework that can incorporate all these different scenarios? So you should be able to have one that is invariant to the input being any discretization or any grid. And so that's what led us to thinking of this as an operator learning, because now we are learning an operator that maps, infinite dimensional spaces, right? That's a mapping between infinite dimensional spaces. And so that makes it fundamentally different and a generalization of our standard neural networks. So in order to go about this endeavor, we, go back to the standard neural network. And then we want to ask, how do we extend this from like finite dimensional inputs and outputs to infinite dimensional spaces? And to do that, right, the main principle is you have certain linear operations and then nonlinearity. And composing this gives us universal approximator, right? Because if you just had linear operation, that is not expressive, right? That's just a linear model. And that's what gives the expressive power of neural networks is this composition with nonlinearities like ReLUs or all kinds of nonlinearities. And so the question is, when we are now extending this to infinite dimensional spaces, can we still retain this overall structure? But now this linear operation, can we replace it to handle infinite dimensional spaces? For instance, here for finite dimensional networks, it's just some form of matrix multiplication, right? So like in fully connected networks or, convolution operation, which is also linear. So there you're assuming fixed-sized inputs and doing a linear operation. So now how do we extend this? And to do this, we take inspiration from linear partial differential equations. So when you have linear partial differential equations, we know the solution is in the forms of a Green's function. So this is the diffusion equation, perhaps the classical and the simplest equation, right, of heat diffusion. And there we know the form of the Green's function. And to obtain solution at any point, what you do is you do this convolution or integration over this kernel here, or the Green's function. And so that's how you can express your solution at any point. So given this knowledge, right, if we can now express this layer as this integral operator and then compose it with nonlinearity, what we get is a highly expressive network, right? In fact, we can prove that it is a universal approximator. So just as on the lines of finite dimensional neural networks, we can now prove that any continuous operator can be approximated by a two-layer neural network, or a neural operator, sorry. So, and indeed, in practice, you can have more layers depending on the compositionality you want. But this kind of shows that you can now have an expressive framework to express any general operator using this neural operator framework. But indeed, then the question is, how big will this neural operator be, right? How many parameters will this architecture have for different operators? And that certainly depends, right? So for instance, for popular families like Navier-Stokes, what we do know is that the solution operator lies in a low dimensional space. So meaning you do not need as many parameters to express this. And that's why you can get these kind of results where you can provide bounds on the size of the neural network architecture to express the solution operator of Navier-Stokes. And that's why, right, there is no magic here. I mean, if we are we are capturing operators that map between infinite dimensional spaces. But if the operators themselves are finite dimensional or low dimensional, then we can use a compact neural operator to express it. And that's where we get both the expressivity, but also compact ways to capture the operator. And note that even though the number of parameters will be small, this neural operator will still be resolution and grid invariant, right? So that's the power it has. So you can compactly express the entire solution operator rather than capturing only the solution at a specific discretization or grid. And so now the next question is, how do we actually solve this, right? Because the whole aspect was, we just conceptually said, if you can solve this continuous integral, right, this integral operator, so you somehow learn this kernel and then solve this integration, and if you can do that in each layer here, then you get a universal approximation. But how do we now design practical architectures to solve this integration efficiently? And that's where we tried different variants, right? So natural thing is to use graphs to like nearest neighbors to capture the learning of this kernel. But what we found to be most effective in almost every equation family that we tried is the Fourier transform. And indeed, right, so many traditional solvers also use the Fourier transform, like the pseudospectral solvers. And so that's can be a very important and a good inductive bias for solving this convolution or integral operators. So what we see is with the Fourier transform, just to remind you, the signal processing 101, right, this convolution in the standard domain becomes multiplication in the Fourier domain. So what you're really learning now is this weight matrix, right? So you're learning a weighting in the Fourier domain or the frequency domain of your input signal, and then doing the inverse Fourier transform. And one of the intuitions of why Fourier transform is very powerful here is the availability of this global correlations, right? If you think about just standard convolutional neural networks, the filters are small, so you can only capture local features like edges. And the receptive field over multiple layers, right, will not be that big. And also, you're kind of filtering out, so you're not able to capture the entire domain very effectively. Whereas with the Fourier transform, it's global, right? You're capturing global correlations, both spatiotemporal, correlations. And that's really important in domains like fluid turbulence, because we know there is global dependency. And so that's one of the reasons, people have earlier tried like convolutional neural networks or UNets, and it hasn't been very effective if you want to try and solve the equations from scratch. And so that's kind of the overview here with the Fourier transform, right? So what you're doing is learning this weight matrix that mixes the different Fourier modes here, but we only filter out the low frequency mode. So we only retain a small number of modes, like say 20 modes. But this is okay because we are now composing it with nonlinearity over several layers. So even by retaining only low frequency modes in each layer, because we have the nonlinearity in the end, we can capture all the high frequency components as well. And to make this practical, we also add a bias term, because sometimes the non-periodic boundary and other conditions could be hard to capture with just the Fourier transform. So having this kind of additional path can be helpful here. And that's it, right? That was a simple framework, just to kind of remind you the overall framework before I show these results. What we had is multiple layers of this Fourier transform, right? And learning the weight matrix over that and filtering out the low frequency components, and then having nonlinearity like ReLUs and composing it over several layers. And there's one detail I left out, because we can also first lift our inputs to, say, a higher dimensional space, right? Have more channels, and also project it back to the solution space in the end. And that's, we see to be effective because the lifting kind of makes it easier to learn the solution here. Yeah, so what is the outcome? We've been very excited to see that we are able to solve the Navier-Stokes equation here. And, that too, you can see this pretty turbulent regime here. And the thing that to me is so exciting is we were able to train on extremely low resolution data, right? So this is the this is the spatial, and this is the temporal resolution. And then at test time, we can directly evaluate it for higher resolution outputs. So this is what we call zero-shot super resolution, because we do not need access to high resolution data, right, at training time. So it makes training also extremely cheap and fast. And then we are able to adapt without any additional training at test time for any arbitrary resolution, including much higher resolutions. And I think that's the power of this neural operator. And what we see is also that this method, right, when you train and test on the same resolution is also better than the other methods. I mean, this is just kind of a quick comparison with the other machine learning methods, right? Because the others are not capable of this kind of zero-shot super resolution. You cannot train on one resolution and generalize on other. But just a quick comparison to show even there we are doing better. So we do well at the same resolution, but also generalize to different resolutions with very low errors. And as I said, the important thing is to be able to capture the frequency spectrum, right? And we know there are all these high frequency content in these turbulent fluid flows, and we see that we are able to capture well, especially if we also train with derivative losses, which the Sobolev norm captures. And I think that helps the recovery. And if you recall, the aspect that makes it tractable to capture this high frequency is, we at each step, we are retaining only low frequency modes for stability and regularization, but ultimately with nonlinearity, we are able to have transformations and capture also the high frequency content. And with this, it's now natural to use this as a module in all kinds of problems like inverse problems. I mean, here we did the Bayesian inverse, right, with MCMC and forward sampling to do an apples to apples comparison in terms of speed up. But you can also think about solving the inverse problems directly by differentiating through the neural operator and converging to an initial condition. So these aspects, I think, will be very effective because in so many applications, we have inverse problems, right? Because what you have is an evolved map, something that has spatio-temporally evolved, for instance, and then you want to go back and recover the initial conditions. And so this can be very effective in speeding up those problems. And now, once this tool is available, we've tried it on a variety of domains. So I'll give you quickly some outcomes of this, effort here. And so plasticity is a problem that, Kaushik Bhattacharya and Buri Gedde have worked extensively on. I won't get into the details, but it is a multi-scale problem. And so you have solvers at different scales. And what we did was, instead of throwing out the entire traditional framework, right, which I think for neural operator would be very hard to solve in the first go, and especially, in a single GPU, we cannot fit such a large model, right? So instead, what we did was to only replace the solution operator at the fine scale and keep the traditional solver in the coarse scale. And even with doing that, we get very high accuracy while being 5 orders of magnitude faster. And in this case, we use simple PCA basis, and that was already very powerful. And so this shows, the ability to speed up very effectively many of the traditional simulation packages and have easy ways to plug in our method. So another exciting application is ultrasound, and here, we want to capture both the wavefront and diffraction, in order to kind of capture the, properties of human organs, right? Whether there is a tumor or not. And so we've seen good promise here in being able to capture that with neural operators. So this is an exciting problem in terms of, I talked about climate change in the beginning, right? So one intervention mechanism that has been proposed is whether we can store carbon dioxide underground, right? Capture and store. And this is a complex multi-phase flow problem. And, we've found very promising results in terms of having a combination of UNIT and FNO architecture, right, that kind of captures both the local and the global phenomenon very in an expressive way. We'll soon release this paper, and I think we got 4 orders of magnitude speed up here. And so, as you can see in these range of applications, we see lots of benefits in terms of using this neural operator architecture and still being able to retain the fidelity of traditional solvers. Yeah, so early on, I mentioned that what I covered so far has been this data-driven approach, right? So we have even ignored the equation constraint. We've just said, give me the training data that maps different initial and boundary conditions to solutions, and we'll train the neural operator. But instead, you may also want to incorporate the equations themselves, right? So how do we capture both the constraints in the equations and data together? And in some cases, maybe there is no data available because it's too expensive for the traditional solver to give us this training data. So in that case, can we purely just use the equations and at test time, So that's one aspect during training, right? So the other aspect is at test time. So far we don't have a formal guarantee that this trained neural operator will be able to solve every instance of the problem. But that's where, if we can further optimize the test time. So we have a trained neural operator. Now at test time, we look at a specific equation and then we say, for this initial and boundary condition and this parameters, let us see what the pre-trained model does. And we can further fine tune on the equation laws, right, to obtain the best possible fidelity or accuracy of our solution. And so this kind of just shows that we can further enhance and give now guarantees, right? Because you can then evaluate if the equations are satisfied or not. So you can have then a confidence in terms of how good is this solution. And so that's what the benefits we obtain. We call this PINO because we have both the physics informed and we have the neural operator together. Whereas the standard physics informed neural network is just doing this on a single instance of the problem, right? So it's only doing this at test time, meaning just on a single problem instance, solve it directly. Whereas what we are saying is, if we are now pre-training on a family of PDEs, right, with different initial and boundary conditions, even if we don't have training data, that pre-training will help us capture the structure of solution operator better. And at test time, that fine-tuning will further ensure that we get ultimately a good solution. And so we do see benefits here, both in terms of being able to converge much faster with pre-training, and for more harder problems like a longer time interval, in fact, be able to get to a better solution, a better error compared to just training from scratch, which really means on that problem instance, you're just doing the pin. That is not as effective compared to also having the pre-training. And so we see here very promising solutions, in terms of getting good errors and also being able to generalize from one Reynolds number to another. So having this combination of physical constraints along with data-driven approaches will be very effective in many of the real-world scenarios, because you usually have a combination of both of them. And in some scenarios, if you have no data but only equations, we can also handle that. And vice versa, you don't have any equations, you only have data. So you don't want to, limit it to one set of parametric equations. That is also okay, right? So this is a very flexible framework. Yeah, so far what I showed was the framework of trying to predict, a trajectory, whether it's in terms of velocity or vorticity. You see here, our goal has always been to spatiotemporally predict the solution, over a period of time. But ultimately, we do not expect this to keep tracking the trajectory forever, right? Because what we have in these systems is a chaotic system. Right, so there's a lot of classical theory that's known about this. It's called the butterfly effect as well, right? So you make small changes here, the trajectory completely diverges, right? So there's no hope of predicting the exact trajectory over a long time period. So if that is the case, what can we hope to predict? And that's where in this latest work, what we said was, in most of these systems that are of popular interest, we can expect that there are attractors, right? In some cases that is formally proved, in other cases there are strong conjectures about attractors, whether it's a single attractor or a finite set of attractors. So given this is known, the idea is, over a long period of time, our predicted trajectory will ultimately diverge from the ground truth. But if we can preserve those statistical properties, right? If we can preserve the same orbits or attractors, then we have captured everything about the system, right? Then we can claim we can accurately simulate the system. And that's the best thing we can hope for in chaotic systems. And this, is very different from traditional temporal predictions. If you think about recurrent neural networks or LSTMs, the goal is always to try and fit the entire trajectory, right? It could be a very long trajectory. You try hard to fit and drive down the error of prediction. But we know this inevitably will fail. You'll have your recurrent neural network having exploding or collapsing gradients, because this is inherently unpredictable. So you should not be training this on long time periods. And so that's a basic philosophical observation we made here, that you should really be only trying to train on local or small time step transitions, right? So what we call a Markov operator. So it's only like looking at the transition of the current time period to the next. By the way, all these dynamical systems that, like the KS equation, right, or this Navier-Stokes are all Markov systems, right? They are fully observed Markov systems. So we know if that is the case, the future evolution is only based on the transition operator or Markov operator in a small time step. If you have that, you can just integrate it over the time, and that's how you obtain your long-term behavior. So given that is the case, our goal is then to learn the operator, this transition operator, using neural operator framework. And then at test time, all we do is just compose it many times, right? So we are never training on a long trajectory. We only train to capture local evolution, right, on a small time step. And then we just zero shot compose it to give us predictions over a long time, and that'll give us statistical properties about attractors and many other properties. And so what we see here is fascinating, right? As I said, over a long time period, it is indeed impossible to capture the entire trajectory. But an interesting observation is that, like standard frameworks like LSTM or GRU, all these that train on a longer time step, right, actually capture the trajectory worse compared to our neural operator that is only trained on small time steps and then just composed directly to get the predictions over the longer time period. So which is fascinating, right? Because this is not the loss on which the neural operator is trained, but still, because it's effectively able to capture this local evolution, it can compose it in a good way and still try to keep track of the trajectory better than these models where you're trying to train on a longer trajectory, but because it's hard to learn, it fails to generalize well and track these trajectories well. And so what we see then is, we then looked at for these local, right, operators, can we, for capturing the local evolution, can we use other frameworks like UNet in addition to the neural operator? And what we see is we're able to capture the spectrum better compared to the UNets. And, so I think the spectrum is the most obvious one. And that's kind of intuitive, right? We are much better at capturing high frequency content because the neural operator is resolution invariant. And so that property we can benefit from in also capturing the statistical invariant properties or the invariant statistics of all these chaotic systems. And what we see is, also just kind of an intuitive plot here that, this we can capture the attractors well, because the idea here is this, right, lower dissipation, like this is kind of the movement along the attractor, right? That's kind of the idea. So we are able to capture the phenomenon of the underlying chaotic system well by using the neural operator to capture the Markovian evolution. Yeah, so, so I think those are some of the main aspects I wanted to cover. And just a quick comment here that, there's a close connection with transformers. which people may not realize. I won't get into the details here, but this attention mechanism is very expensive in transformers, and you can replace the kernel with Fourier transform and get similar architectures to these neural operators. And in fact, we can prove that in the general framework of neural operator, transformer is a special case. And so we can get kind of these other architectures that are very similar to the neural operator, where there's been promise also on standard image benchmarks. So I think there are some nice connections. So this is not just limited to PDEs, but a much more general framework. Just a quick comment on, at NVIDIA, we have SimNet as a way to build these methods at scale. At the moment, we have the PIN implementation, and we are adding the neural operators into it, and being able to, do all kinds of aspects, such as the forward inverse and the data simulations at scale, and being able to, have support for, say, mixed precision, right, multi-GPU. So really enabling you to tackle practical problems at scale here. Yeah, so really the takeaway I have here is this notion of learning the operator is a generalization of standard neural networks from mapping between finite dimensional spaces to now infinite dimensional spaces. And by building a foundation of using integral operators, right, this convolution with a kernel as the linear operator, and then composing with nonlinearity helps us come up with a universal approximation framework for any operator. But we also see it's very practical because we can use the Fourier transform. It's a great inductive bias for many of these families. It can capture the global correlations well, and at the same time be much faster than traditional methods. So I hope I gave you an overview and also so many exciting applications. Really looking forward to your thoughts and any questions you might have.
Great, well, thanks very much. We might have time for a quick question or two. Anyone have a question? Well, I'm going to jump in while I can. So you have these one time, you're kind of learning this small time steps and using that in a chaotic system and using that to identify the long-term statistics. Do you have a sense in which, how do the statistics, the accuracy of the statistics depend on the accuracy of your approximation to a single time step? This is kind of a big jump from one to the other scale.
Precisely, right? And that precise characterization we are trying to work through, and that indeed, depends on the particular family as well. It's not clear if we can theoretically show those bounds, but in practice, what we do see is as the error goes down in approximating the local evolution, we also get better approximation of the longer time behavior. But I agree, like kind of making that precise seems challenging.
Yeah, right. Okay. Okay, I think we better move on in the interest of time, but thank you very much for a really great talk.
Thank you.
Lexing, can you share your screen?
Yeah, sure. Okay. Can you see my screen?
Yep, looks good.
Okay, let me just do, I think then just restart again. Okay, you can see it, right?
Yep.
Yeah, good. Okay, great.
Okay, I'm happy to welcome Lexing Ying, Professor of Mathematics at Stanford, who will speak on Sobolev regularization of stochastic gradient descent for neural networks.
Okay, great. Yeah, thank you very much. So I would like to thank all the organizers of this wonderful workshop. So I've been listening to some of the talks yesterday and also this morning and until now. And it's really exciting to see so many people from different areas coming together. Okay, so today what I'm going to do is I'm going to talk about some recent work that I did with Chao Ma, who's also at the Stanford University. And the title of this work is a sublevel regularization of SGD for neural networks. Okay, so yeah, so this talk is only about one single paper. So at certain places it might get a little bit technical. So if some things are confusing, and please do let me know, and feel free to interrupt me. Okay. So in this talk we care about neural network and SGD. Okay, so we're mainly concerned with multi-layer neural network and optimized and trained with stochastic gradient descent. So the network that we care about is of this very simple feed-forward form. So X is going to be our input data, and the W is the collection of all the weights of the neural network. And so the feed-forward neural network, what it does is that it takes X, multiply with the matrix W1, and then go through this, send it through the activation function, multiply with W2, and activation function again, and so on and so forth. And here you see the network has L+1 layers. Now, one of the key questions in neural network research and also in SGD is, why does SGD generalize? Well, okay, so this is not one of the million-dollar questions, but I guess, I mean, in post-academia and industry, I mean, millions and millions, even, I mean, hundreds of millions of dollars have been invested into answering this question. Okay, so this is also sometimes called the implicit regularization of SGD. Now, so, I mean, one folklore explanation to answer this question is that, one explanation is that SGD tends to find a flat minimal, and flat minimal generalize well. Okay, so this is, you probably hear this a lot. But if you think about for a second, this doesn't really answer the question. It really just turned one question into two different questions, right? You can ask, the first question is that, why does SGD find a flat minimal, right? And the second question is that, why flat minimal generalize better? Okay, these are all both valid questions. Now, so as mathematicians, I think to fully answer these questions, we should probably make the statement a little bit more precise. And one way to make it more precise is to say that, what do we mean precisely by flat minimal, and what do we mean by good generalization? So we feel like one definition for flat minimal is the following: is that at the W star, which is the weights defined by the SGD, the flatness could be characterized by the following quantity, which is the gradient of my model function f with respect to the weight W should be small. Okay, that's what we mean by flat. And also, good generalization means that the gradient with respect to x is small. Okay, so at least at this level, we have a more precise definition about what we mean by saying that SGD generalize well. Now, but that doesn't really fully help, right? Because they just change these two questions into slightly more precise form. The first question becomes, why does SGD finds a solution W star such that the gradient with respect to W is small? And the second, why small derivatives in W implies small derivative in X? Okay, so in this talk, we're trying to answer these two questions. And the short answer for the first question is that if your SGD finds a solution and the solution itself is stable, and then stability implies flatness. Okay, so in some sense, as long as you have a stable solution and you get a flatness for free. And second is that to answer the second question, to transfer from the smallness of the W derivative to the smallness of the X derivative, we need to exploit not only flatness and also the multiplicative structure of the neural network. And by putting these two things together, we can transfer the bounds of W derivative to the bounds to the X derivative. Okay, so this is the main message of this whole talk. And for the rest of the talk, I'll just try to explain those things in detail. So I think at this point, maybe I would like to ask the audience, are there any questions at this point?
Looks good to me.
Okay, good. All right, so let's continue. Okay, so typically when we write a paper, we follow a linear flow, right? We answer question 1 and answer question 2. But the way we actually, Chao and Ma, which actually approaches the problem, we are doing it backwards. So we start from 2 and then go back to try to explain, start from the end and try to see what condition we need to add. So therefore, in this talk, I'll follow the same thing. So what I'm going to do is I'm going to start with part 2 and try to answer why flatness and also the multiplicative structure together will allow you to transfer the bound from W derivative to the X derivative. And then after that, I will explain why stability implies flatness. Okay. All right. So first, what do I mean by multiplicative structure? the multiplicative structure is really just the feed-forward neural network structure that I wrote down in the first slide. So in the feed-forward neural network, with the input x, the first you're going to multiply with W1, and then for the product, you feed through this activation function, and so on and so forth, right? So for notation convenience, it's useful to introduce these hidden variables h1, h2, and all the so on and so forth. So therefore, this feed-forward neural network can be written as a bunch of equations. So the hidden layer h1 is going to be the activation function applied to w1x, and so on and so forth. So one useful thing about this hierarchy, this multiplicative structure, layer structure, is that it allows you to take the gradient very easily, right? So this is just the famous backpropagation rule. So for example, if you want to calculate what's the gradient of this function with respect to W1, you can apply this chain rule, and you'll see that this is the formula, right? It's a derivative with respect to all the hidden layers, and finally, and for the hidden layer, you take the last hidden layer, you take the first hidden layer, the H1, you take derivative with respect to W1. And now, and also, and the derivative with respect to the input data X can also be written in a very nice way, okay? But the important thing to realize is that these two parentheses, formulas in the parentheses are exactly the same because of this multiplicative structure between W1 and X. So this is one of the key things we're going to use. Now, let's see why this multiplicative structure allows us to transfer the bound on W to X. So let's take a look at what is the gradient of X, of F. Well, it's equal to the product of these two pieces. And so therefore, and this is a, so therefore there's a vector, its 2 norm is bounded by the matrix 2 norm of W1 and times the matrix, the vector 2 norm here. Now, the second step is trivial. We're going to divide by the norm of X and multiply by the norm of X again. So this quantity we're going to keep. And let's take a look at this product of these two quantities. Now, if you take a look at the first formula here, so on the left-hand side, you have a matrix. On the right-hand side, you have the product of the two vectors. You have the outer product of the two vectors. So therefore, the L2 norm of the matrix on the left-hand side has to be equal to the product of the norm of the two vectors on the right-hand side. So therefore, the product of these two vectors exactly give you the 2 norm of this gradient of W1F2 respect to the 2 norm. Okay. So once we have this, so you see that as long as this quantity W1 norm over the X norm is bounded, and then we can transfer any bound on W to the bound on X. So that's what we mean by a multiplicative structure allows to transfer the W bound to the X bound. Okay. Now let's make it slightly more precise. And so our model function F, we denote it by X and W, and where W contains all the parameters. Because of this multiplicative structure, we can write the W1 with X together and then group the rest of the W's into the second parameter, okay? And denote this function by F tilde. So our data is given in terms of Xi and Yi's, where Xi is the points in D-dimensional space, and the Yi are the scalars, and the whole W, when we vectorize it, and it can be viewed as a vector in the W-dimensional space, where W lowercase w corresponds to how many parameters we have in the system. In this talk, we're mostly going to focus on the loss function, which is given by this quadratic loss. And we believe that our work can be extended to other loss functions as well, but for the time being, let's just restrict to the simple case. We also assume that the solution that we care about, the W star, the optimal parameter, is a zero loss interpolating solution. So, and this has been observed in many numerical results and in the literature. And as long as you have the large number of parameters in the neural network, often you can interpolate the data. So this is a reasonable assumption. So the key quantity that we care about is we're going to use is something called a flatness. And I believe that this has appeared in several places. And essentially the flatness is a trace of the Hessian of the empirical loss function at a point parameter W. Okay, it's a sum of the eigenvalues at the Hessian of this point. Now the good thing about this flatness is that if you look at the flatness at your interpolating solution W star, then if you write down what does this mean, and by applying the simple calculus, you see that this is equal to this formula. But the beautiful thing is that if my solution W star is interpolating, and this term is going to be equal to 0, so the second term is going to drop out. So therefore, the flatness at W star is exactly equal to the derivative bound in terms of W at the W star, and the summing over all these training points. Okay. Now, once we have the definition of the W star, well, we can go back to the previous slide. Previous slide give you the derivative in X at an arbitrary point X, right? now what we can do is that we can sum this over our training point xi's, and by taking sum and also take the mean over all the xi's, we get this formula. So therefore, what this formula says is the following, is that if we take the average version of our x derivative at our training point, this will be bounded by this factor multiplied by the flatness. And in order for this factor to be manageable, we need the neural network weights at the first layer to be not too big. And also we need the neural network input to be not too small. Okay. So neural network input not to be too small is a condition very easy to satisfy, because you just need to normalize your input, right? This is being commonly done in most of the neural network training. And W1 small, there is some theory in the literature arguing that W1 cannot be too large, especially you have this ReLU activation function. But in some other cases, you just have to just verify once you get to train the neural network, you have to check that W1 is not too large. Okay. Now, here, just putting everything we said into a more precise theorem form, is that on the left-hand side, what you have the gradient at all the training point xi's at your interpolating solution W star. Now, on the right-hand side, you have this quantity, which I just talked about, multiplied by the square root of the flatness. So I want to make two remarks here. The first is that the left-hand side itself is only at this point, only at the training point. Okay, so it's a derivative at the training point. Why? Because only the training point appear in the training of the neural network. So therefore, it's natural that we bound the derivative at the training point at this point. And the second thing I want to emphasize is that so far, I only about this care about the 2 norm of these quantities. But the whole proof can also be extended into the P norm, LP norm. So for example, in the case where P is equal to 2K, so by changing the proof a little bit, we can actually get this formed. Okay, this estimate. So on the left-hand side, you have this L2K kind of norm of the gradient at the training point. On the right-hand side here, you have the 2K version of the flatness. Okay. All right. Any questions? Okay. So before we use the theorem and move on, let's just take a look at, whether this is true numerically or not, right? So it's always good to have a numerical verification. So here we introduce 2 quantities, GW and GX. So here GW is the norm gradient in W, and the GX is a gradient in X of our model function. Now, on the left-hand side, we have the example, which is a fully connected neural network trained on the Fashion Minutes data set. Okay, and on the right-hand side, it's actually a convolution neural network. Okay, so it's our work can also be extended to the convolution setting. So this is in the convolution neural network trained on CIFAR-10. Okay, on the left-hand side, you can see that the different dots are different color coded, and so it's corresponding to different learning rate. Okay, so here we choose a mini batch size roughly around 20, and the learning rate goes from 0.05 all the way to 0.5. And you see that here there's a beautiful linear relationship between the x derivative and also the w derivative. So this is essentially is numerical evidence that our result is true. And in fact, that the theorem is true, but this is numerical evidence to see this is actually working. And on the right hand side, we have different batch size. Okay, so the batch size go from 10 all the way to 50, and we also see that GX and GW more or less follow a linear curve. Now, before I move on, it's also, it's good. I think this picture is very useful. It's giving you about what is the main idea of what we have discussed so far, just in the 1D case. Now, consider the case where the input data X is 1D and also W is 1D. So because our neural network FW star X, XW, sorry, is actually can be written as F tilde of X times W and the product of it with some extra parameters. So therefore, it only depends on the product of XW. Here W essentially should be W1. So the first layer W star. So it only depends on the product of W1 and X star. So therefore, what it tells us is that the function F itself is actually going to be a function of the level set, these green curves, right? Now, if you take a look at our theorem says that our theorem works well when W star is not too large and also X is not too small. So therefore, we don't want to, this is the bad regime, right? This is the regime where our theorem is not very useful, okay? So we're gonna consider to the left of this, to the good regime. So which is the theorem essentially says that in the good regime, if your function f is smooth in W, it has to be smooth in X as well. And this can be seen very easily on this picture because of this level set structure, right? If I have a function which is only wiggle smoothly in the W direction, for example, as I have on the left-hand side, and because of this, it's a function which defines our level set, and the level set is not to squeeze too much in the X direction here, so it has to be very smooth in the X direction. Now this picture gonna break down when we go back to the bad regime, right? Because in the bad regime, it could also be that the dependence on W is very flat, but the dependence on X is very rough. Okay, so but as long as we move away from the bad regime, and we're in good shape. Okay, this is what the theorem says. Okay, so these the numerical example and also the picture is just trying to give more intuition about what's going on here. Now, one thing I mentioned in the remark earlier about the theorem is that so far the theorem is only valid at the training point xi. But in order to really to show generalization, what we need is that we need the value of the gradient of x away from the training point, slightly away from the training point. So in order to do that, we introduce this this definition, this condition called the C delta K. This is a technical condition. But what essentially says is the following: is that if you take a look at the gradient of, so if you take a look at the gradient of W at the point W prime, which is not too far away from the W, okay. And then the gradient in W shouldn't change. I mean, in fact, it cannot go to infinity, right? It should be roughly bounded by a constant plus the gradient at W. So I allow the gradient to change rapidly, but I mean, I wouldn't allow the gradient to suddenly go to infinity. Right? This is essentially impose some kind of like a regular condition on landscaping W, and it's very benign. So we believe that this is a reasonable assumption to make. So under this assumption, we can then transfer these. The following theorem allows us to transfer the bound on the x derivative at the grid points. At the training point xi to in a neighborhood of the training points. So here, what we do is that we introduce this set called x delta. So x delta is the union of the small ball delta radius balls around all the training body xi. And as long as my neural network is satisfy this technical condition at my W star, this is my the solution find by SGD, and then the derivative.
Mixing. I thought, yeah, I wasn't sure if it was me or if we just lost him. It looks like maybe we lost him.
Hello?
Oh, there you are.
Hi, Greg.
Yeah, we lost your feed for a minute.
Oh, okay. Sorry, I really apologize for that. Yes, let me start. Okay.
It's always hard to know because I couldn't tell if my internet was out or if yours was out or what.
Can you see my screen now?
Yep, it's coming up.
It's coming up. Okay, great.
Now we can
sorry,
see your
yeah. Okay, but so what did you lose me? Is this on this slide or?
Yeah, it was on this slide.
Okay, so yeah, the point on this slide is that by using this technical condition, I can transform the bound on the derivative in x from the grid from the testing point xi to the neighborhood of xi. Okay. Right. Let me briefly summarize what we learned from this part 2, which appeared first. Is that first the multiplicative structure of this neural network induce a connection between these landscaping x and the landscaping w. So if we have the gradient bounding w, we also have a gradient bounding x. And also the soft left norm, semi-norm, that essentially the gradient in w can be in x can be extended to be a neighborhood around the training data set as long as we have this technical condition. And finally, that most of the theorem that when I introduce it, in terms of the true norm, but it can also be extended to the LP norm for P much larger. Okay, we're going to use that later. So now let's move to the part 1, which appears second. Okay, why does SGD finds a flat minimum? Okay, so the short answer is that if SGD finds a solution, the solution is stable, and the stability implies flatness. Okay, so now what stability for SGD and the gradient descent mean different things, right? Okay, so I think this has appeared several times in the literature. And so if you take a look at the gradient descent, let's consider a simple model function where the fx is just equal to ax squared. Now, if the learning rate eta is less than 1/2a, where a is this curvature and this constant in front of x squared, and then the gradient descent will nicely converge to the origin, which is the optimal solution. And in fact, it doesn't need to be less than 1/2a, but if eta is less than 1/a, then it will still converge, but the solution will oscillate a little bit. Okay. But on the other hand, if eta is greater than 1/a, and then the solution is going to blow up, right? Because this is the stability of the numerical methods for solving ODEs. So 1/a is a clean threshold for GD to converge in this case. But for SGD, things are slightly more complicated. The reason is that in the case of SGD, the fx function, the nice ax squared function, is usually a sum of multiple components or average of multiple components. It could be f1, f2, or it could be many. So let's just consider 2 cases. In the first case, when f1, f2 are really close to this f. So in this case, roughly, as long as eta less than 1/a, will still converge because f1, f2 are similar to f, and no matter whether you choose f1 or f2, that will give you very similar gradient. But on the other hand, if f1, f2 are very different, so in this case, f1 is very sharp, f2 is very flat, and in fact, that choosing eta less than 1/a typically will give you divergence. Because whenever you choose f1 and this become unstable value, so therefore the solution is going to blow up to infinity. Okay, so which means that SGD, as long as you have as long as you have drastically different curvatures for different components, and then this imposes some condition on the maximum learning rate you can choose. Put it in the other way, that if, for example, your SGD converges for a certain learning rate, and then that also imposes how sharp your different components can be. Okay. Now, so let's study the SGD dynamics. So this is the typically simplest SGD mini-batch training algorithm. So where eta is the learning rate and B is mini-batch size. And here we use like a CIT to denote different components, different testing data you're choosing a certain mini-batch. Now, so in order to study the stability, what we do is that we can take a look at the linear dynamics around the final W star, the solution, the optimal solution. So if you write down the linear dynamics, and this is what you get, it's just really a linear equation, but the operator here itself could be random because we're using mini-batch. Okay. Now in the remaining of the discussion, we're going to assume that W star is equal to 0. So therefore, it's really just simply a linear equation that we need to consider. Now, we define the linear stability as follows, that if the interpolated solution W star is case order linear stable for SGD with a certain learning rate eta and mini-batch size B, if the following condition true. What this condition essentially says is that if you take a look at the different case order moments of my weight vector W, and they will be bounded, okay, independent of time. So here the constant C could be depend on K. So this is essentially this is a very reasonable definition. It just said that the case order moments of my random W weight has to be bounded. Now, once by using the definition, we can try to write down what is the expectation of that. Well, the expectation of this is just the expectation over a mini-batch of this multiplier and tensor with itself K times. And we denote this operator to be Tk. And so therefore the recurrence relationship of the expectation is just simply the left-hand side is equal to the T operator multiply the expectation of the previous step. Now, therefore, the result of linear ODE essentially tells us is that in order for the W star to be K order linearly stable for SGD, if and only if the operator norm of this T is to be bounded by 1, i.e. that if you apply T to any initial condition that you want, it has to be bounded by the norm of that initial condition. Now, so here I'm just rewriting this lemma, and now how do we? The next step is to try to transform this lemma to what we want, a bound in the derivative in W. But to do that, all we need to do is that we need to just try some testing vectors. Okay, so the testing vectors we're going to try is just E1, E2, all the way to EW. These are also different canonical vectors in my weight parameters, my neural network weights. And so by applying this, by writing down what exactly the T is, and also just putting and using this norm bounded by one condition, and what we see is that this gives the following bound. We have the following theorem, which is a bound on this normal the weight, the derivative with respect to the W, the neural network weights. And I would like to make one remark here is that on the left-hand side, we have this gradient of this my model function with respect to the W's at all these training points. On the right-hand side, you see that it depends on both B and also eta. Okay, so what is B here? B is the mini batch size, and eta is the learning rate. So as the mini batch size goes to larger and also learning rate goes to smaller, we know that it's easier for the SGD to be stable, right? And so this is also reflecting the theorem, because as B goes to infinity and also eta goes to 0, the right-hand side is going to get larger and larger. So therefore, it imposes a weaker and weaker condition on this gradient of W at my training point. Okay, great. So yeah, the part 2, which I described first, is essentially tells you that the flatness and also this multiplicative structure gives you that allows you to have a bound on the derivative of X derivative. And here essentially tells you that as long as you have the stability, you have a bound in the W derivative. Now what we'll do is that we're going to ready to combine these two parts together. Okay, so we call this the Sobolev regularization effect of SGD. And the reason why we call it Sobolev because we bound the different derivative in X and different derivative in W. So the regularization essentially comes into two parts, part 1 and part 2. So part 2 is what I just described, I first described, and then part 1 is what I just described. And by combining these two theorems that I described earlier, and we get the following theorem. Okay, so this is just, this is just combining these theorems together. It's trivial. So it's because the part 2 tells that we can bound the X derivative by the W derivative, and part 2 says that we can bound the W derivative by this square root of 2B over eta term. Okay. So the estimating the theorem and the way I formulated it is in terms of the L2 K spaces, but we can also have the L infinity estimate, and the only difference is that we have to pick up this extra n factor here. Okay. Now, if you take a look at this bound, and we see that this bound is actually not too bad when it's actually quite useful when K is large. Because typically you would expect that the training data n to be fairly large. But you see here, we have raised it to the power of 1 over 2K. So therefore, this quantity itself can actually be pretty small. So, and on the right-hand side also has this component, which is 2B over eta, take the square root. And so therefore, as long as my mini batch size is not too large and my learning rate is not too small, and this bound is very useful. Okay. Now, finally, we're ready to transfer this what we learned so far into this generalization bound. So here we assume that we have target function, which is called f star, and this target function is the yi is just given by f star xi. Okay, we assume there's no noise at this point. So the generalization error is given by the following: is that suppose the W is a neural network that you find, and this fxw is your model function. You take the difference between the true ground truths, and then evaluate it over the take the expectation over all the possible data sampled from this measurement. Now, by just directly using the previous theorem, so we can show that the following generalization bound. So we have to make a few assumptions, but these are the assumptions which I already alluded to in the discussion so far. So first, that we need the W star to be k-sort linearly stable. And second, that we need this technical condition that to transfer the X derivative bound from the testing points to a neighborhood of it. The third thing, we need to make sure that for any point that we sampled from this data distribution has to be not too far away from, with high probability, not too far away from some of the testing point, training point. And finally, we make some reasonable assumption about the Lipschitz condition, the derivative of the target function. By putting all these things together, we have the following bound for the generalization error. Okay, the remaining two terms are typically small because they depend on eta square epsilon, so with some constant in front of it. So theoretically, you can ignore it. So the biggest contribution actually comes from the first term, and it has an eta square, which is a small term, but it also has some big term, which here is n to the power 2k, and also square root of 2b over eta. Now, in a typical neural network, assume that it's trained with a fixed mini-batch size and also the fixed learning rate, and this become a constant. So therefore, the only big term is this n to the power 2k. So really what we are playing is with these two terms, which is n to the power, let me just, write it down, is n to the power 1 over 2k, and times this delta square, right? And times delta, and then the square. So what essentially we want to make sure is that now if the number of sampling points n is not too large, then for general distribution in high dimensional, this eta itself cannot be too small, because essentially all points are actually far away from each other. You're not really packing the whole space. But if, for example, your data distribution is inherently sampled from some low dimensional manifold or union of low dimensional manifold, or some kind of very tubular or very flat sheets of data, and then this condition makes sense. You really that the delta could be actually decay faster than n to the power 1 over 2k. And this will happen if, for example, if your effective dimension of your data d is of order k. Okay, so that will work. So therefore, the theorem is useful when the theorem is true, but its most useful case is when the data is actually sampled from a low dimensional structure or a union of multiple low dimensional structures. So as an extra bonus, we can also prove an adversarial robustness of our neural network we obtain. The reason is simple, because the reason, so here's the precise bound. We say that suppose we get this our interpolating solution W star, and what we can show is that if you perturb x a little bit by distance delta, and then the model function will only change slightly. So this is one form, and this is multiplied by this term multiplied by delta. And you see that as 2k is large, this term itself could be under control, and as long as the batch size is not too large, learning rate is not too small, this size is also under control. So therefore, this is, you can roughly proportional to delta. Now, I mean, this is obviously a form of adversarial robustness, because what it says is that if x is your training data, if you move your training data a little bit by a certain distance, the response function, the model function itself is only changed slightly. So, if this is true, then adversarial case cannot happen, because adversarial case means that if you change your training data a little bit, you'll get a totally different result. Okay. All right. To summarize, what we talk about today is one explanation about why SGD generalize. So it generalize comes in two ways, from two aspects. The first is that linear stability allows us to show that if you get a stable solution and this gradient W is bounded for the model function. And also the multiplicative structure of the neural network allows to transfer the gradient W to the gradient in X. And finally, if we have a bound of the gradient in X, then this shows that our neural network generalizes well and also is adversarial robust. Now, there are a few questions needs to be answered. So for example, what would happen if my W star is not an interpolated solution? Okay, now, and here we assume that loss function is a quadratic function, but what if my loss function is not quadratic? So we believe that our method, our proof technique can be extended to general general loss functions as long as it's near the minimal, it actually has a quadratic approximation, but this is future work. And finally, more importantly, is that what if the optimization method itself is not SGD? So we see that in the literature, for many neural networks, training with momentum methods, training with Adam, training with Aramis prop will give you much better result in SGD. And so hopefully our method can also be extended to these common optimization scheme. So finally, so here, even though, I mean, the multiplic structure of the neural network appear in all the layers, but in fact, what we use is only use it in the first layer. because for the rest of the layers, we treat it as a black box. So the interesting question will be that if we leverage the multiplex structure in all the layers, can we have a more regularization effect? Can we say more? Okay. So with this, I would like to conclude my talk, and thank you very much for your attention. And then this is a paper and it's archive. And if you have any questions, I'll be happy to answer them. Thank you.
Great. Well, thanks very much. Let's see, Ben.
Okay.
No?
Ben, you have a question?
Yes. Very nice talk.
Hi.
So one question.
Okay, thank you.
Can you extend? You mentioned already. Can you say a bit more about when the solution is not interpolating? Do you think you can push your techniques to get results also for generalization bounds?
Oh, sorry. What do you mean by when the solution is not interpolating?
Yeah, you mentioned. Yeah. Can you extend?
We're working on that, and well, I guess so I don't have too much to say because there are certain terms we have to estimate, but it's not. But yeah, because I don't. Yeah, sorry, I don't have too much to say because I haven't worked out the details.
I see.
Okay. Yeah. Sorry, this is probably not a very satisfactory answer because there's certain terms we assume to be zero. In the interpolating, if the solution is interpolating, but if these things are not zero, we have to find a way to bound them.
Yeah. Can you say a bit how you translated the bound on the derivative of the X into generalization bound? Maybe I missed it.
Oh yeah. Okay, I can say that. Let me. You can still see my window, right? Okay.
Yeah.
Let me just open the slides again. Okay. So. Sorry, my notability. I have to restart it. Okay, so yeah, okay, so the theorem is here, right? So okay, so what we do is that if you take any point X, right? So we want to compare fxw minus f star x, right? So this essentially, if you take the square of this and then you integrate over X, then you have the generalization bounds.
Right.
We just do triangle inequality. We say that this is bounded by fxi w for some training data minus f star xi plus fxw. So you can see it, right? Mm-hmm. Minus fxi w plus f star wi, sorry, f star xi. I apologize. F star xi minus f star x, right? Now, so we choose an xi such that it's close to x. The reason we can do that is because we have the assumption number 3. Okay, but my solution is interpolating, right? So therefore, so there's a w star here. Because my solution is interpolating, so therefore the first term is 0. Now for the second term, this is about the difference of f at the two different x points, x and xi. But because I have the gradient of fx bound, so I can bound that. And for the last term, and this is about my target function, but here I made as an assumption that the gradient of the target function is also bounded. So therefore I can bound all 3 terms.
I see, so triangle inequality, okay.
Yeah, it's just a simple triangle inequality.
And then the smoothness of your the condition, basically the points are pretty.
Exactly. So here I need that for every point in my typically that I can sample from with high probability, I already have a training point which is close by.
Yeah. So they're similar. Yeah. Okay. Makes sense. Thank you.
All right. Yeah. Sure. Thanks.
Xiangpeng.
Hi, Lejin. Very nice. So
thank you.
2 questions. So one is perhaps a bit just clarification. So sometimes you write the gradient of W, right? But I'm not exactly sure whether some of these derivatives are only with respect to the first layer weights or with the full weights.
Oh, we only need to, okay, so good question. So yeah, maybe, okay, so if you take a look at here, so if we wanted the X bound, we only need the derivative in the W1, right?
Mm-hmm.
But if I have the sum over all the possible derivative with respect to all the possible W, that certainly gives an upper bound on the W1. So therefore, So therefore, the inequality in the right direction. So in fact, the flatness is actually give you more than you need.
Mm-hmm. And then for like the linear stability,
yeah.
in the definition, you sort of use the derivatives in all directions. Is that right?
Yes, that's right. Yes.
Okay.
Because I mean, when it's stable, it is stable, right? All the I think all the different components of W should be bounded. So I mean, one can make weak assumptions, but we didn't do that.
And yeah, so one question I have, I mean, the second question I have is that actually in practice, like let's say that we train a neural network and it gives us some weights, how would one actually check whether it's linear stable? I mean, case order linear stable?
Good question. I guess, well, I mean, it's not mathematical proof, but empirically, if your solutions stay around a certain point for a long time and you can empirically estimate what the moments are, and that will give you some confidence whether it's so-called k-stable or not. But I agree with you. I mean, the short answer is that this so far I don't have a criteria to check just simply bounded from the data, because it's possible that you wait for a long time and then suddenly there's a jump which brings you to some places which are far away. And but this condition is only and also about the but once you find the solution, and if you can, once you find the W star, right, interpolating W star, and if you knew the neural network, which you can, if you have the computational power, you can actually calculate all these quantities. And as a posterior, once you find it, that you believe that this is the solution, you can check it. But this is not some work that you can do easily, because these are huge matrices and tensors.
Okay. Yeah. Thanks for clarification.
Yeah, sure.
Other questions?
Yes, I have a question. Sorry.
Yeah, sure. No.
I'm still confused as to why only W1 is needed in this. It seems like intuitively, it seems like you would need sensitivities for all the W's. So there's something really missing.
Well, right, because I mean, one thing, for example, is that W1 is the one that is directly interacting with X, right? So, for example, the neural network is, for example, if you use ReLU, right, the activation function is homogeneous. So then, therefore, what you can do is that for example, for the 10th weight, 11th weight layer, you can actually multiply one by a big factor and multiply the other by the by the reciprocal, and you will not affect the behavior of the neural network too much either, right? So, but by multiplying these one layer by a huge factor and the next layer by a small factor, you will be able to change the gradient f of these two layers dramatically. You can actually make one to be very close to 0 and one to be very close to infinity. So, but that does not affect, for example, the derivative with respect to the input, because they automatically cancels out. So that's why we only need the gradient with respect to W1. We don't need the gradient with respect to the whole W.
And so is this is independent of the activation function, or if you have like a non-ReLU activation, is that?
Yeah, so far it is independent of the activation function.
Okay, thank you.
Yeah, sure.
Other questions? Well, I have just one. So could you do something similar with a Fourier network? I mean, it seems like you'd still have this kind of multiplication structure, but you have these additional Fourier transforms involved.
Yeah. Well, I mean, if you view the Fourier network, I mean, so you can Fourier transform everything, and then, I mean, for example, you can Fourier transform your data input data, right? Then the traditional convolution neural network will become a Fourier network, but you still need to do some kind of like a convolution in the Fourier domain. So I haven't worked that out, but I think, I mean, maybe we can transfer it, but I'm not sure. I haven't done it.
Hi, Joe.
Hi, Joe. You're muted.
Oh, sorry. Can you hear me?
Yeah, I can hear you now.
I would like to ask a very naive question. So, if during the training, if we rescale the parameters in the hidden layers, so that we can keep very small parameters in, for example, W1, does it mean that we can control the generalization error in your boundary to make it very small? If we use that rule, we can rescale that to make the last parameters very large and all the other hidden parameters very small.
Let me see. If you rescale the parameter such that you make the W to be very
W1 can be made very small.
Well, if you make a W1 to be small, you make the W2 to be large, right? You have to, right?
Yeah, we can make all the hidden parameters very small, only the last.
No. You can make the last layer W1 to be very small. That's what you said. And you can, but then you have to make the other ones big, right?
Yeah.
Yeah. Now, so I think that will help you in the part 2 of the analysis, right? It become more and more flat in X, but this will impose danger on the part 1 of the analysis. And then because the solution find you might not be k-linear stable.
I see. So how can we see that point in the linear stability?
See. Let me see. Well, I mean, okay, so if you make a W1 to be very small, I like to use this, for example, use this picture. And so it's kind of like, this is my W, this is X. So you're gonna be here. So therefore, you can make W1 to be small, but then this DF DW1 can be really, really large, right?
Yeah.
So yeah, your DF DW1. Okay, I'm thinking DF DW1 is going to be very large, and then sorry. Okay, so my notability always have problems. It keeps on crashing, so apologize. So if the W1 is going to be very small, the gradient W1 will be large. So therefore, this one will be, you see, let me see. Okay, so it's a good question, but do I have it? No, it's not here. So I think I have to study carefully, but my guess right now is that if you do that, and then your SGD with this learning rate and this mini batch will probably not be stable at such W1s.
I see. Thanks. Yeah. I will think about that later.
Yeah, and also, I mean, the other thing is that you're changing the training algorithm, right? Every step is not just SGD, so therefore you have this readjusted. So therefore, this linear stability has to be redone. So I don't know, I don't have a satisfactory answer, but this will be my guess.
Thanks.
Okay, I think we better stop at this point. So thank you very much for a great talk. We have a break for 10 minutes, and we will start again at 3:20 Eastern time. I'll see you then. John, there you are, John. How are you? Welcome.
Hello.
Thanks for coming today.
Yeah, thank you for having me.
Yeah. Do you want to go ahead and share your screen just to make sure everything's working okay?
Yeah, sounds great. Right. Let's go ahead. You see it?
Yep, we got it.
Okay.
Good. Yep, we'll wait just another minute or so. Make sure everybody's here. All right, well, it's possible my dog is going to start barking in just a couple of minutes, so why don't we get started so we can avoid that. So I'm very happy to welcome John Wright, Professor of Electrical Engineering at Columbia. We'll be speaking about deep networks and the multiple manifold problem. So go ahead.
Okay, great. So recording in progress. Okay, so thank you for the introduction. Thanks to the organizers. It's been a great workshop so far, so it's really great to be here. So I'm going to talk a little bit about some adventures that we've had in the last few years in trying to understand a little bit of how deep networks interact with data with low dimensional structure. So in particular, in this talk, we'll be thinking a lot about manifold structured data. So everything that I'm going to talk about today is joint with some really outstanding folks. Sam Buchanan, Dara Gilboa, Tingran Wang. And these folks are really the main drivers of the work. They have contributed in multiple ways. The first way was really by dragging my research group into this area and dragging their advisor into this area, kicking and screaming. So they really got us all excited about neural networks. And then in the course of developing some of the results that you'll see today, they really did some very heroic technical heavy lifting. And so if you're working on sort of the mathematics of information propagation in deep networks or the effect of random initialization, there's a lot of stuff buried in the papers that I won't get to in this talk that might be more generally useful. So Sam will actually give another talk in the student section where he'll go over a few of those tools and ideas. But anyway, all of the credit for the work really, really goes to these folks. Okay, so deep networks. So as I said, this talk for myself represents a kind of first encounter with the area of deep learning. In that regard, I'm a little bit late to the party. And as I started to encounter this area, as a mathematical engineer, the first question that sort of comes into my mind is, well, what are the model mathematical problems in this area? As we saw yesterday in a few of the talks, I think Ron DeVore laid this out really nicely, that in a lot of areas of engineering and applied mathematics, we really like to think in terms of model problems. And the reason that we like that is that in other application areas, that's been really fruitful, both in terms of generating improved results and in terms of generating insights. So, just an area that I'm personally fond of is this area of sparse approximation. Thinking about signals with low dimensional structure and high dimensional space, and when we can recover them from incomplete, noisy, corrupted observations. And this is an area that was kind of a point of focus for a number of folks in a number of communities for a number of years. And it was really, I think, gratifying to sort of see what people were able to come up with when they got centered around a particularly well-chosen model problem. And the cool thing about this is that, not only did the results get better? We get better bounds, we get faster algorithms, but there are a lot of insights that sort of come through along the way that are sort of generated as byproducts, right? The importance of the structure of the data, right? Low dimensional structure and dictating my resource requirements, how much data do I need? How much compute do I need, right? This all comes back to the structure of the data. At a technical level, the importance of that our operations preserve the structure of the data, this sort of isometry ideas. And that at an even more technical level, how we can use those to guarantee that iterative optimization methods do what we would like them to do. So sort of certificates of optimality. Okay, so we like model problems. And so then the question is, well, what are the mathematical problems, model problems for deep learning? And at least a first impression upon encountering this area is that deep learning writ large is an area that's not really driven by mathematical model problems. There's a lot of really amazing mathematical work that's been going on. We've seen a lot of it in this, in this workshop so far. But a lot of what has really driven the applied progress in this area, over the past 10 years or so, hasn't been mathematical model problems, but rather has been the kind of model problem that you get by focusing on a data set, right? If you think about a data set as a sort of formal model for an engineering problem or for some engineering considerations, and you sort of focus on that world and try to ratchet up the performance, well, performance improves, and we learn a lot along the way. There are a lot of sort of insights that have been gleaned from this kind of step-by-step attempt to ratchet up the classification rate. Examples are the importance of depth, right? Deep networks tend to work better. Some kind of isometry property, right? That it's important that information propagates in a stable way through our network. And then, of course, the canonical example of this is overparameterization, that somehow networks with more parameters than we have data points do a lot better than we might expect based on classical statistical principles. Okay, so, this is an area that, despite a lot of really outstanding and really inspiring theoretical work, is, kind of largely empirical. And, we're learning a lot along the way. And so then a question that, I think kind of is at the back of all of our minds, or at least is at the back of mine, is, well, what should the role of mathematics be in this area, right? How can we help? And of course, this is a very general question, and probably the other speakers in this workshop have sort of better or more sophisticated answers to it than I do. But just a few personal thoughts. So there are a few general questions that come up in deep learning that are really hard to answer in this data-driven world, in this world where our universe is a data set. One that we saw earlier today is this issue of uniformity, right? So for example, if I'm in a computer vision application and I know that objects can move, how do I give a uniform guarantee of classification performance over that set, right? I need to make sure that my network is invariant. That's a for all statement. And so that seems to require some kind of mathematical reasoning, some kind of structural reasoning. We saw a really nice example of that in Rishi Kandor's talk earlier today in the workshop. Another example is robustness, right? If you want to guarantee robustness to a class of perturbations, then somehow this feels like it requires us to think analytically to some extent. And then a third issue that's a little bit hard to address in this world of the data set is actually how the structure of the data influences what I need to do to solve the problem, right? If my whole world is this data set, and then I get only a very indirect look at that question. And so, with some of these considerations in mind, we sort of set out a couple of years ago to try to think about what would be some good mathematical model problems here, trying to look for some sort of end-to-end guarantee of performance in some kind of a simple scenario. I've kind of framed this in a big way, but obviously this is a personal answer to these questions. The field has a lot of really good answers that, probably better answers that we've seen in this workshop so far. But for us, the thing that kind of stood out in thinking about these questions is really the role of the data structure. So we know that data arising in a lot of applications in vision and signal processing in the sciences tend to be structured because of the physical processes that generate the data. And so, one type of question that you can ask here is, how do deep networks compute with low dimensional structure? How does low dimensional structure help, right? We saw an example of this in the last talk. And are there some model settings where we can sort of think in an end-to-end fashion about what I require in my network, in my data, in my computation, in order to do the right thing over some structured data set? So these are the types of questions that are motivating this talk. And in particular, we'll think about this for data with manifold structure. So we'll imagine that our data set consists of several low dimensional manifolds in a high dimensional space from which we see data samples. Of course, low dimensional structure is ubiquitous in applications, right? It shows up all over the place. Manifold structure, you have to look a little bit harder to see, in a very clear fashion, right? If I take a computer vision data set, typically there are a combination of different types of variability, right? There's a kind of variability in the shape and appearance of objects that we typically model as probabilistic and treat probabilistically. And then there's a variability that's induced by some of the nuisance parameters in the image formation process, right? The fact that objects move around, lighting conditions change, so on and so forth. And this is more structural in nature, right? This tends to cut out low dimensional manifolds in the high dimensional space. Okay, and if you want to develop a theory for some aspect of neural network training, this structural variability is an interesting place to start, right? Because this is one, as we've seen in some of the other talks, that has a lot of analytical meat in it, right? There are things that you can model here. Also, as we've seen in some of the other talks, this is one that you really want to guarantee to be able to handle well, right? You may not be able ahead of time to guarantee to see every type of dog in the world, but you certainly know that if you see an object at one pose in an image, you could see it at other poses in the future. So we want to make sure that we're doing the right thing there. Okay, so this is an example of how low dimensional structure shows up in vision applications. Of course, low dimensional structure also shows up in scientific applications because the physical systems and physical laws that generate our data are often simple. This is a kind of extreme example of this. This is from a collaboration with some folks in astronomy and astrophysics at Columbia. So they're sort of interested in the properties and behavior of black holes. So this is gravitational wave astronomy. And here, at least in some versions of this problem of sort of detecting when black holes are doing interesting things far away in space, we run very naturally into data with manifold structure. And the reason is that the systems that are of interest to the astronomers are typically situations where you have a small number of objects interacting, say 2 black holes are merging. So black holes are simple, they're simple objects. They have relatively few parameters, maybe the masses, spins, some angle of inclination, so on and so forth. So if I think about all of the instances of this system that I could encounter, these cut out a low dimensional manifold in the high dimensional space. And then one of the principal problems in computing with this data is figuring out, given an incredibly noisy signal, whether what I've seen is a noisy sample from this manifold or whether it's simply noise. Okay, so, again, this is just another example of how we might run into manifold structure in an application. Again, this is a particularly clean example, but pretty much every physical system generates some form of low dimensionality. Okay, so with all of that as backstory and motivation, the sort of technical problem that I'd like to talk a little bit about in this work is kind of an abstraction of these last two problems that we've seen, where I imagine that I have data that come from two manifolds. So I have two submanifolds of the high dimensional data space. I see some samples generated from a probabilistic distribution on those manifolds. And I would like to learn a classifier that correctly labels the manifolds, in the sense that I have two manifolds here, say a positively labeled one and a negatively labeled one. And what I'd like to do is I'd like to put a positive number on every point on the plus manifold and a negative number on every point on the minus manifold, right? So I want to correctly label all of both manifolds. So, this is kind of a cartoon model problem, right? It's cartoon both in terms of the structural assumptions on the data and in terms of what we're asking for on the output. You can see that the output here as a kind of very strong form of generalization, right? We're asking that when we see new samples from these distributions, we're going to do perfectly on them. Okay, but that's the problem. Now, one technical detail of many to come here. So in this work, we ask our manifolds to be submanifolds of the sphere. So all of our data are normalized. This is purely a technical convenience. I'll tell you later on when we start running into things that that you should really worry about, but this is probably not it. The reason that this technical convenience is helpful is that it allows us to think in terms of angles between data points. And when we start pushing data through a neural network, we're able to think in terms of how those angles between the data points evolve as the data propagates up the network. So, that's why we ask the data to live on the sphere. But in any case, with that said, this is the model problem that we would like to think about here. So I have two manifolds. I have data that are sampled from them. I would like to learn a classifier that correctly labels every point on each of the manifolds. And I'd like to know, when and how I can do this. So I'd like kind of an end-to-end algorithmic guarantee, right? With this network structure, with this algorithm, then with this much compute, this happens. Okay, so this is what we would like to do here. Any questions or comments on the problem setup before I start talking in more detail about our geometric assumptions?
Can I ask a question?
Yeah, sure.
How right now you are labeling, how do you define the landmarks, the important landmarks?
Okay, yeah, good. So here we're sort of imagining that we have a learning problem. So we are imagining that we see labeled data, right? In the cartoon at left here, we see images of either hedgehogs or hairbrushes, right? So we see labeled data. We assume that the data samples, which here are the xi's, are drawn IID from probability distribution on the two manifolds. And we assume for each of those data samples, we know which class it came from. So we have a label yi, which is either plus or minus 1. So, in your question, you mentioned landmarking, and that's also a very important problem.
Because
so it's a little bit different. Here, this is a supervised classification problem.
Correct. Because you are using right now still images as the ground truth. What about when it comes to the deform shapes or deforms like the dogs? You're using the dogs pictures. How you can recognize whether the train model can still recognize it as a dog?
Yeah, excellent. So I think there are two answers to that. The answer within sort of the universe of this talk is that images of the dog under varying articulation cut out a manifold in the high dimensional space. And what we're going to do is we're going to try to prove a theorem that says that if you see enough samples from this manifold, then you will correctly classify every point on the manifold. And so you'll sort of guarantee that you do the correct thing when you see that dog at a new pose. So that's sort of the answer within the context of this talk. Now, in this talk, as you'll see in a few minutes, we're going to analyze some fairly generic neural networks. And actually, I think that in truth, it's an interesting, it's sort of an important and fruitful direction to think not only about the statistical and geometric properties of these objects as subsets of the high dimensional space, but also like what are the network operations that allow you to compute specifically with that kind of deformation that you mentioned. And so, you know, I would say sort of stay tuned on that. But yeah, it's a good question.
Thank you.
Okay, great. So maybe we can move forward a little bit. So this is sort of our model problem, right? So we have two manifolds, samples from the manifolds, want to classify the manifolds. Okay, so our ability to solve this problem is going to depend a lot on the properties of these manifolds, right? Intuitively, if they're higher dimensional, then the problem will be harder. If they're curvier, then the problem will be harder. If they're closer together, then the problem will be harder. And so when we start thinking about what kind of resources we need to solve this problem in terms of data, in terms of the network structure, in terms of the compute, it's all going to be phrased in terms of these kind of geometric difficulty parameters. And I've listed on the slide here the relevant ones for this talk. So this talk is about the case where the dimension is 1. So here our two manifolds are two curves. Obviously, in most practical applications, the dimension is higher than 1. So, you know, this is very much a limitation of the results that I'm going to show you. As you'll see, there's probably enough here to do dimension higher than 1, but we haven't done it yet. So this will be a talk about d equals 1. Sometimes this happens, you know, you wake up one morning and you've written 300 pages about d equals 1. That's the case here. So this is a talk about dimension 1. So in dimension 1, curvature is, you know, pretty simple. This is an extrinsic curvature of the manifolds as submanifolds of the sphere. So, you know, what that means is, as you see in the picture, you're going to, at a point, make an osculating circle. You're going to look at the reciprocal of the radius of that circle, and that's your curvature. Separation is pretty self-explanatory. And then there's one more geometric property that sort of ends up being important here, which is this last thing that we've taken to calling the Clover number. What this is reflecting is the tendency of the manifolds to loop back on themselves. So basically, it's going to turn out that when we go to do the analysis, problems in which the manifolds tend to be nearly self-intersecting are more challenging than problems in which they're not. So this Clover number is sort of capturing how loopy M is. And in particular, this is captured by looking, you know, at a point on the manifold, asking how many times we return to a neighborhood of that point. And that's sort of captured by a covering number of a certain set. So this Clover number is that number. It's capturing how loopy this manifold tends to be. And this thing tends to be pretty small in practice. It's going to be bigger when the data themselves exhibit certain symmetries, right? For example, in the 2 digits, in the images of the 2 digits here on the slide, if I think about rotations of the 4, well, every rotation of the 4 is pretty different from every other rotation, right? They cut out something that kind of looks like, that kind of looks like a circle. For the 1, there's a near symmetry when you flip it over. And so the manifold of 1s nearly self-intersects. So it's going to have bigger Clover number. So this is sort of what's captured by this thing. In the slide in upper left, we have Clover number 1, 2, 3, 4 for some different geometric configurations, right? Basically, how many times you can return to the same point. Okay, so these are our geometric problem parameters. These are going to be what dictate whether we can solve the problem and how hard it is to solve. And again, the major restriction here for the papers that I'll talk about is that we only do d = 1. Everything else is pretty general. So curvature can be arbitrary, although you pay for it. Separation can be arbitrarily small, although you pay for it. Clover number can be arbitrarily big, although you pay for it. And we sort of tell you how much you pay for it. Also, since this is a math conference, I should say that we're assuming that our curves are sufficiently differentiable, and you'll see that the uniform bounds on the derivatives in the parameterization with respect to arc length also show up in the result. But I think the most interesting geometric parameters here are the ones that I described. Okay, so these are our geometric assumptions, and again, we sort of want to know, you fix the geometry. Let's figure out how much we need to do the right thing in this strong sense. Okay, so to do that, we're going to analyze a sort of concrete network structure and concrete training algorithm. Our networks are going to be deep, fully connected networks. The depth here is going to be a very important resource for solving this problem. We're going to train them using gradient descent with random initialization trained over big N IID samples. Here, a few details. So our networks are going to be deep and somewhat wide, right? The width is going to be an important resource here. Our networks are structured as tubes. So in the theoretical result, the width of all of the intermediate layers is constant. We call that width n. Actually, some aspects of this are sharp enough that you could sort of change it and optimize something a little bit. But for simplicity, we've made it a tube. And if you're an expert in this area, you know that sometimes it's not a tube, but here it can be a tube. Okay, so this is our network setup. We're training from randomly initialized gradient descent. Our initialization is kind of the standard one, the HA initialization, where the initial weights are IID Gaussian with variance 2/n. 2 is to compensate for the fact that it's a ReLU network, so we throw away half of the things. And this is the variance that allows information to propagate stably through this network. So this is going to get us the kind of isometry that we alluded to earlier on in the talk. Okay, so that's our network setup. So again, our resources here are the depth, we call that L, the width, we call that little n, and then the amount of data that we've seen, right? And the theory question is, what resources do we need in terms of the properties of the data? Right? And ideally, eventually, we would like those to be minimal. They won't be minimal here, but we'll be able to give you some sufficient conditions. Okay, so this is what we would like to do. Okay, so we're analyzing a concrete training problem, kind of like we saw in the previous talk. We're training with the square loss. And we're analyzing gradient descent. And so, the algorithmic question here is basically a question about whether gradient descent does the right thing. Does it approach a solution that correctly labels the manifolds? Okay, and personally, so this is asking about the behavior of a local method on a non-convex problem. My personal sort of preferred approach to this is to work in parameter space. For a lot of simpler non-convex problems in dictionary learning and deconvolution and matrix recovery, it's possible to do this, and you can sort of get insights into how the symmetries of the problem shape the geometry of optimization. And you can sort of really know in a very fine-grained way what's going on and how to leverage it to get fast algorithms. So this is really how I like to think about non-convex optimization problems. This is not what we're going to do here. And the reason is simply that this problem of analyzing training of a deep network is hard. We have multiple layers, right? Those layers are sort of compounded hierarchically. There's a symmetry between each pair of layers, right? There's at least a permutation symmetry. And right now, at least for myself, we don't really have the technical tools to reason about this in parameter space in a sort of convincing and general way. So what we're going to do is to sort of follow a lot of smart people in this area who sort of don't really think in parameter space, but instead think about the neural network in terms of the input-output relationship that it represents. So basically, you're sort of thinking about it as this big soup of parameters that's allowing you to realize a certain input-output relationship. And one crucial object that shows up there, which was, I guess, really nicely introduced in the talk of Jason Lee, is this neural tangent kernel. So this is an object, here we're calling it theta, that takes in 2 data points. And what this thing is measuring is basically the ease of or difficulty of independently adjusting the network output on these 2 data points. So if theta is big, then there's a lot of correlation between the network output on X and the network output on X prime. And so I'm going to need a kind of big change in the parameters to make them do different things. So in particular, what you would ideally like from a fitting perspective is that theta XX is big. That says that it's easy to change the output at X. Theta X prime is big. That says that it's easy to change the output at X prime. And the off diagonal term, theta X prime, is small. That says that changing one doesn't affect the other very much. And so we're sort of allowed to independently adjust them to achieve the result that we want. Okay, and so that's the neural tangent kernel in notation. So we learned about this through this really nice paper of Jacot et al. But this is the focus of a lot of very insightful recent works in the field. Jason Lee talked about this. There have been contributions from many folks. So this is a sort of very actively studied object. What we'll see is that we actually do need to know a few new things about this object to really get what we want here, which is kind of an end-to-end guarantee for this particular problem. But this is the perspective that we're taking. And as you'll see, this is a really natural object once you start to think in terms of the input-output relationship. So in particular, if you think about what happens when you try to minimize this square loss. So, first you think about some kind of continuous time analog of gradient descent, the gradient flow. Well, this square loss is an integral over the data. Here, this mu n is the empirical measure. So this is like a sum over the training samples. And you're squaring the misfit at each point, right? So if you differentiate that, then if you differentiate that with respect to theta, then basically what you get is, just by the chain rule, is the derivative of the network parameters with respect to theta times the error integrated across the data. Okay, so this is how gradient descent works. And if you want to know what that does to the error, well, that sort of runs you right into this neural tangent kernel, right? So if you say, how does the misfit at point X evolve? Well, that's the derivative of the output with respect to the parameters times the derivative of the parameters. And so if I just follow my nose a little bit, this operator theta falls out, right? And so here in this integral equation, theta is a kernel, right? It's taking 2 points, x and x prime, it's spitting out a number. You can also think about this as a linear operator on the error zeta, right? So my change in zeta is minus theta zeta. Theta is this operator. Okay, and so in general, we should expect that this error is decaying quickly, right? We're doing a good job of reducing the fitting error if this zeta is aligned with the lead eigenvectors of this operator theta, right? This theta is going to have some big eigenvalues. Intuitively speaking, these are going to correspond to low frequencies. Some small eigenvalues, these are going to correspond to high frequencies. And so we expect fast decay if our error is mostly aligned with the eigenvectors corresponding to the big eigenvalues, right? Simply because of this equation. And of course, this theta is a function of the current parameters. So this is also evolving over time, right? So that's also going to have to be accounted for. But the key intuition here is that we're going to be doing well if the error is aligned with the lead eigenvectors. Okay, so this is the neural tangent kernel and sort of how it shows up. Now, when we actually go to do analysis, we can't, we can't implement gradient flow, and so we instead analyze a finite stepping gradient method. So just gradient descent with a small step size tau that we'll prescribe as part of our theoretical result. But the intuitions for this are similar. Again, this finite stepping gradient method is going to do a good job of reducing the error if the error is close to the stable range of this operator. Okay, so this is so this at a high level is this sort of neural tangent kernel approach to analyzing the evolution of gradient descent. Again, this is an input-output relationship approach. It doesn't tell you what the parameters do, but it's a really useful tool for getting going here because you don't have to worry about what the parameters do, at least not explicitly. Okay, so then the question is, well, okay, is it actually true that the error is well aligned with the stable range of this thing? Are we actually going to make rapid progress? And that's going to depend on a number of factors in our problem. That's going to depend on the geometry. It's going to depend on the properties of the network. And it's going to depend on the sort of initial function that's implemented by the network. And so, kind of in analogy to some of the certificates that we alluded to earlier in other areas where you sort of can construct a witness that gradient descent will do what you want. Here we like to think about the behavior and reason about it in terms of what we've taken to call certificates here. The idea is basically, again, you're going to be doing well if the fitting error at initialization, so f theta 0 minus the target, is close to the stable range of this operator theta. Because again, theta measures the changes that are easy to make with my neural network. And so we can encapsulate this by saying, well, if I can well approximate the error as theta times something that's small, this g, then we're in pretty good shape. And in particular, when you go to sort of prove theorems, you're going to want a certain quantitative approximation here. You're going to want a certain quantitative smallness. But basically, we're going to say that gradient descent will do well if my error can be well approximated by theta times something small. And again, that theta times something small is sort of capturing implicitly the alignment between the error and the eigenvectors of theta with large eigenvalue, right? If the error is all in the small eigenvalues, then I need a really big G. Okay, so that's this notion of certificates. If you like kernels, this is also sort of tightly related to the reproducing kernel Hilbert space norm of the error in the RKHS that's generated by theta, right? Because again, we're saying that the error is theta times something small. Okay, so this is this notion of a certificate. Again, maybe a little bit technical and a little bit of a mouthful on the slide, but what this is really capturing is that when this thing exists, our fitting problem is one that our neural network is well suited to solve, right? In the sense that I can make rapid progress with relatively small changes to the weights. Okay, and so, what do these things look like? Again, the intuition is that when a small G exists, the error is near the stable range. So we're going to be doing well. The G tends to reflect a lot the geometry of the manifolds. So plotted here is an example of G. Again, this is a function over the two manifolds. And you can see that this tends to be big where the manifolds are close together and where they're very curvy, right? So again, this is sort of reflecting the importance of those geometric parameters, the separation and the curvature. Okay, but this notion of a certificate is going to be the sort of technical notion that drives our analysis. And a sort of first lemma that we can prove is that if you have a certificate, so if you've set up your network such that it can do a good job of adjusting to the initial misfit, then, indeed, you will converge to a solution that perfectly classifies the manifolds. So that's what this lemma says, is basically, if this is true, then we're in good shape. And, I've sort of stated it here in a way that hides the details, but to make sure that that's true, I need sufficient resources. In particular, I need enough depth. We'll come back to that in a minute. I need enough width, and I need enough samples. And we'll talk about how each of these quantities sort of plays into the overall complexity as we go. But basically, the point of this lemma is just that if you have a G, if you have a certificate, then gradient descent is going to solve your problem. Okay, and so then the sort of big question here that links the geometry of the problem to the resource requirement of the network is really, well, when is this true, right? When do you have such a certificate? Okay, and this is where the depth of the network really becomes an important resource. So it turns out, because of the way that information propagates in deep networks, as you increase the depth of the network, this kernel, the neural tangent kernel, gets sharper. So what that means is that it becomes more preferential towards nearby points. Or put another way, it does a better job of ignoring things that are not nearby. I'm more able to independently adjust the output at non-adjacent points. So my network depth in this setting is a lever that allows me to increase the approximation, sort of the ease of approximating complicated functions with my neural network. And the way that that operates, again, is through this sharpening of the kernel. Here's depth 5, 10, 50, 100, 500, 1,000. So as you get deeper, it gets sharper and sharper. And so the way that one can try to reason here is that basically the depth is going to need to be set based on the geometry, based on how complicated the manifolds are. So you're going to set it well enough that this operator is sort of localized at the scales that are important in this problem. So sort of localized at the scale of the separation and localized in a way that's dependent on curvature, and so on and so forth. The way that this plays out mathematically is, again, you're trying to argue that the error is close to the range of the kernel by generating a G. You approximate the operator as something that's accounting for the nearby points and then something that's accounting for everything else. The nearby ones, if you make a local approximation that's sort of below the scale of the curvature, then the nearby one can be approximated by an operator that's invariant over the manifold. And so you can sort of use classical harmonic, you just use Fourier analysis and you can invert that. The operator as a whole is hard to invert analytically because you have a structured data set. You don't. Typically, we never have explicit information about the eigenfunctions, and this certificate problem is sort of asking us to indirectly get at the alignment between the eigenfunctions and the error. We don't have the eigenfunctions, but we can still reason about this kernel and this integral operator by basically approximating it as something whose eigenfunctions are simple and something else that we can sort of account for. And so, the way that this is done in the paper is by using a combination of a sort of Neumann series argument and an iterative construction. And there's a lot more than what I can talk about here, but this is sort of the basic idea, right? The basic intuition is that shallow networks tend to be correlated in what they do to different points. Deeper networks tend to be better at adjusting network outputs on distinct points independently. And so we're going to leverage that to be able to reason about the invertibility of this integral operator. And that's going to be key to how we prove things here. And
John, I just wanted to mention, it looks like you have quite a few slides left. I just want to point out you have like 4 minutes left.
Yeah, thanks. Sorry about that. I will do my best to get a few key intuitions in, and I will make sure that I finish on time. Thanks. So the point is, if you make the network deep enough, then you can argue that a certificate exists. Again, depth is an important resource in making that happen. If a certificate exists, then gradient descent succeeds. In reasoning about this is where sort of the network width and the number of samples become important resources. In particular, the width in this setting is kind of a statistical resource. This is making sure that the behavior of randomly initialized gradient descent is in some sense regular and in some sense close to a large network limit that one can reason about. And so one of the things that one has to do to get a result here is to reason about the concentration of this neural tangent kernel about its initialization. This is a kind of interesting subproblem in concentration of measure. You have this kind of sequential structure in the sense that if I think about a randomly initialized neural network, I have a sequence of layers. Each of those has some random weights. So I have this kind of sequential randomness where I do something and then I do something independent to it, and then I do something independent to it, and so on and so forth. It turns out that martingale tools are, kind of really natural for reasoning about such processes. And if you sort of dig in carefully and do a little bit of analysis, you can use a combination of martingale tools and some sort of sharp estimates for the evolution of angles between points through the network to get sharp concentration results for this kernel. And in terms of the sort of rates that we achieve, this is the one part of the paper that has good rates. The rest of them are very bad. But these turn out to be not too bad, and in some sense best possible. So this is a sort of a piece of the technical analysis that may be more broadly applicable. Okay, but in any case, here width of the network is a statistical resource. Data is also a statistical resource. So the idea is we're going to make the network deep enough relative to the geometric properties of the manifolds. We're going to make it wide enough to ensure that gradient descent sort of behaves in a regular manner. In particular, that width here is going to be polynomial in the depth. And then the amount of data is basically going to be enough to cover the two manifolds at a scale that's dictated by a kind of aperture of the kernel, right? When you sort of want to generalize, then correlations of network outputs between points help you, because it means that putting the right sign on this point also sort of drags nearby ones in the correct direction. Okay, so that aperture of the kernel sets the number of samples that you need. And if you do all of those things, then you get this kind of end-to-end guarantee. What this says is that when the depth is sufficiently large relative to the geometric properties of the manifolds, when the width is sufficiently large, and when you have enough samples, then indeed you solve this problem in this kind of strong sense that we articulated at the beginning of the talk. So what I think is, what I like about this is the fact that this is an end-to-end result. So it's only depending on the geometry of the problem. What's not great is if you look in the papers, these polynomials are big polynomials. So, there's certainly room to improve there. I will skip so you can sort of leverage these ideas to do interesting things in science applications. That's maybe another talk or another 10 minutes, so we'll skip that. And we'll just wrap up there. So, I think that these questions of how neural networks interact with low-dimensional structure, how we can get end-to-end guarantees for model problems, I find interesting. There's a lot still to do. So, hopefully this work is some kind of a step in that direction.
Great.
Okay,
right, well, thanks.
So, thank you.
Yeah, thanks very much. I think we're running a little bit behind, so maybe I'll just let people contact you directly for questions.
Okay, yeah, sorry about plowing through the question time.
No problem.
Yeah, thank you.
Yeah, lots of great ideas there. So I'm sure there'll be plenty of questions, but I think we'll need to move on for the moment.
Okay, sounds good.
Guido, are you able to share your screen?
Oh yeah, let me give it a try. I think this one, sure. Okay, so I'm not sure what you see right now.
Yep, you can see your presentation screen.
Okay, wonderful. All right.
So, yep, I'm happy to welcome as our last talk of the day, or at least the afternoon session, Guido Montefar, Assistant Professor of Math and Statistics at UCLA on the geometry of linear convolutional networks.
Thank you very much, Greg. It's really a pleasure to speak here and present this very recent work on geometry of linear convolutional networks that we wrote together with my dear colleagues or collaborators, Kathleen Kohn from KTH, Thomas Merck from UCLA, and Matthew Traeger from Amazon. So I'm going to try to monitor the chat, or please feel free to interrupt if you have any questions along the way. Okay, so, well, linear networks, this is certainly a topic that has been studied for a while now, maybe starting with the pioneering work by Pierre Baldi and Kurt Horneck. And one of the reasons we're interested in these networks is that they can give us an insight into the effects that the parametrization can have when conducting optimization in deep neural networks. But maybe I will try to convey the idea that they can also be useful to try to get an understanding of the geometry of the function space and how it affects the optimization problem. So certainly the geometry of the function space is one of the perspectives that has received a lot of attention in the past couple of years, because maybe you have an objective function, a training function in function space, which is convex. And so if your function space, like your model, is nice, maybe nearly linear, then this optimization problem can be easy. In the case of linear neural networks, there is quite a bit of work that people have done. But so what we wondered is what happens when we have convolutions. And so let me give you a little bit of an illustration. So a linear convolutional network, in this case with one-dimensional convolutions, is going to be parameterizing a family of functions that goes from some D0 dimensional space to some DL dimensional space. So it's taking an input X and mapping it to this value. So it's a linear function. So we have a matrix W that we're multiplying with the input. But now the matrix W is going to be a product of other matrices. So these are going to be the layers of the network. And each of these matrices, we're going to ask that it is a convolutional matrix. And in the case of the 1D convolutions, what that means is that we're going to have a particular row that we're going to be repeating all over the matrix. And we're going to be shifting it at the subsequent rows. Now this shift here is going to be the stride of the convolutions. And we're also going to have a certain number of entries in every row that are non-zero. And that's going to be the filter size for the convolutional matrix. Now you see that there are repeated weights in here. So all along these diagonals. And so we have a situation with weight sharing. And we also have these zero entries where I didn't put any entries. So we have, so to speak, clamped weights, and we have repeated weights. So here is another example. Maybe we say that the dimension for the output is going to be 3. So that means we're going to have 3 rows in here. We're going to say that the filter size is also 3. So then we have 3 entries here that are non-zero. And if the stride is 2, then that means that we're going to be shifting this row by 2 every subsequent row. So that's what a convolutional matrix could look like. And so in here, we're going to have this product, right? Now, the linear convolutional network architecture, that's going to be specified by a triplet of vectors. So the first one, the D, is going to be telling us basically the width of the layers, or basically the outputs that we're going to get at every layer. Then K is the vector that contains all the filter sizes in the different layers, and S is a vector that contains all the stride sizes for the different layers. Now, okay, so this is the roadmap. Geometry of the function space. So what kinds of functions can we actually represent by this type of neural networks? Then I'm going to tell you a little bit about the optimization problem, and then try to do a comparison with fully connected networks. Okay, so expressivity. Now, the function space of the linear convolutional network is going to be denoted here MDKS, and that's going to be the set of all matrices that map from D0 to DL. So these are going to be the end-to-end matrices. So that is this product of the different layers. Which of the layers is a convolutional matrix? Our first question is, what is the impact that the architecture has on the geometry of the function space? So this is a set of matrices, and it will have some geometry. We want to know what that is. Maybe the first observation here is that W, the end-to-end matrix, is going to be a convolutional matrix. So when we are doing this composition of convolutions, we're going to get a convolution again. And we can, not too difficult to compute what is going to be the filter size. So it's going to be given as a product of the filter sizes of all the layers, and it's going to depend a little bit on the strides. And the stride size of that convolution is also something we can compute. Is going to be just the product of the stride sizes of all the layers. And a corollary from this observation is that the set of convolutional matrices, end-to-end convolutional matrices that we can represent, is a subset of the set of convolutional matrices that map from D0 to DL. And in this case, the difference is over here, we're looking at those matrices that are given as compositions of convolutional matrices. And over here, these are just convolutional matrices. So this guy here is a vector space of matrices. The only constraints that we have is that some of the entries are 0 and some of the entries are repeated. But this is in particular, it's a vector space, it's convex and nice. So, and this is a subset of that. Now, one first question that one may ask is, when are these two things equal? So we're gonna denote that as filling. So an architecture DKS is filling if these two things happen to be the same. And if you think about it, that's, it does something like saying you can represent every matrix that you could possibly represent. Now, when does this happen? Still focusing on the case of stride 1. Now, this is kind of the first observation is the following. So we can identify convolutional matrices with polynomials. And the way this works is that if you look at this matrix, what we're going to do is now take every row, or every column, I mean, and assign to it an index. So of course, they are naturally indexed. So, but we're going to write that index in terms of this monomial. So this is an x to the power k minus 1, where k minus 1 is the size of the filter, minus 1, and that's going to be basically indicating that this entry is sitting here at the beginning of the filter. So the W0 is at the beginning of the filter, and the next one is going to get assigned this kind of basis vector, which is another monomial. And we write it in this way so that so this actually turns out to be a polynomial with real coefficients in these two variables x and y, and is of degree k minus 1, and it is homogeneous because of the way we have defined it. We have here a power k minus 1, and here again k minus 2 times power 1. So this is homogeneous. All right. So, and the observation that we had previously was that these compositions are actually, again, convolutional matrices. And when we write them in terms of these polynomials, what we observe is that, in fact, maybe first of all, so this identification that I'm writing here is going to be denoted by pi. And so if I look at the polynomial that corresponds to the composition of all these matrices, it turns out that it is given precisely by the multiplication of the polynomials of the individual layers. So once I identify this thing with this polynomial, I can just go ahead and multiply these polynomials together to get what would be the output polynomial. All right, so now using this property or this observation, we can already prove our first theorem. And what it says is that if we take a matrix, and that matrix is going to be an element in our function space by the, represented by our neural network architecture DKS, if and only if the polynomial that is being represented has at least E real roots. So, a polynomial has zeros, and we're going to look at how many zeros this polynomial has. And we're requiring that it has at least E many real roots, counting multiplicities, where E is the number of filters that are even. All right, so I just look at basically all the filters that I have in my neural network. I count how many of them are even, and then the convolutional matrices that I can represent are precisely those that correspond to polynomials, which have at least that many real roots. And from this, once we're talking about polynomials, there is a lot of mathematical technology that we can exploit and use to try to understand these models. And so an observation that we can derive from there is that this set of convolutional matrices is in fact a full dimensional semi-algebraic subset of these end-to-end convolutions of this vector space that is kind of naturally containing it. So full dimensional just means the standard sense of the word. You have as many dimensions as the ambient space, as this other object in here. And semi-algebraic, what that means is that it is a subset that is being cut out in terms of polynomial inequalities. So linear inequalities are an example of polynomial inequalities, but you could also have a quadratic equation that cuts out this set from there. So that means that the entries of this matrix satisfy certain constraints. So there is a polynomial in the indeterminates given by the entries of this matrix, and that polynomial has to be larger than or equal to 0. So those are going to be the algebraic inequalities that determine that set. Okay, next one is that we can actually also see that the function space or the architecture is going to be filling. So that means again that the function space is equal to the natural ambient space if and only if the number of even filters in the network is at most 1. And this is kind of interesting because maybe it's something you wouldn't expect a priori or directly, but that's the way it comes out. So, and in particular, what this means is that, if we wanted to be able to represent any convolutional matrix as a composition of these convolutional layers, then we would rather, we would have to pick all the different filters to be of odd size. So it could be, for example, filters of size 3 or 5 or 7, but we wouldn't choose even filters. Or we would be able to use only one even filter. Let me show you an example of what happens when we have 2 even filters. So as I told you in the theorem, so if we have at most 1 even filter, then we can express any convolutional matrix. But if we have 2 or more even filters, then we're going to get those constraints, those inequality constraints. This is still in the case of the stride 1. And so let's look at the polynomials, so pi of our function space. So these are going to be polynomials in the 2 variables x, y of degree k minus 1. And these are going to be the polynomials that have at least 2 real roots. So as we saw here, so the polynomial is in the function space precisely when it has at least as many real roots as there are even filters. So we have 2 even filters, and therefore we're going to have at least 2 real roots. And so in particular, if we look at the complement, so we look at what is left behind, so then that's going to be the set of polynomials which have no real roots. And the reason for this is that if you count how many entries or what is the degree of this polynomial, so this is going to happen to be an even number. And so an even polynomial can have essentially 2 roots or 4 roots, etc. So once we say that it has at least 2 real roots, then the complement is going to be those that have no real roots. All right, so and that set turns out to be precisely given by the union of the positive polynomials and the negative polynomials. And both these 2 sets, they are convex cones because whenever you have a polynomial that is positive, meaning that it is always above 0. If you take 2 of those polynomials, you can add them together with positive coefficients, and you're still going to get one of those polynomials. And so therefore, this is a convex cone, and this one as well. This is illustrated down here for a particular example. So we see here is this cone and this cone. Those are what I'm plotting here are the coefficients of quadratic polynomials in one variable. So there are 3 coefficients for the quadratic term, for the linear, and for the constant. So these are 3 real numbers. They correspond to the entries of the filter. And as I was saying, they satisfy constraints. And the constraints are precisely this cone. And so that's going to be defining the boundary of our function space. And these 2 cones are the complement of the function space. So the function space are all the points in here. And these cones are the boundary of the function space. Okay, so now you can already kind of imagine what's going to happen if we try to do parameter optimization in here. Maybe we have some data set given to us and we want to do least squares regression. Maybe that data set is going to correspond to one point that is sitting in here. And least squares regression is going to correspond to minimizing some quadratic distance to this cone. And that's going to lead to some interesting effects. Okay, so let me tell you a little bit more about the boundary of the function space. It turns out we can actually characterize this more generally, and this is the way it looks. So in order to do that, we're going to look at the combinatorial property. And so let's see. So we take a polynomial again. So this is kind of corresponding to our convolutional matrices. And we're going to say that it has a real root multiplicity pattern, or RRMP. And this is written in the following way. So it has a component rho and a component gamma, and rho and gamma are vectors. And so if this polynomial can be written in the following way. So we have the polynomial P, and we're going to factor it into some terms, P1 to PR and Q1 to QC. And those factors are raised to the power of the entries of the vector rho and the entries of the vector gamma. And these P's and Q's, they are going to be polynomials of degree 1 and degree 2, both of which are irreducible and linearly independent. What it means to be irreducible is just that you have a polynomial that you cannot factorize any further unless you're just pulling out some constant. And so for a linear polynomial, that's, I think, maybe quite intuitive that you cannot split it any further. And for a quadratic one, when you cannot split it, what it means is that it doesn't have any real roots. So if it had real roots, you would be able to split it into two linear factors. Okay, so but whenever you can factorize a polynomial in some particular way with irreducible factors, and then the multiplicity of those factors, that's what we call the real root multiplicity pattern. You can see that this rho 1 corresponds to the multiplicity of the root, the single root of this linear polynomial in here. And similarly for the other guys. And the gammas are the multiplicities of the of the complex roots. Okay, now here's the theorem. So as before, we let E be the number of filters that are even, and we let this be bigger than 2 because we want to have a function space that is not equal to the ambient space. So we want to look at the boundary. And so in that case, our matrix W is inside of the function space in our model, if and only if. And this is just a restatement of what I told you before. But now in terms of the real root multiplicity pattern, what we are saying is that this rho, these are the multiplicities of the real roots. And if we look at the sums of all the multiplicities of the real roots, so this is just the total number of real roots, we're requiring that this is larger than or equal to the number of even filters. So it's a restatement of the previous. And another statement that we can make is that this function space is closed in the Euclidean topology. And furthermore, the boundary of that closed set, denoted here by this partial M, corresponds precisely to those filters or to those convolutional matrices whose corresponding polynomial has a real root multiplicity pattern, such that, first of all, it is in the model. So we have at least E real roots, counting multiplicity. And if you were to add, to look at the number of multiplicities that are odd, then that's going to have to be less than or equal to E minus 2. This is a kind of one of those magical mathematical statements, if you ask me. But this gives us a characterization of what this boundary is. So we can actually say what that is. Another observation that we can derive from this is that the Zariski closure of the boundary is a discriminant hypersurface. Now, this is a mathematical jargon. What this means is that if you try to think about a boundary, you can think of it as a surface, some type of manifold, and more generally, this could be an algebraic variety. And the smallest algebraic variety that contains that set, maybe we can call it the Zariski closure. And there is one particular such surface that is the set of zeros of a discriminant. And what that means is that we're looking at the polynomials that have repeated roots. So, so the boundary of our model is going to be contained in a surface that contains all the polynomials which have double roots. Okay, so this is a, kind of a very well-studied object, and so that's very useful for our purposes. Okay, here is an example. Let's say we take a linear convolutional network with 3 layers, and every layer has filters of size 2. So that's our k equals 2, 2, 2, and strides 1. So concretely, that would look like this. So the first layer would be this guy here. So, and so we see the filter of size 2 right here, and it's repeated on these 3 rows. The next layer is this one, and the last layer is this one. In terms of the polynomials, what we see is that, okay, once we multiply this out, we get a matrix of format 1 by 4, and this matrix would correspond to this particular polynomial. So we're just, rewriting this polynomial, and this guy is the same. And what we're saying is, all these factors multiplied together gives us precisely this guy. And here we can actually look at this discriminant hypersurface, and we can look at this loci of real root multiplicity patterns. So let's see. So this is a cubic polynomial of degree 3. And what are the possible real root multiplicity patterns? So we can have 3 distinct real roots and 0 complex roots. So you know that the degree is going to be the number of roots, both real and complex. So we can have 3 distinct real roots and 0 complex, or 1 real root and a double real root, or we can have a triple real root, or we can have 1 real root and one complex conjugate pair of roots. And so let's see, according to the statement in the previous slide, we would know that our model actually consists of, those guys which have at least E real roots, and the boundary would be those where the multiplicity, so the number of multiplicities that are odd is at most E minus 2. So here E is equal to 3. We have 3 even filters. And so the model is going to be those that have at least 3 real roots. So all of these guys above are part of the model. And the boundary is going to be those which have at most one odd multiplicity. So among these guys, only these 2 have an odd multiplicity, namely this one has multiplicity 1 just once, and this one has multiplicity 3 just once. This one has multiplicity 1 3 times, so this one is not part of the boundary. So, and if you look at this is kind of plotting the set of coefficients A, B, C, D that you can obtain in the model. So, although here I think A is being fixed to 1 in this figure. Oh yeah, we're dividing all the coefficients by A. So this is just plotting 3 coefficients and fixing one of them to be 1. And actually these 3 different roots, those are the ones that are sitting on this side of the surface. That's the interior of the model. This guy 1, 2, those are precisely the points on the surface. That's the boundary of the model, or at least the 2-dimensional part of the boundary. And this triple real root, this is this red curve in here, that is also part of the boundary. And this other guy here, a single real root, that's outside. That's everything out here that is not part of the model. Okay. Another example, so we can actually look at different models that can end up having the same function space. So this is something that happens quite a bit. So, and this is maybe an example. So we have a network with 3 layers versus a network with 2 layers. And it turns out that these 2 networks represent the same set of functions, even though they have a different parametrization. And the way we can see that is just by using the arguments from this theorem. So we can write down the factorization. So they look different. Of course, here we have 3 factors. Here we have just 2 factors, but they end up giving the same function space. And this is the way it looks. So we can list all the possible real root multiplicity patterns and see what they correspond to here in some figures. So this is also a quadric polynomial, and there is a way in which we can plot a figure. So it's by looking at correspondence with what is known as the Press polynomials. and then just plotting those guys in here. And similarly to before, we can look at this loci and see what they correspond to in the figure and see what they are. As it turns out, this part above here, this is the complement of the model, and the boundary is this piece in here, this kind of blue ball, and the blue ball corresponds to those guys. Let's see, where we have 2 real roots and no multiplicities that are odd. So all those guys that have at least 2 real roots and no odd multiplicities would be this guy, this guy, and this guy. And those are precisely the guys that we are going to end up getting here as the boundary. So the 2 is the ball, and there's this line down here is the set of points that have 2 double roots, and this point in here is the point that has a quadruple real root. But there are also some other structures in here, and I'm going to get back to those in a moment. All right, so maybe before proceeding, I can tell you a little bit about what happens when we have larger strides. So in practice, maybe we have not only stride 1, but also larger strides. And turns out we can do a similar construction. Now, in this case, you see we're shifting the rows by, say, S. And we can also create this identification with polynomials, whereby now the polynomials are going to, this transformation is going to be, or this identification is going to be pi sub S. And what we do is now these guys are raised not to the power k minus 1, etc., but s times k minus 1, etc. And so this is going to be a polynomial where the variables, if you like, you can think of them as being x to the power s and y to the power s. And we have a similar property as before, but it's a little bit more complex. So if we look at the polynomial of the composition, then that's going to be the product of the polynomials. But now we're going to use the polynomial with step S1 for the second matrix. And S1, interestingly, that's going to be the stride of the first layer. So the stride of the first layer has an impact on the polynomial for the second layer. And so, okay, but once we do that, we can formulate a theorem. So where if we see that, let's assume, this is kind of just to avoid trivialities, like the filter size of the last layer is more than 1. And the stride size is more than 1 in at least 1 layer, because otherwise we're in the setting from before. Then our function space turns out to be a lower dimensional semi-algebraic subset of its natural ambient space. So semi-algebraic is as before, and lower dimensional in this case means that the dimension of this set is actually smaller. So we not only have inequalities, but we also have an equation, at least one equation that is satisfied by the points in that set. And in particular, these type of architectures are not filling. So there are a couple other specific statements that we can make. For example, when the filter size is, when the last filter size is 1, then that doesn't kind of have an impact. So if you think about it in terms of these polynomials, you can see why. So if the filter size is equal to 1, then that's just a constant. And so multiplying by a constant doesn't change anything. And the other thing is, oh yeah, so it doesn't have an effect. And the other thing is that if the stride size of the last layer is 1 or something else, it doesn't matter just by this observation. So the stride of the last layer doesn't enter the picture, but only the strides up to the second last layer. So there's kind of identifications that we can see and things like that. Okay, so another interesting extension, of course, are the convolutions in dimension more than 1, and in particular, d-dimensional convolutions. So for images, we would have d equal to 2. But we could also have, 3-dimensional objects. So the input is now going to be a tensor of order capital D, and the filter is again a tensor of order capital D, and the particular format would be K1 times K2 all the way up to KD. So these are the sides of our little box that we're going to be sliding around the input. And then, so our convolutional tensor, our layer, is the capital W is a tensor of order 2 times capital D. And it can again be identified with a polynomial In this case, it's going to be a polynomial that has more variables. For the one-dimensional convolutions, we had just the variable x and y, and now we're going to have one variable for each of the directions that we have. So we're going to get capital D pairs of xy variables, and they have a particular degree. So previously we just had the degree for the size of the filter, but now we have the degrees for all the different sides of the filter. And so this guy is going to be homogeneous of degree kj minus 1 in each of the pairs. And again, we have this composition of self-convolutional tensors being expressed in terms of the product of the other guys. And now here maybe a statement again is that if we have a linear convolutional network with an order larger than 1 and more than 1 layer and non-trivial filter sizes, meaning that they are also not equal to 1, then the function space is again a lower dimensional semi-algebraic subset of the natural ambient space, and the architecture is not filling. Okay, this is just a little bit of an overview of some of the results that we can obtain in those cases, but let me move on to the optimization before I run out of time. All right, so optimization. Okay, of course, there's a lot of things that you can ask and try to investigate. One is convergence of gradient descent, but fundamentally, some of the things that we're interested in are what are the critical points of a loss function? Are there many of them? Is the loss function convex, or are all the critical points going to be saddles, as is the case maybe in fully connected linear convolutional linear networks? Or not, or what? And so what we're going to observe is that in linear convolutional networks, there can be interesting effects happening. And so let's focus on the one-dimensional convolutions of stride 1. Now we're going to define a loss function to be a function capital L that is a composition of two functions. First, little l and mu. So little l is going to be a smooth function on our function space, on our natural ambient space. So that could be the square loss, or maybe some regression, some other regression loss or classification loss. And mu is just the parametrization. That's the map that takes all the layers and multiplies them together to give us the end-to-end matrix. Okay, so typically this little l, the loss in function space is going to be convex, but our parametrization, of course, is non-convex. And as we saw in the previous images, the function space is also not convex. Now, how are the critical points in function space related to the critical points in parameter space? Because that's maybe one of the fundamental problems and questions in deep learning, and so that we seek to investigate here. So let's say there are some things that are more or less straightforward to see. The first, or maybe the one thing that is maybe straightforward to see, is that if you have a critical point of the loss function in function space, then the parameters that are representing that point, so that's a function, end-to-end filter, they're going to be critical points of the loss function in parameter space. So, it's kind of saying like, if you reach a local optimum in function space, there is no way that you're not going to be reaching a critical point in parameter space as well. But the other way around, what happens? So let's say that I have a critical point in parameter space. Then what can we say about the corresponding end-to-end filter? So let's say, I find a local minimum in parameter space. Can I, for example, say that's going to be a local minimum in function space, or maybe even say that is going to be a global minimum? Or can we do any kind of characterization of this thing? So in the case of fully connected linear networks, some of the things that people have observed is that all the critical points are going to be either saddles or global minima, for the square loss at least. And for the saddles, they have a nice characterization that corresponds to matrices of low rank. So, there is one way of saying something like that. And what's going to be happening here? That's kind of our question. The first thing is that, if you have a critical point so there is going to be an equivalence class. So we have a lot of symmetries in the parametrizations of neural networks, and linear convolutional networks are not an exception. And so let's say, we have something like a scaling equivalence. And what that means is that, let's say we have two parameter choices. We're going to call them scaling equivalent if there are scaling factors, alpha 1 to alpha L, which multiply to 1. And, this gives us a scaling between the parameters in the two cases. And now here's a proposition. So let's say we have an end-to-end matrix that is not zero. Then the set of parameters that represent that matrix consists of a finite union of scaling equivalence classes. And then either all parameters in an equivalent class are critical points or none of them are. So it's as if we were saying that, so we have a function, and in parameter space, it is going to be represented by a discrete or a finite set of fibers or scaling equivalence classes, and some of them may be critical points. So, but if any one point in one of those classes is a critical point, all of them are critical points. And if one of the points is not a critical point, then the entire scaling equivalence class is not a critical point. Okay, so this is a figure that I'm gonna maybe explain later in more detail. But so there is a kind of a correspondent, a discrete, this is talking about the number of equivalence classes that you might get, but I'm going to return to this. All right, so maybe to motivate this and the way we came up with the mathematical results that we obtained, it was also looking at a couple of examples. And so this is a numerical experiment for the square laws and gradient descent. And as I mentioned, so if we have a critical point of the loss in function space, then the corresponding parameters are critical points of the loss function in parameter space. And now we want to know what happens if we have a critical point in parameter space. What can we say about the function? So we look at this example that I showed you before. So it was the convolutional network with 2 layers. And we want to see what goes on. So we generated random targets. And you can see that the targets belong to different classes. They have different real root multiplicity patterns. So for example, some of the targets with 5% of them were of this class, and 72% were of this class, 22% were of this class. And then we did a random initialization, and this model is such that actually generically all the initializations, they fall in the interior of the model, and this is the only real root multiplicity pattern in the interior of the model. And then we run gradient descent until convergence, and we verify what is the type of solution. And we see that for this type of target, the solution converged 100% of the time to, gradient descent converged 100% of the time to the same kind of solution, and the mean loss was 0 or numerically 0. For some other targets, if you recall, this guy here is actually at the boundary of the, let me try to make sure that I'm not telling you something. So these guys, for this model, so these guys, so no, this guy is not on the boundary of the model. This guy here, so maybe I can show you the figure quickly. This is the figure. So the 1, 1, 2 that I was showing you are the points over here. So this is not at the boundary of the model. But these points here are outside of the model. So they have no real roots, and you see they happen 22% of the time. Now, when we train the model, so sometimes, so we do expect that, so we have a target that is outside of the model, and the loss function is convex, it's the square loss. So we expect that if we're training, the critical points are gonna be sitting at the boundary. And so, when we're training, we're gonna hit the boundary. And that happens a lot of the time. So maybe we hit these points in here, 2, 1, which is the boundary, 92% of the time. So that's the solution that we obtain. But sometimes we obtain a solution that is not at the boundary. And so that's kind of interesting. And so we want to understand how that is happening. Let me see here. Here, this is the complement of the model, and this is the boundary. So you see that sometimes we get to a boundary and sometimes we don't. So we get some critical points that are not sitting at the boundary as we would have expected. And in this other model, which has the same function space but a different parameterization, this effect is even more pronounced. You see that sometimes when we have a target that is in the complement of the model, we would expect that training, so the critical points in function space are definitely sitting at the boundary. So those are these guys here in orange. But many times we converge to points that are not at the boundary of the model. So and therefore we can tell for a fact that these guys are going to be critical points in parameter space, which are not critical points in function space. So that's pretty interesting. And so we actually can understand these guys and these effects. So let me tell you how that goes. So what we're going to do is, for a real root multiplicity pattern, we're going to define a corresponding locus of points or of functions. Those are going to be the end-to-end filters whose polynomial has that particular real root multiplicity pattern. And this is some type of surface sitting there in the space of matrices. Now here's the theorem. So let's take an end-to-end matrix, and it has this factorization, and it has a particular, it belongs to this particular locus. Then first item is that if this is a critical point of the loss function in parameter space, then it is going to be a critical point of the loss function restricted to this locus. So that means it's a critical point of the loss function in function space when we restrict it to this particular locus. And secondly, so we have a critical point of the loss function in function space over a particular locus with the real root multiplicity pattern. And it should happen that none of the factors of the end-to-end filter has a double root. Then that parameter is a critical point of the loss function in parameter space. So what this is saying is that we can look at certain sets of functions, look at the critical points of those sets of functions, and if there are no double roots in the individual factors, then these correspond to critical points of our loss function for our model in parameter space. And in fact, for the square loss with generic training data, this item 2 is an if and only if. And we actually believe that this is true for some other losses, but we still have to work out some details. All right, so let's say we want to find all the critical points in parameter space for the square loss and generic data. So then we can list all the real root multiplicity patterns of the polynomials of degree k-1. So it's the size of our end-to-end filter. For each of those guys, we will decide if the polynomials with that particular real root multiplicity pattern can be factored according to the architecture such that no factor has a double root. So the factors are the layers, and we're basically asking that the parameters in each layer, so the layers correspond to filters, and the filters correspond to polynomials, and these polynomials can be factored. And we want that those factors are never equal or don't have the same roots. So this is kind of the pipeline. So we look at these polynomials, the multiplicities, and we want to see that these factors, they don't have a double root. And combinatorially, what that means is that we have a certain number of balls, like these row i's are these multiplicities, and those balls have size 1 because those are the factors that have a single root. And they have a color I. Maybe there's going to be the particular root that we're looking at. And we have the same for the complex roots, and those have size 2. And what we want to do is put those into a number of bins, and those are our layers, and they have a particular size, namely the size of the filters of every one of the layers. And we're requiring that no bin ends up containing 2 balls of the same color. That's kind of the combinatorial problem. And this is a purely combinatorial property that is characterizing the whole thing. And in this case, we call this real root multiplicity pattern compatible with the architecture. So you see that there are certain patterns that will be compatible with certain neural networks, but not with others. And I'm going to show you an example. Then for those patterns that are compatible with the architecture, we determine the critical points of the loss function in function space restricted to that particular locus. And yeah, that's it. So for each of those critical points, we find the factorizations, and those are the critical points in parameter space for our model. And in particular, we observe that the critical points in parameter space, this is a finitely many scaling equivalence classes. Okay, here is the example, and this is kind of explaining now these observations that we had experimentally. So we know that these two neural networks represent the same set of functions, but have different parameterization. And experimentally, we had observed that even if we are training data outside of the model, we can converge to some points that are not critical points in function space. But in this other model, that happened even more frequently, and it was not clear why. Now with the characterization that I showed you before, we can say why that is. Namely, if we look at the compatible architectures with factorization, so this looks like this. So for this network, and that particular type of targets or of points, let's say this 1, 3. The 1, 3 is a pattern that is compatible with the architecture k equals 3, 2, 2, but is not compatible with the architecture 4, 2. So because we can factorize polynomials, here there's a factor that is repeated only once, and there is a triple root. So the factor P2 is repeated 3 times that we can distribute across the 3 different layers. And well, I'm almost finished. And so that's why that happens. So we can explain that phenomenon. I'm going to skip the invariance of gradient flow, but just to tell you that we can classify the invariance, and this allows us to say what's going to happen if we know what is the initial parameter. Now my summary. So we have in fully connected linear networks that the function space corresponds to rank-bounded matrices. So if you have a layer that is small, then you're going to end up getting a low rank matrix end-to-end. And those are described by algebraic equations. So these are polynomial equations. Near convolutional networks, turns out that the function space is described by sector factorizations, and we get an algebraic, semi-algebraic subset. So polynomial equations and inequalities. And this ends up implying that we can have non-global minima of the loss function in parameter space, even if the loss function in function space is convex, and even if our function space is a vector space. So the reason is just a different type of parameterizations. And in fact, this settles one of the problems that seems to have been out there for quite a while about the existence of local minima for the square laws in linear networks that satisfy constraints on the weights. Okay, so that's the end of my talk. Thank you very much.
Great, well, thank you. Are there questions? So just one quick question. Do you have any ability to say anything if you include a nonlinearity like ReLU? Can you say anything about different architectures, right, given the same function class?
Oh, well, that's a great question. That's something that we have not looked into yet. So there have been, of course, a couple of works out there that have tried to extend analysis on fully connected linear networks to the case where you have nonlinearities. And kind of the picture that comes out from there is that, indeed, there is some of those observations that you can port to the case when you have nonlinearities. I guess the main message that we are conveying here is that we can still get a lot of interesting effects in the geometry of the function space once you have constraints in the weights. And these constraints certainly are going to transfer in one way or the other, but the specific shape of the, of the resulting optimization problem, that's something we still have to study.
Okay, great. Well, thank you very much. And thanks to all of our speakers today. It's been a great session. We will continue with contributed talks this evening at 7 p.m. So hope to see you back then. Thanks very much.
Let me join with my iPad.
Okay.
Okay. Okay. That should be good.
Good. Could you try to switch your slides? Switch your pages. Yeah, it works. Thanks.
Okay.
Maybe Jintai, are you here?
Yeah.
You try to share screen because of the tight schedule. We just want to make sure the 4 speakers
Yeah, I see.
can share screen.
Share my screen. So can you see?
Yeah. Can you try to
the full screen? And
screen? Yeah, it works.
Okay. Okay. Thanks. Yeah. Let me stop here.
Okay. Sam, are you here? Sam, could you try to share screen? He's not here. Zhiyan, are you here?
Hi, I'm here. Yeah, I can try to share my screen.
Thanks.
Yeah, so can you see the screen?
Yes.
Can I switch?
Yeah, it works. Thanks.
Okay, cool.
Should I share?
Yeah, you can start sharing your screen.
Okay. Okay. Okay.
Still have a few minutes. Let's wait to 7 p.m. All right, it's time to get started. Welcome back, everyone. In this evening, we're going to have 7 contributed talks. Our first speaker is Shuhao Cao from Washington University in St. Louis. He's going to talk about Galerkin transformer, a linear complexity attention without softmax. Let's welcome.
Thank you. I really appreciate Haizhao allows me to present my research here. So, and thanks for the organizer. And so today, I'm going to talk about some of my recent research. I think the theme, so here's a summary. Okay, so let me get the summary like up front. The too long didn't read is, the summary is we are standing on the shoulder of giants. So we combine 2 state-of-the-art methods together, and we try to explain one of them. So, and here is our problem. So the problem is parametric PDE. For example, what we have is we can think it's an operator equation, and this is our problem. We want to learn an operator T such that A is our coefficient. A can be in the Banach space or Hilbert space or whatever, and we want to learn a map, a data-driven method, so that we input an A. The method give a solution U, okay? And also, another problem is when we have a measurement U, and we put U and maybe some measurement noises, the model should give us back A, okay? So in my humble opinion, I think deep learning models are particularly suitable for these type of nonlinear mapping because it's pretty efficient in capturing nonlinear mapping. So okay, so let me first use this example. So this is a toy example, and it's from the Fourier neural operator paper. I think earlier Anima already talked about their seminal work in Fourier neural operator in this paper iClear this year. So this is our input, and this is our output. Okay. As we can see, this coefficient has a random interface and has these island-shaped interface. This is like satisfying some distribution. It's push forward of some pure Newman problem, so that at every point, the most likely around it is the same coefficient, but it has some probability to jump to another coefficient. So it formed this kind of a random interface, and this is a solution to this like a Darcy flow problem with a fixed forcing. Okay. Forward problem is using this as input and this as output, and inverse problem is using this as input and this as output. Okay. And when we have discretization, okay, so this is a famous sequence to sequence problem because we discretize, once we discretize the domain, and we have 2 sequences. So it's like, for example, we can have F1, F2 up to Fd, and each one of these are a vector of dimension n. So what we want to do is we want to construct a map from this dimension. So n can be very big. Okay, n can be like 100,000, but d is like fixed. So d is called the dimension of the latent representations, and n is the sequence length. And of course, it's related to our discretization. And if we can afford it, we can make it very big. Okay, so and here are some like operator learners. And these 4 papers are from the Caltech group, mostly led by Andrew Stewart and Anima Anakuma. Okay, so Anima actually gave a talk earlier today, and the state among which the state-of-the-art model is a Fourier neural operator. is last one, this one. I mean, it generates lots of buzz in the iClear 2021. I think lots of people are talking about it. It's like it's surpassing models that 50 times the parameter of it. For example, ResNet, UNet, EfficientNet, and very powerful. And I think it's a milestone method. So in my opinion. And other operator learner include DeepNet. George talked about it earlier today. And other people are using like convolutional neural network to learn some operators. So so here are some and many others, of course. But there are this is I think this is a booming new field. But so now let's talk about the real behemoth in the house. If we view the operator learning as a sequence-to-sequence problem, we have to talk about transformer. Transformer is arguably the most influential work in the last 10 years in natural language processing because it really achieves a sequence length invariant performance. So, for example, if LSTM or other RNN, if we have longer sequences, the performance is naturally degraded because either in training or in evaluation, and because of the structural, this type of thing, because we have to know like previous input to know the next. But attention introduced in transformer paper is a state-of-the-art model. The computation is parallel, and it's extremely powerful. And we can have these, for example, in my in the title of this talk, we have these two Sesame Street characters. One is Bert, the other is Ernie. And I mean, these computer sciences people are really good at naming things. So Bert is a bidirectional encoder representation from transformer, and it's also a Sesame Street character. So, and the smallest Bert has 80 million parameters. So it's very big. And but let's play with it. So so this is a natural question to ask. So this is a figure I reproduced from the original transformer paper to better like represent its math. So let's ask this question. Can we apply the transformer to the operator learning problem related to parametric PDE? So this is a question we would like to ask. And it like transformer, this architecture has so many advantages, and it's very hard to resist to try it. So let's try it. Okay, for example, let's try it in this famous benchmark problem of Visit-Burgers equation, and we know the initial condition. So we know the initial condition, and we want to know what it's like at time 1. It's not like a time 0.1. It's marched so forward in the time. The dependence is totally like a non-linear. So it's not in the like and it's a non-linear equation, of course. But it has a damping term, so it's kind of good. And this is what the problem looks like. So we have, this is like the solution, and this is the initial condition. And these are like randomly chosen 4 samples from the data set. And so let's try to apply it. So this is the result. So the first one is the classic transformer. So, and we apply the original hyperbolic, this positional encoding from transformer. And the next one is Fourier neural operator. And we can, so this is my own re-implementation. So it's a little better, but it's a little better than the original, but much better than the transformer. So this I tried this last year. The transformer had 22 million parameters. It's like, I don't know, 50 times than the Fourier neural operator, but it's almost like 100 times worse. Okay. So let's try to improve it. And we're standing on the shoulder of giants. Why I'm saying this, because inspired by Fourier neural operator, if we view, so because I'm a coder, so I like to read other people's code, and from how Fourier neural operator applies this convolution, this Einstein sum on this matrix, And I learned that we can really linearize it very fast, because this matrix, so this matrix is an m by m matrix. I mean, so this matrix is an n by m, n is the sequence length. It's very long, it's very big. So its complexity computation is n squared by d when we multiply these two things together. I mean, so it's very costly. So it's, even though its performance is a sequence length invariant, but its computational complexity is very bad. Okay. So now, inspired by Fourier neural operator, we linearize it by a very simple way. And we can see that when we linearize in this way, it can be represented by this type of a Galerkin projection representation. So this is like our, trial basis, and this is our test basis. This is our incoming function. Okay. So, and also following this practice, we can simplify it a lot, and we can have this approximation property. And if we have learned finite element, and we can tell immediately this corresponds to a mixed finite element method, which is a saddle point problem. And the interpretation is extremely nice. So using natural language processing people's language, if we have a query, so some incoming query, and it's a function in some Hilbert space, and we want to deliver the best value. So the value is like the output, and it's our trial function space, and the key space is to test the response of this query, and it's our test function space. And the in-soup condition actually tells us the test function space has to be big enough so that we can unlock this best approximator. And exactly, we showed, use this in-soup condition to show the approximation capacity of this linearized attention mechanism. So, I mean, I don't know if ever people has done this before, but it's very nice mathematical theory. However, it doesn't quite work in practice, so we tweaked a few components. The first one is we changed the layer normalization scheme. So we work the layer normalization so that it's almost like something like this, for example. So I believe every one of us have seen this. This is nothing but, for example, Gram-Schmidt. The Gram-Schmidt divides by the norm square. So it's very like a layer normalization. We have to divide something. So we choose to apply layer normalization in this way, and then we apply this mesh-weighted normalization instead of a softmax. No softmax, very fast, okay? And we use Euclidean coordinates as positional encoding, just like a Fourier neural operator, and we, just like AlphaFold 2, so we concatenate it to multiple key structures of the network, and instead of just once, like the original. And what's the result? And here is example one revisited. So we compare Fourier neural operator. We re-implemented it a bit. We changed a few structures, and we use our Galerkin transformer. So we use 4 Galerkin attention encoder layer and 2 this spectral convolution layer from the Fourier neural operator. It's like we allocate 2/3 of the parameter to the Galerkin attention and 1/3 to the spectral convolution. What's the result? We increase the original performance by 200 times. I mean, it's crazily good. And I also compare with the random feature attention from DeepMind and Favorite Plus from Google AI. And but because they are trying to approximate softmax, so I mean, so our point is removing softmax is the best approach for operator learning. So, and of course, the parameters are matching, just 500K or something. So, and the next example is we try to tackle the inverse coefficient identification for Darcy flow. I think this should be example 2, sorry. So basically, we have our coefficient, and this is our solution. Given the solution, we try to infer the coefficient. So that's our problem. And again, so here is our result. So again, the good-looking transformer achieves the best performance, but we can also see that the Fourier, like curiously, actually, Fourier neural operator actually achieves the resolution invariant performance, even though it's like worse than our model. But it's worth, I mean, noting because the spectral convolution in frequency domain has some merit. But so recently, the community start to exploit like a multi-level hierarchical attention, and I mean, which is our next goal. So that's it for my talk, and here are some acknowledgements.
Thank you very much for a nice talk. Any question from the audience? Please feel free to unmute yourself or raise your hand. Eric.
Yeah, so thank you for the nice talk. That was a really interesting. One thing, you know, with regard to transformers, one thing that doesn't make a ton of sense to me is if you have like a sequence that comes from a PDE, where really all the information that you have is encoded in the previous entry for kind of your current, for the update. It's kind of Markovian in a sense. What's the point of looking at the whole sequence to kind of learn these things? You don't really need that information. You just need the local kind of update. Does that make sense?
The answer is, I do think we need, for example, I mean, using the simplest example, if we want to invert this operator, even though this one is local, so this is like 5-point stencil, I mean, it's 5 diagonal in the 2D, but this one is global. In the sense that if we want to invert a finite difference matrix.
For sure.
Right, this one is dense, right?
Yes. I guess my question is more for like the transient case, right? Think of sequences in a true sense, not like, you know, like anything that you would do with a elliptic PDE and spatially, any sequence is artificially imposed by you kind of after the fact. But
yes, so
temporal sense.
I mean, the answer is more light on. So, for example, this one. If we just use local information, this is impossible. So this is the training data. The training data is using a 20 by 48 like a long sequence. And the evaluation can be done like 4 times the resolution of it. I think Anima talked about it earlier today, that originally the CNN approach. So for CNN, for example, for CNN, the dimension, so if we use LeNet, for example, LeNet 5, the dimension is hard-coded. Indeed, we only need, when we tried to, for example, distill the information, for example, image classification problem, eventually our label is in a much lower dimension than, for example, the original information, the image. But right now, we're trying to preserve this information. So sometimes it's even like, for example, so to think how amazing Fourier neural operator does. I mean, after I first implemented it, I'm totally blown away by it. So to think about it, how a network can directly input this image and gives us this. I mean, no ever deep neural network can do this. Only an operator learner can. So CNN can, but CNN cannot be trained on a lower resolution, but evaluate on a higher resolution. So, but we need this sort of a global interaction to get this type of performance.
I see. So your argument is that if we go to kind of a local thing, we lose a scaling.
Invariant thing.
Yeah. Okay.
Mm-hmm.
All right. Thank you.
No problem.
Any more questions from the audience? So how can I ask a question? So do you plan to make your algorithm discretization invariant?
Say it again, discretization invariant, you said?
Yeah, so I think you've discretized the object first. And
yes, we discretize it first. That's correct. We discretize it first. Let me use this again as an example. For example, our model. So this one is, for example, we trained on. So suppose this is our black box model. Okay. So for example, we trained using this type of sequence. This is like, for example, the latent dimension is 96. And this one is 2048. And it outputs another 96, 2048 matrix. And the number of parameters in this learnable map, it does not scale with respect to this number. It only depends on how many bases we choose here. And using this trained model, when we do the evaluation, we can use a much longer sequences. For example, we can give it, for example, the resolution like 10 times the original one. We can still get decent performance.
I see. Thanks. In the interest of time, maybe it's time to for the second talk. Jincai, could you share screen?
Sure. Yeah.
Our second speaker is Jincai He from UT Austin in the Department of Mathematics. He's going to talk about observation properties of deep learning CNNs. Let's welcome.
Okay, yeah. Thanks so much for organizers for such a wonderful workshop. I'm really appreciative for the chance, for the opportunity to present our recent work about the approximation properties of deep ReNU CNNs. This is a joint work with Professor Jianchao Xu from Penn State and Ning Li from Peking University. Okay, so yeah, Shuhao just give a great presentation about how to apply transform in solving PDEs. Transform is very popular and fancy today. So today I will talk about some old fashioned things about the application of CNNs in programs. So let's start our story from from older fashion. That is about the classical CNN structure. It's about, for example, the Net5 is the first, which is considered as the first successful convolutional neural network, like for digital number. And also this AnnexNet. This is considered as the beginning of the new revolution of deep learning. We are coming from the background of computational mathematics. So there are some perspectives from computational mathematics to try to understand and try to improve this CNNs. For example, the dynamic system viewpoint, which is very, very popular recently, I believe. And also we propose to use multi-grid or iterative method to understand also for the reasoning type of CNNs. But there's questions when we start DNN, the first thing is about approximation, but when we start CNN, it seems that here, and there were very few studies about to deal with the approximation properties of CNNs. And so there are people don't believe CNN can have approximation ability, or it seems that people don't believe that we need approximation for CNNs. But in some situation, we actually need, for example, recently we noticed that CNN is more and more popular in numerical PDEs and scientific computing, right? Especially also the similar case what Shuhao mentioned, for inverse program, if you have an input as some observation of your solution and you hope your output is the source term, And if you have a structure grid, and then this map is from like almost from a matrix to a matrix, right? When you talk about matrix to mapping from matrix to matrix, right? CNN becomes a natural choice, right? Also before transformer. Okay, so in this kind of situation, approximation theory becomes necessary for CNN. Okay. So here we start. We first like to show that the approximation theory for classical structure of CNN. Then we try to extend this kind of result to a more popular architecture like a ResNet, Preact ResNet, or ImageNet. Okay, so let's first have a setup of like for notation. We follow the notation in PyTorch. We think about our input. It's almost like, okay, you have C channel, and the spatial dimension is like D times D. You can think about it, for example, say equal to 1 for grayscale image, or say equal to 3 for color image, or say equal to 1 like for if you want to reconstruct the mapping from the solution to your source term, then this U is this X is a solution on this. Is a solution of PDE on structure grid. Okay. And you think about it, you have a kernel with the input channel, lowercase c, and the output channel, uppercase c, and the spatial dimension for this kernel is 2k plus 1 times 2k plus 1. This k can be arbitrarily large, but finally, our main task is like to reduce this to 3 by 3, right? Okay, so then we define this convolution with multi-channel as like this. Then you will notice that right here, this index will exceed the range of the dimension 1 to D. So we needed to pad that. Here we introduce two mainly use the padding. One is constant padding, which means you pad a constant around your input, or you can do periodic padding, which means that you pad your input to be like a periodic function like from each dimension. And then we have this classical deep ReLU CNNs. Here we assume that the sigma stands for a ReLU function, and we will explain later why this can only works for ReLU actuation. And here then we have this CNN. CNN is a special kind of DNN, which means that we just replace the Fourier connection layer by convolution layer. And here, and because of a parameter sharing, we have a special form of bias. And then after all, you will got a third order tensor. Then you vectorize it. You put it as a vector, and then you have this last Philo linear layer. And here we mentioned that in practice, right? In practice, we only apply convolution kernels with 3 by 3 kernel with multi-channel. And here this will stand for like a vectorization, and this B is like to denote the bias. Okay, we first show the approximation for classical things. Think about you have omega. This is a bounded domain in this like a matrix space, but this is just you think about you vectorize your matrix as a very high dimensional vector space, and you assume that this function is like have a baryon norm is bounded. Okay, this baryon norm of this function is bounded in some sense, and then we prove that there exists a CNN with as defined before. Okay, with 3 by 3 kernels, multi-channel. Here we give some this hyper parameters of this CNN, which means we have the depth that only depends on the input dimension. Okay, and we have the width, like the number of the channel, also only depends on the the dimension of input. And here, this output channel for the last convolutional layer, that only depends, that can be arbitrarily large. That will characterize the approximation power of a CNN. That is, okay, look at this order. I guess if we're familiar with this kind of like approximation server of DNN with one hidden layer to deal with like under a setup of like a baryon space setup, we're very familiar with this kind of order, right? So here, then we will we have some properties of this result. Okay, this is for 2D. Okay, which means that right? If you deal with 2D image processing or 2D like numerical PDEs, you can, in some sense, you can may apply this theorem. And here, this result is only for like, okay, which means that it seems like you have just one channel, but actually this can be applied to a multi-channel case. That's I also work, okay. And this convolution here, like before this KL, this convolution is considered as the most commonly used type, right? If we use ResNet, DenseNet, efficient net, or then we just use this 3x3 kernel with multi-channel with the constant padding or periodic padding. Here, one thing I want to mention is that this cannot be applied to a reflection or replication padding. I will show it later because of the important thing, okay. One thing I also want to mention is that this result, right, you will say, because this say L, this L only depends on the dimension of input. So as asymptotically, we achieve this the same approximation rate to this DN with one hidden layer, and we believe that this can overcome the curse of dimensionality, because for a 2D input, this D square, if you say this is an essential dimension, right, that they will be extremely large. So, but anyway, you can always keep this half order of your approximation power. And we will show it later. This can be applied to ResNet, Preact ResNet, and ImageNet. So here we put some remarks about the result. Okay, first, actually we can just use 3 steps to prove this theorem. One is like you have we can establish a connection between DNN with one hidden layer and the CNN with one hidden layer, but you have an extremely large kernel. So, right, this is not commonly used in practical setting, and so we need the following theorem to this is a decomposition theorem for convolution with large kernel. This K can be arbitrarily large. This M is almost like the channel of output. So you can have a series of a small 3x3 kernel. This is a linear result, but this is a pure algebraic and constructive result. And this result only works for constant and periodic padding, does not work for reflection or replication padding. And then you have this result, you just need to rewrite your CNN with one hidden layer with large kernel as a deep CNN, right, with 3x3 kernel. But here you need to put the activation function. So here you need to apply some property of ring rule. You can finish your result. Here I put some remarks about some related work. Like for this work, there's some work. This work deal with one-dimensional convolutional neural network. This kind of convolution is defined by polynomial multiplication. Actually, this step, the first and the third steps are easy to establish. The second step, the decomposition theory, is the key of this theorem. So if you have a convolution that is defined by polynomial multiplication, then if you have a large kernel in this convolution, then your decomposition theorem becomes a decomposition theorem for polynomial, right? So we know that, okay, for polynomial on 1D with real coefficient, we know we can decompose it. We can decompose it to some polynomial with just a linear or a power of linear or power of quadratic, right? So then we finish the proof. But we know that on 2D we do not have any like decomposition theory for 2D polynomials. So that's the reason why we can just like generalize this result to 2D with this kind of convolution. And so that's the reason why we need such a pure algebraic and constructive proof for this for this mostly commonly used convolution operation. And for this result, they can this one can be applied. This one can be applied to the second one can be applied to 2D, but that can only be applied to some special, very special function class. Like the function should be like a invariant transformation invariant in some sense, and this can only be applied to periodic padding. And okay, one thing I want to mention is that for this result, if you have periodic padding, you will have a very concise and straightforward proof. But if you have a padding with constant padding, then proof becomes very subtle. You need to be very careful about the index. And then we try to generalize our result to CNN with some more popular architectures like ResNet, preactive ResNet, and ImageNet. So first is like, okay, actually this ResNet and the preactive ResNet, I want to make a clarification here. That is, okay, these two neural network established by the same authors, okay? But here is distinguished, that is, this is ResNet and the preactive ResNet. They just have a different place to put this activation function. This is and this one is in a general setup. This one is more efficient, observed by the Lex paper from the same author of ResNet. And in our like the dynamic system viewpoint, we are actually thinking about this kind of ResNet. Actually, I don't know. There's no name actually for this kind of ResNet, because if we refer ResNet, especially for computer science guys, they will say this is a ResNet. But it seems that for mathematical guy, when we refer to ResNet, it seems it's this one. Okay. Oh, anyway, so we have such a this following structure of ResNet, but here we needed to put a projection operator here, PL. This is also discussed in the original paper of ResNet, because here we have BL and AL. If we change the dimension of channel, we have to put this one to feed the channel. Okay. And then we have the following theorem. Here we consider that this P is given a priori because. Okay, because you can think about it here. If we will put this PL as 0, so this one will, you can drop this term, right? Then this will just generate to a classical CNNs. Then, right? Then in some sense that is cheating, a proof, right? So, and the other, the other important reason is that actually this identity in ResNet is key, is crucial. Feature of ResNet, we needed to put this one and in priori, and we do not train this in some sense. So here to deal with that one, we needed to put some extra effort, but finally we can still prove this. Okay, and then for preactive ResNet, we still similar to the ResNet, we still needed to given this projection in priori, and but we can still prove it. But here we needed two extra a channel for the last output, such that we can actually deal with this effect of this term. Okay, and then we hope to deal with some ImageNet. First, we introduce ImageNet a little bit here, because if you're familiar with multi-grid just we have just two main components for multi-grid. One is smoothing on each grid, and then along each grid you will have a restriction pooling in the CNN language or coarsening in multi-grid language, right? And we have this structure. If we get rid of this nonlinear activation, we got a pure geometric multi-grid. If we add this is ImageNet. Okay. And then we correspondingly we have ImageNet structure like this, and also this piece is given a priori. Actually, the reason why we are interested in preactive ResNet and we prove the approximation for it is that we can have a simple connection between the ImageNet and the preactive ResNet, and then we can prove the approximation result for ImageNet based on the approximation result for preactive ResNet. And finally, we have some concluding remarks. Okay, so here for this work, we actually the first thing is that we have a decomposition theory for convolution with large kernel on 2D. Okay, for constant padding or periodical padding. Okay, and then we have the approximation theory for the classical structure, and we have for some popular structure. And then we are thinking about some future works, like because for this work we do not involve like a pooling. We want to incorporate pooling in approximation theory of CNN, and also maybe this can be applied to numerical PDEs, Or because here we need to have a bridge that is DNN with one hidden layer. So we hope that we may have some more intrinsic approximation theory for CNNs. Thank you, everyone. You are welcome for question.
Thanks a lot. Maybe we have time for one quick question. Okay, can I ask you a quick question? In the main theorem, the network structure is not typically used in CNN. You have a weight increasing as the index L.
Right.
And suddenly, the last layer, you have a much larger width.
Right. Very good question. Very good question. But we can explain this like this. If you have a CNN, you can have some redundancy, right? So in some previous layer, you can, because here we assume that your previous layer, the channel for the previous layer, just have 2L plus 1. That is a small number, right? If L is small. But for practical CNN, people will like increase the channel a lot, right? After the first few layers. So if that number is large enough, you can think about that you can maybe where I should make this to be like this one should be greater than this number. So then that one can help to explain the real practical thing. But yeah, this one is
that makes sense.
Number. Yeah.
Thanks. So in the interest of time, maybe it's time for the third speaker.
Mm-hmm.
Sam, are you here?
Yes, thank you.
Could you try to share your screen?
Yes. Can you see the shared content?
Yeah. So our next speaker is Sam Buchanan from Columbia University. He's going to talk about deep neural network and multiple manifold problems. Let's welcome.
Thank you for the opportunity to speak. Yeah, I'm a PhD student at Columbia University with John Wright. And John, so I'm presenting our joint work here. John presented this earlier as well. I hope that my talk will be able to shed a bit of light on some of the more technical aspects of the work and complement John's in that way as sort of a technical appendix talk, if you will. And this is also joint work with Dargyal Bo and Tigran Wang. So I'm going to be presenting so the talk's based on a couple of papers. One we presented at ICLR earlier this year, the other we just posted as a preprint. A lot of the notation and topics will be especially drawn from the second one. So if you're interested, I encourage you to check it out. As John, if you caught his talk earlier, was talking about, we're interested in trying to study a model problem for how deep neural networks can sort of provably classify data that have nonlinear low-dimensional structure. Trying to understand these interactions is maybe a path towards understanding how these networks work on practical data sets where this structure can be pretty ubiquitous. So the problem we're studying in this paper and that I'll present now, we're going to call the two-curve problem. And this is a binary classification task where the two classes are disjoint one-dimensional submanifolds of the unit sphere. And the task is like this. So you get capital N IID samples from some density that's supported on these two manifolds. The samples come with labels. And the task is for you to train a neural network with simple gradient descent and guarantee that after not too many iterations, this network is going to achieve perfect generalization. So this sort of strong sense of generalization where you perfectly label the two manifolds from finite samples. A couple of technical details on the data model in this problem before we get into more specifics. So in this paper, we're assuming that the curves are smooth, regular, simple, so they don't intersect themselves, also disjoint, they don't intersect each other. They're closed, so they're topologically circles. And for technical simplicity, we also have this assumption that they're contained in a cap of radius pi over 2. This is purely for technical convenience, and I hope we can remove it soon. So under these assumptions, I'm going to denote arc length parameterizations for the curves by superscript plus and minus x. And throughout, we're going to be talking a lot about two different measures of distance on the sphere and between points on these curves. So the extrinsic distance, I'll call it the angle, is like the spherical geodesic distance between points. And I'll also label the intrinsic distance measured in this arc length parameterization as d subscript m, and just declare it to be infinite if the points are on different components. The network we train here is especially simple. It's just a standard deep feed-forward neural network with ReLU activations. We're going to give it a Gaussian random initialization with the standard parameterization settings of the variances. And we're going to train with, so this randomly initialized constant stepping gradient descent on the empirical mean squared error from the n finite samples that we get. So the difficulty of a problem instance in this model, the nice thing about having the data with low dimensional structure is that we can summarize it in terms of certain geometric and statistical properties of the data. So I'll just summarize them quickly here with definitions and talk about some intuitions. The ones that will show up in our results. So we have curvature. This quantity here, I guess, is the intrinsic curvature, measuring how far away the curves are in a worst case sense from being great circles. We have a separation here. And so although I'm labeling this in the figure as the separation between manifolds, the way it's defined here, it can also measure sort of how simple the curves are. So how close they come to intersecting themselves. So it's sort of a self-separation measure as well. Something we'll need to state some results is also a count of, at a given point, how often points on the other curve can loop back, or the curve can loop back to itself. I'll just denote that by this clover symbol. And we'll also need to use some properties of the density. In particular, we assume for our analysis that the density is bounded below by a positive constant. And the theoretical question we can try to resolve in this nice model, trying to understand the interactions between the network and the data, is how do we need to set these simple architectural summary hyperparameters, the width, the depth, and the number of samples, relative to the geometric properties of the data in a way that we can guarantee the gradient descent succeeds in this problem. So to get into it, I'll just show our main result quickly, as John presented earlier. So the result just is pretty simple to state. If the step size is sufficiently small, and if you set the network depth to be a sufficiently large polynomial in geometric and statistical properties of the data, as well as a mild logarithmic dependence on the ambient dimension, and if you set the width and the number of samples to grow like sufficiently large polynomials in the depth, then very rapidly gradient descent will give you a neural network classifier that perfectly separates the two manifolds. So it's a simple result to state. Took some time to obtain. And I think something that may be interesting here, as far as I know, this is the first generalization guarantee for training deep networks to classify data with non-trivial, non-linear low-dimensional structures. So the nonlinear qualifier is doing the work there. In the rest of the talk, I want to try to give some intuition into the proofs and tell a couple stories around how the different architectural hyperparameters are allowing us to solve the problem in our analysis. So first, I'll just mention the way we're proceeding in the analysis is using this neural tangent kernel regime techniques. So this is a regime where you set the network width to be sufficiently large such that all throughout training, none of the weights in the network change very much. And the final predictor that you get from gradient descent is equivalent to a certain kernel predictor with a kernel that's generated by this sort of taking inner products of gradients of the neural network at different points, evaluated at the random initial parameters. So this has been studied a lot in the theoretical literature, and it's led to some very interesting guarantees for neural network training. And like I was saying, I'll try to tell some stories around this, how this kernel plays a role in our analysis, and some potentially more broad technical contributions that we have, maybe of broader interest. So the first story is about the role width plays. In particular, it's a statistical resource. When the width is large, quantities concentrate well around their expectations, and that allows us to have a sort of deterministic quantities that we can analyze to prove that generalization and fitting proceed. And the depth plays the role in particular as a fitting resource. So when the network depth in our analysis is set large relative to how complicated the geometry is, it gives us an ability to fit better. Deeper networks fit more complicated geometries. And I won't have time to talk about all aspects of the proofs. Please, reach out if there are other things that you find interesting here. So first, the width story. The role that width is playing first and foremost in our analysis is it ensures that this random neural tangent kernel, which is our sort of random process, is uniformly close to its expectation over the initial random weights all throughout the training, the gradient descent training process. And sort of the figure at the right is showing some degree as I increase the width further and further, empirically, I get better and better concentration of one trajectory of this random process around its infinite width limiting value. And so the result we prove here is sort of a new rates of concentration for this kernel. These are uniform rates of concentration. So the bound is a high probability tail bound that holds simultaneously for all inputs. And it holds in the regime where the width grows linearly with the depth. So as soon as the width is growing linearly with the depth up to polylog factors, as well as polynomial dependence on the dimension. So just a couple quick comments on this result. Previous best results for these rates of concentrations for deep ReLU networks were shown by Aurora et al. In 2019. Their rates were quantity L squared over n to the 1/4 power. Their result is more general than ours. The network width doesn't need to be the same in every layer, but we've sort of sharpened these results here. And in particular, the results we have are essentially optimal. So Hanan and Nika have studied concentration of the neural tangent kernel in the case where the two points x and x prime are equal, so on the diagonal. And in that setting, they show sharp upper and lower bounds on the variance. If you integrate out this tail bound in order to get a bound on the second moment, you'll get something that matches up to log factors. And so we can sort of conclude as well that these bounds are essentially optimal, in particular as reflected through the depth. So that's all I'll talk about for the width story. And next, I want to talk about the role depth plays in the analysis. And for that, I need to introduce some notation around what we call the certificate problem. So I will, in the rest of the talk, use this theta kernel notation to denote appropriately scaled infinite width expected neural tangent kernel. And I'm going to use a bold theta to denote the integral operator that's associated to that kernel. So with that notation, the certificate problem, which is sort of abstract, but I'll try to interpret it, is to find conditions on the width and the depth, these two parameters, so that we can find a certain approximate solution to this specific integral equation here involving the NTK and the initial random network f sub theta 0. Actually the initial random error, so that network minus f star. So we need to have a good approximate solution to this integral equation, and it needs to have a small norm. So that part is important. So just to try to put some context into this problem, I'm showing a figure at the bottom where I take a certain data set, the toy one from before, and I compute a discretization of the neural tangent kernel integral operator over that data set, and just sort of quantitatively invert it and plot what the certificate looks like. So one thing we can take away from this specific example is that, so it seems that in this case, the certificate is not totally regular. And in particular, it has these certain intervals where it takes on relatively large magnitude around points where the problem is somewhat harder. So in particular, points where the two manifolds come close to touching each other, or where the curvature is relatively large. And just unrolling a bit in the figure on the right, I'm taking the same certificate plot at left, plotting it in a chart for the two curves, and also showing two different traces corresponding to neural tangent kernels of different depths. So 10 and 100 are shown here. And what we can take away from this plot is that the norm of the certificate decreases as the depth increases. So both in sort of L infinity and in the average sense. So we get an intuition from this type of an experiment that depth can help in guaranteeing that a certificate is small, or that there exists a small certificate for the geometry. And we're going to try to unpack that further. So one minor simplification thing to note, Asaris, is that, so the certificate problem, again, is kind of abstract here. If you're familiar with the neural tangent kernel literature, one point to make is that the existence of a certificate of small norm is more or less equivalent to the target function, this initial random error, having a small RKHS norm in the RKHS that's associated to the neural tangent kernel. So since in the neural tangent kernel regime of training, we intuitively have that the final predictor is equivalent to a kernel method with the NTK, it should come as no surprise that having a small RKHS norm, and by that I mean having a certificate exist of small norm, is very important for both optimization and generalization. So a bit more notation in the rest of the talk. So we can use the fact that we have this Gaussian random initialization for the initial parameters to guarantee that this kernel theta is rotationally invariant on the sphere. So in particular, we can find some function psi such that theta is equal to that function just composed with the angle function. And in the rest of the talk, so I'm going to simplify my life a bit. We do this in the paper as well. I'll work with a version of theta superscript circle, where I subtract off the value at pi. So that just makes the kernel concentrate a bit better. It takes value 0 at the largest possible angle. And we can phrase a corresponding certificate problem with this integral operator instead of the previous one. All that's changed is that we've changed the kernel here. We've subtracted its value at DC, if you will. And we show in the paper how a solution to this problem implies a solution to the original certificate problem. Okay, so just some intuition for why the certificate problem is hard. the natural thing to try to do to solve this problem, well, it's just a linear integral equation. So we'd like to try to diagonalize the integral operator theta. We can always do that because in this case, we have a lot of regularity on the manifolds. So we can find some, in particular, some non-negative eigenvalues and corresponding eigenfunctions such that the operator can be expanded in this way. And we'd just like to use properties of these eigenfunctions and eigenvalues in order to figure out, so how should the solution of the integral equation, the certificate problem behave? What's challenging in this setting, so what you do normally, and what has been done to great effect in the literature, is so in certain highly symmetric geometries like spheres, you have that this theta operator acts convolutionally because the kernel is rotation invariant on the sphere. And as a result, sort of as I see it, you have closed form expressions for these eigenfunctions, which you can use to compute. You can compute estimates on inner products of any sort of function of interest with eigenfunctions, and you can figure out the eigenvalues and precise rates of decay for them as well. The difference in the setting we consider here, where we have nonlinear low-dimensional structure, is that even characterizing the first eigenvalue or eigenfunction is going to be a hard problem in geometry. So we can't rely on closed form expressions if we want our results to apply to general nonlinear geometries. And just to highlight a bit more why maybe existing approaches that could use asymptotic techniques may not work so well in this setting, if we try to formally write down an inverse for the certificate problem, so applying a formal inverse for the integral operator to this initial random error, what we see in this eigenbasis expansion is that what we need to prove that this quantity has a small norm is both a characterization of the eigenvalues as well as precise alignments between this initial random error and the eigenfunctions. So it doesn't feel like it's going to be sufficient here to proceed with asymptotic characterizations of the spectrum of these eigenfunctions. In particular, we need a more direct approach. And what we leverage in the paper is just a couple of qualitative insights, and we see how far that takes us. So what we find experimentally is that this kernel theta decays as you increase the angle, as you move away from zero angle. And as you increase the network depth, this decay gets faster and faster. So at right, I'm just showing this rotationally invariant kernel plotted over a chart for the two sphere at different depths. And we have this sharpening effect. So I've normalized it as well, but with this normalization, sharpness comes through. So we will try to exploit this property, and we will in our analysis by saying, okay, so if this kernel concentrates, sharpens as depth gets larger and larger, maybe we can use depth as an approximation resource in order to approximate this neural tangent kernel operator by a convolution operator on the manifolds that's in particular localized, so compactly supported. I'm defining this operator hat M sub R here with a parameter R that we should imagine is just a sufficiently small number. And what I've done that's different from the neural tangent kernel is I've changed out the domain. So I've localized it as well. I'm not using the angle in the definition of this operator that I'm applying the kernel to. I'm using the intrinsic distance as well. So in our analysis, we proved that there's a suitable approximation property between this operator and the initial neural tangent kernel. And that allows us to solve the certificate problem modulo, sort of working out a lot of the reductions I hinted at before. So the main result we get, so if L is sufficiently large relative to the geometric properties that appeared in the main theorem, then we have a certificate of small norm. In particular, the norm can be sort of controlled using the depth in a very weak sense that satisfies our approximation guarantees. So that's the depth story that I have. Just concluding with a couple of remarks. So I hope that some of these tools may be more broadly useful. Our concentration tools, these analyses, they're somewhat intricate, but they only use the fact that in the initial random neural network, the structure is compositional. At each layer, you're injecting sort of independent randomness by multiplying the previous features by a random linear map. So I think these techniques can be applied more broadly to get good rates in other architectures as well. And the localization analysis can be useful as well because it allows us to proceed in the NTK setting without having a specific diagonalization for the kernel. I think this may be useful more broadly and for higher dimensional geometries and maybe other kernels as well. And although what we're doing here is admittedly very rudimentary, we're sort of in the long term hoping that we're building up towards some kind of a toolkit that helps us to analyze theoretically training and optimization and generalization of deep neural networks instead of just focusing on the shallow case. Okay, so I'm a little bit over, but thank you for listening, and thanks one last time to my collaborators.
Thanks a lot for a wonderful talk. Any question from the audience? Can I ask a question about the theorem concerning the benefit of depth? So you prove that if that is sufficiently large, there exists a function g says such that you have some good benefit. But this theorem, it seems that it does not exclude the possibility that even though depth is small, there might be also some g function satisfying this property. So
yes,
am I correct?
Yes, yeah, and this is an excellent point. So maybe I can say two things. One thing is that, yeah, I absolutely believe that I think this is a very interesting open problem that I hope maybe some of my collaborators will work on around this, which is, I'm not sure if you're familiar with some of the work on kernel regression on spheres that's come out recently, but there exactly the story is that all you need is a depth 2 neural tangent kernel. There's no benefit of depth. And as you say, there's no necessity proved here. This is just a sufficiency result. And absolutely, you can, so I may not have talked long enough to give a sense of exactly what these parameters are corresponding to, but you can get a sense that the rates are not sharp here either. These are sufficient guarantees, and unlike the concentration result, they're not optimal. I do think qualitatively, though, based on looking at how these certificates computed numerically behave for geometries, like in the figure I tried to illustrate with at the start, I do believe that there's a trade-off. If the geometry is very irregular, there's always going to be a certificate, but it will have a larger norm. If you don't make the depth large, you can use the depth as a tool to sort of decrease the norm. And I think it's also interesting to try to explore optimal trade-offs here. So one thing is that I'm only talking about this sort of RKHS norm part of the problem. But if you look at the whole training dynamics, making the network depth bigger, it helps you fit in this sense, but it means you need a larger width and you need more samples as well. So understanding these sorts of very sharp architectural trade-offs, even in the feed-forward setting, I think are interesting theoretical questions. And yeah, you're totally right on the money on the question.
Very good, thanks. So in the interest of time, maybe let's move on to the fourth talk. Zhiyan, could you share your screen? Okay, great. So our fourth speaker is Zhiyan Ding from UW Medicine. He's going to talk about overparameterization of deep ResNet, zero loss, and mean field analysis. Let's welcome.
Okay, so thanks for the introduction, and hi everyone. And first, I want to thank the organizer for letting me introduce our recent work in this fantastic workshop. And today, I want to talk about the overparameterization of deep ResNet. And basically, I will focus on using mean field tools to study the zero loss phenomenon. And this is a joint work with my colleague Shi Chen, my advisor Qing Li, and Stephen Wright. Okay. So in this talk, I will introduce 4 different parts. And first, I will briefly go over the overparameterization and the ResNet. And then I will introduce our main results. And finally, I will pick up some related works to introduce. Okay. So first, I will quickly go through the overparameterization in neural network. So in this talk, we will see the neural network as a tool to approximate our target function yx. And here, x is the input and y is the output. And our neural network is tuned by changing the parameter theta. Okay. So now we define the function generated by neural network as g theta x. And to find the best theta, we need to define the loss function e theta. So in our work, we consider the L2 square loss. And here, yx is the target function, and mu is the distribution of input. And in this formula, mu can be the real distribution of the input, or mu can also be the summation of delta functions generated by the data set. Okay. And then to find the best theta, we need to optimize the cost function. And in general, the cost function from neural network is always not convex. And then according to the classical optimization theory, it's very likely that the gradient descent or stochastic gradient descent will trap in some local minimum or saddle point. However, in real application, these two methods can always converge to zero loss when the system is over-parameterized. Okay, then this phenomenon can no longer be explained by classical optimization results. So it's interesting to study what is the mechanism that allows gradient descent or stochastic gradient descent to find the global minimizer. Okay, and in our work we consider the deep and over-parameterized ResNet. So we focus on the following ResNet model. Here, F is an activation function, and in the formula, L is the number of layers, and M is the number of parameters in each layer. And here, theta is the parameter that we can tune, and G theta X is the output of the neural network. Okay, and in this talk, we say ResNet is deep if L is very large, and over-parameterization means M is very large. Okay, then under this setting, we can also write down the formula of loss functions. And in our work, we consider the continuous limit of SGD or GD, meaning that we let training step go to 0. And then theta is tuned from a gradient flow, which is a ODE here. And here, S represents the training time. Okay. So now I want to introduce our main results. Formally, we will show that when M and L is large enough, then the loss function will be close to 0 when S is large enough. And this is our main theorem. And in this result, you can see that when we choose S, M, and L large enough, the loss function is small with high probability. And this suggests that when we have a very deep and over-parameterized ResNet, it's very likely that the loss function will be close to 0. And here, the lower bound of M comes from the mean field limit. And the continuous limit will give us the lower bound of L. Okay. Then basically our proof contains some key steps. First, we let L go to infinity and consider the continuous limit of ResNet. And the next, we let M go to infinity and consider the mean field limit of ResNet. And in both cases, we can give an explicit convergence in terms of L and M. And finally, we study the limiting gradient flow and prove it will give 0 loss under some assumptions. Okay. So now I first want to introduce the continuous limit. Here we first let the number of layers L go to infinity. Now in our ResNet model, if we see 1 over L as the time step, then when L go to infinity, this basically means the time step H go to 0. Then the ResNet model will converge to our ODE. And the artificial time T is from 0 to 1, okay? And in this limit, our parameters also transfer to parameters depend on T. And we also define the loss function using the output of the neural network, okay? And then the gradient flow of the parameter is no longer a simple ODE. It will become to a coupled ODE, okay? And here, delta E over delta theta is the Fourier derivative. And basically, in this limit, for each fixed T, we have an ODE, and for fixed T, theta ST changes in S according to this ODE, okay? And the right-hand side of this ODE depends on the whole profile of theta ST. So this is a coupled ODE, okay? Now, so now we can also make this limit rigorously. And according to this result, when L is large enough, we can see that the loss function is close with high probability. And we note that this bound of L is sharp in terms of the discretization error, okay? And the second step is the mean field limit. So to consider the mean field limit, we need to let the number of parameters m go to infinity, okay? Then the ODE for C will change to OIE. So here, you can imagine that theta mt is RID drawn from rho theta t. And then the empirical expectation will converge to the true expectation. And the next, since m approaches to the infinity, the set of parameters theta t will be replaced by the distribution rho theta t. And in our work, rho theta t is a curve of probability distribution. This basically means for each fixed t, it's a probability distribution in theta. And the cost function in the mean field regime is still defined by the output, okay? So finally, the gradient flow of theta should transfer to a gradient flow in rho. And here, when you look at this PDE, if you omit the variable t, this limit PDE is the Wasserstein 2 gradient flow of rho, meaning that you take the gradient flow in the space of probability distribution with Wasserstein 2 metric. However, in our case, the situation is more complicated. So in fact, similar to the continuous limit, we will have a coupled PDE here. And basically, we should change rho theta ts in the space of the curve of probability distribution. And for each fixed t, we have rho theta ts changes in S following a PDE. Okay. So similar to the continuous limit case, we can also rigorously justify the convergence of mean field limit by showing the cost function is closed with high probability. Okay. Then combining this theorem with the continuous limit result, we can justify that rho s is the right limit of theta s when L and M is large enough. So up to now, it's reasonable to consider the equation for rho and E rho to study the convergence of E theta s, okay? So then the last step contains the study of the gradient flow for rho. And basically, we want to show that the cost function will converge to 0 when S is large enough under some assumptions. So for the global convergence result, we have the following theorem. We can prove that the cost will converge to 0 under two conditions. So first, rho s converges to some limit rho infinity. And the limit rho infinity has a dense support for some t naught. This basically suggests that if rho converges to some set point or local minimum, then if the limit point has dense support at some t, then this limit point is the global minimum. And in our recent paper, we also gave some conditions when these assumptions can be satisfied. Okay. So now, if we combine the global convergence result and the continuous limit result and the mean field limit result, we can prove our main result. This basically shows that when M, L, S are large enough, the cost function is close to 0 with high probability. Okay. So finally, I want to introduce some related works and some future directions. So in fact, there are a large amount of literature, and I'm not an expert in this area. So I just pick some papers, and there must exist other interesting papers. So the first paper is Yiping Lu's paper in 2020, and our recent work is largely inspired by their paper. And in their paper, they consider a modified version of the mean field limit, where they also see the artificial time t as a parameter to 2. Okay, so the next 2 papers are from Bach and May are also interesting. And these 2 papers study the over-parameterized 2-layer neural network with mean field tools. And their results can bring some hope to relax our assumptions in the theory. Okay, and the last paper also considers the zero loss phenomenon in over-parameterization setting. But they consider the problem in a different way. They consider a different scale of neural network where the neural network will drop into a different regime called neural tangent kernel. And then using some optimization skills, they can also prove zero loss convergence result. Okay, so I have finished my talk and thank you for listening.
Thank you very much for the talk. Very, very interesting. Any question from audience? Can I ask a question about the proof technically for the main theorem? So you have 3 steps. First, you take the depth go to infinity.
Yes.
Second, you take the width go to infinity, and then combine them together. So my first question is, does this can we use the rule activation function in your theorem?
Yes. So this is a very good question. So here you can see in our results, I hide the assumptions for f. So in fact, in our paper, we should consider a C2F. So basically, we can't use ReLU as an activation function, but I believe that we can extend our result to the ReLU activation function, but it's not very easy because ReLU is not C2 or even not C1.
I see. So if we want to extend it to ReLU, so I'm interested in the limit when you take the depth go to infinity. For example, if we fix the width and take the depth go to infinity, then we can prove that with probability 0, you can identify the global minimizer.
Yeah. Oh, I see.
Because of the dying ReLU phenomenon.
Okay. I see. Yeah.
So this means that in your 3 steps in your proof, there might be some something dangerous. For example, your target is to analyze fixed width, fixed depth neural network. When you take the depth go to infinity, that the purpose to take that to infinity is that you want to get something some contained model such that it is easy to analyze and use this model to approximate the performance of the finite width, finite depth model.
Right.
When you take depth go to infinity, that model is dangerous because the dying ReLU phenomenon.
Oh,
this might be something difficult to go through.
I see. Yes. Yeah. So I am being so to be honest, I just learned deep learning like maybe 2 or 3 months ago, so I'm not very familiar with all of these things. But I think what you said is reasonable.
So I'm wondering, is it important to take that go to infinity first? Why not take width go to infinity first and take that?
Oh, yeah. So I think in our proof you can also take m go to infinity first. Yeah, I mean with go to infinity first, it can work. I think.
So then, because if we take width go to infinity first, that means that we use a finite depth network and infinite width network to approximate the original model, and this model is good. It's a good model. We don't have dying ReLU phenomenon.
Okay.
And then we try to take that go to infinity. So maybe this is.
Yeah. So what I want to mention here is, so the reason we also want to take L to infinity is, so here you can see the lower bound of M is independent of L. So basically, basically in some existing zero loss results, they can also do the deep neural network, but this lower bound will depend on L. So, and I think that's one of the reasons we want to take L go to infinity also, but I think your suggestion is right. Yeah, I will think about it later. Thank you.
Thank you. Any more questions from the audience? There is a comment from Sam. So maybe you can also check the comment. There is a reference there. Maybe it's into you.